remarks, but we can still chat a bit before we officially got started. So do you see the opening remarks slide?
Yes.
Great.
By the way, I have started the YouTube streaming, so people can now watch the whole workshop from the YouTube as well.
Alper, could you add Yuqian and Rod as a co-host? Okay, I think we can start. So people are still joining. It's a bit early for, I mean, a bit too late or a bit too early, depending on where you are, but it's we try to make the schedule friendly to as many people as possible. But yeah, it's an international workshop. So, okay, one of the organizing team members of the RSS 2021 workshop on declarative and neurosymbolic representations in robot learning and control workshop. So I'm going to give a brief opening statement, opening remarks. And so I'm one of the main contact person of this workshop, and the other is Alper. So Alper will step in to introduce another component. So we have two components in this workshop. So, okay, I'll start. So first of all, we have a pretty big organizing team because we actually submitted two proposals, and so it happens that the two proposals share a pretty similar theme, neurosymbolic robotics and declarative reasoning in robotics. So the workshop chair of the main conference suggested that could you guys maybe consider merging the two proposals to have one workshop. It turned out it's a very good idea and things are going very well. So we got the chance to know each other and we merged the materials. So I think so far it's actually a good opportunity to have a one merge successful workshop. So Alper is a main contact of the workshop and has been working on many things, many components. Thanks a lot. And then it's myself from SUNY Binghamton. And we have Rode Gruppen from UMass. I think Rode is here. And Yuqian Jiang, a PhD student working with Professor Peter Stone at UT Austin, and Matteo Leonetti. So Matteo very recently moved from University of Leeds to King's College London. I think just 1 week or 2 weeks ago, very recent move. Matteo, are you here? Yeah, I don't think I saw Matteo's name here. And Tiffany Liu from UMass. And Erhan Ostap from Osaka University, Japan, and Ozin Jane University, Turkey. I think Erhan was here, and we chat a little bit. And Justus Pieter from University of Innsbruck, Austria. Yeah, here, right? Yeah. And Benji Rossman. Yeah, hi. So Benji, I think he emailed that because of the time zone, he probably have difficulties joining us today. But still, are you here, Benji? No. So and Tadahiro Taniguchi from Ross Macon University, Japan. And you're here. Yes, very good. And Emery Oger, so from Benghazi University. So Emery helped a lot on the university organization, particularly assigning the papers to different reviewers. So as you may know that we have a very short timeline for reviewing the papers, but we actually give at least one review. And I think many papers we give 2 reviews. Where I think Emery did a fantastic job, and special thanks. So that's the organizing team, and so many thanks to our fantastic invited speakers. So people are very busy, and but thanks a lot for all of you sending us the bio, the abstract, the title, and some of them arrive a little bit late, but now we have all the detailed information about the talks. So many thanks. So the invited speakers include Masataro Asai from IBM Research in Cambridge, UK, and Anthony Cohn from University of Leeds, and Katerina Fragkiadaki from CMU, assistant professor of computer science, and Nichols, University of Oxford on AI robotics, and Leslie Kaelbling on reinforcement learning, robotics and AI learning, and Georgia Konidaris from Brown. And Ben Kuipers, thanks a lot. Ben, you are early here and really help a lot on the junior members of the organizing team. And Luís from UFRGS, and Cynthia Matuszek, UMBC, and Sheila McIlraith from University of Toronto. So again, many thanks to all the invited speakers. So it won't be a workshop like this without all of your help and support. And a side note is that, so other than the invited talks and the panels, so if possible, we strongly suggest the invited speakers to sit in the lightning talks and also stay in the, in the Gathertown session. So I think the authors, particularly the junior authors and the organizing team will really appreciate your participation there. And we hope to talk to you and maybe ask some questions in the Gathertown and other sessions. So please stay as much as you can. But we know that you have a very busy schedule. So feel free to, step in, step out in the middle. But we hope to see you here more. Yeah. So invited speakers and anyone, so from the organizing team, I think I probably missed something or maybe have inaccurate statements. So please feel free to correct me or step in to add anything. Thanks. So from the call for papers being sent out and the paper deadline, it's pretty short. But we were lucky enough to receive some very good quality submissions. So we have 8 long papers, also 4 short papers. So the format of the presentation is that each of the long paper, authors of each of the long papers has sent us a 10 minutes video. So we don't have time to play all the videos edit them into the schedule, but the videos have been there on the website for a few days. So hopefully you have watched the 10 minutes videos. And also each long paper and each short paper is allocated the 2 minutes for a lightning talk. And also each paper, long and short, is given a poster. So there will be a Gathertown board over there, and you will see the posters for all the papers. So please join us in the Gathertown session and talk to the authors and communicate more in there. Okay, that's long papers and short papers. Yeah, we have a few ways of participating in the workshop. So Zoom is an interactive way of joining us. So I think Alper and I has sent the links to all the registrants. I believe so. I think Alper sent the very last email just a couple hours ago.
Yes.
So if you are joining right now from YouTube and you want to talk to us, maybe post questions on the chat box of Zoom, please use this Zoom link. So and we also have YouTube there. So everything is synced live to YouTube. There is, I think, a half minute or 20 seconds delay there, but everything is streamed live on YouTube. We will try to move the questions from YouTube, if any, to Zoom, but so we can't do it very, very timely. Maybe there is a delay, so I'm sorry about that in advance. Finally, we have Getathon. So Getathon, we have a 1-hour session in the very end of the workshop. So invited speakers and of course, organizers and authors, please join us there. And yeah, that will be maybe the fun part of the workshop. Anything I missed? Yeah, and drop an email to at least Alper and I anytime if you have any questions about the format or you don't know how to participate in the event. Okay, so this is the main part. We have about 10 minutes, 8 minutes. So this is we have 2 themes because we submitted 2 proposals that share some common interests. So we decided to merge together. I will give a brief introduction about theme 1, and then Alper, I will switch to, so Alper will share screen and talk about theme 2. So I don't have slides here, but the idea is that there is a classical AI, so people develop rules, and we have a lot of the knowledge representation and reasoning methods that are very nicely and naturally representing human knowledge and do reasoning inference very efficiently. So that is declarative knowledge. Declarative knowledge are developed from by people, for people, and they are very good at what is that? So explainable AI. So things are pretty clear and knowledge are very well structured. But declarative knowledge and the reasoning methods are relatively weak in scalability. Say if we develop very large programs with many rules, we soon find that there might be inconsistency. And if one rule is not correctly developed, that kills the whole knowledge base. So scalability is not one of the strengths of declarative knowledge. Of course, we do have very large knowledge bases, so that's not a general statement. But if we develop small programs, so we find it's pretty hard to make it large about reasoning. And also, it's hard to incorporate a lot of knowledge from different people. So we will find it's relatively fragile when we use classical AI methods. So at the same time, when we develop policies or controllers for robots, people are using more and more of the data-driven methods, learning-based methods. So learning-based methods are pretty robust, and also scalability is pretty good. Particularly when we talk about vision and language, we have the large models that can use a lot of data and pretty good at scalability. But learning-based methods are relatively weak in explainability. And also it's like a black box and pretty hard to see why the robot is making this decision and why it's not making another decision. So there's a complementary features between declarative knowledge representation and reasoning, and also those learning-based methods that is highly data-driven. So that motivates the development of theme 1. to bridge the gap between declarative knowledge representation and reasoning and data-driven learning and control. And we are interested in how they can be coupled within theme 1. So that's the idea of theme 1. And next, I think Alper will talk about theme 2. So Alper, are you going to share screen?
Yes.
Yeah.
Thank you for the nice opening. I guess you can see my screen right now. So for the theme 2, we were interested in neurosymbolic methods.
Sorry, Alper, I see a white screen empty.
Yes, okay, that's okay. So for theme 2, we are interested in neurosymbolic robotics because we are thinking whether can it solve our problems. So the last decade has shown us that deep neural networks can be adapted into many different domains, and most of the time they increase the performance. And I guess most of us would agree that learning representations that are of increasing complexity have some desirable properties. And deep neural networks can partially achieve this objective. Of course, however, there are some things that cannot be done efficiently with deep networks, such as reasoning, symbol manipulation, and there are some other problems with them, such as adversarial input and so on. Of course, these can be addressed, but currently we don't have a good solution for them. And on the other hand, symbolic AI methods operate over a set of discrete symbols and rules via logical reasoning. Once a problem is transformed into appropriate symbols and rules, systems benefit from the full power of search and planning. Yet the biggest downside is the question of what should be the symbols and how should we learn them. Because we have to define them, it's a very hard job to define all the necessary symbols, and most of the time we could be wrong in defining the symbol as well. So now the question is, should we look for different inductive biases or priors in deep neural networks so that they are more appropriate for logical reasoning? For example, convolutional neural nets have the inductive bias for translational invariance, transformers, can learn long-range dependencies, LSTMs, graph neural nets, all have different priors and are better suited for different problems. Or should we look for neurosymbolic AI solutions where we integrate deep neural nets with symbolic AI methods? And most importantly, what do these questions mean in the context of robot learning, where the robot perceives the world as a high-dimensional, multimodal, continuous state through its sensors? So we are interested in combining whether should we combine these two approaches, or should we follow the neural path to achieve the robot learning in the real world? And this is the general schedule of our workshop. So for the 2 hours, we'll have the first mini session. We will have 3 invited talks. Benjamin Kuipers, Katerina Fragkiadaki, Cynthia Matuszek. This will be hosted by Roderick Gruppen and co-hosted by Justus Peter. Then the RSS main conference will take 3 hours. So we'll have a 3-hour break and continue with the mini session 2, and that will take 2 hours. And we will have 15 minutes for contributed talks, and then again for a 2-hour session, the third session with talks of. Let me read the names of these talks. So in the second session, there will be Anthony Cohn, Nick Hawes, George Konidaris, and Sheila McIlraith, hosted by Matteo Leonetti and co-chaired by Yuqian Jiang. And in the third session, we will have Masataro Asai, Leslie Kaelbling, and Luís Lamp. And this session will be hosted by Shichi Zhang and co-chaired by Emre Uğur. And now I can give the screen to Roderick, and we can start the first session. Thank you.
Thanks, Albert. Just a little bit. So I actually made a mistake just now about the long paper and short paper. So there is one paper from Stephen Tomic that's supposed to be in the short paper list, but I by accident moved it into the long paper. So just a little announcement, and sorry about that. Yeah.
Okay, well, I guess we'll begin with the first set of speakers. My name's Rod Grupin. I'm at the University of Massachusetts, and my co-chair, I guess, chair in real sense, but co-chair in title, is Justus Piotr. Whenever I think about the task that faces us today in this discussion, I think about one way to think about it is the difference between, for instance, procedural knowledge about how to do a task and declarative knowledge. And procedural is just how you do everything, which resources to use, how do you deploy them. It's very control, very low level. We're very good at inventing consistent sets of procedural knowledge in order to accomplish myriad tasks. But the new frontier is in scalability, and that's where declarative comes in. So declarative really discusses the entire structure underlying a domain, and that structure can then be extracted and used in abstract ways. And the crown jewel, if you will, of declarative knowledge is the emergence of symbols, which we can use to communicate between agents and form economies by virtue of the structure we can exploit. So today, the first set of speakers are going to be talking about declarative knowledge and its use in robot control and how it really is going to bring forth that next generation of robotics applications. Our first speaker in this quest is Ben Kuipers, who I've known for quite a long time. He's a professor of computer science and engineering at the University of Michigan, where he studies and has studied for a long time AI and robotics, in particular representations and means of learning, common sense knowledge of space and dynamics and objects and actions. And so you can tell he's really doing it all and looking at that frontier square in the eye. He has recent work that he's been doing on focused on ethics in robotics and how robots might eventually someday function as contributing elements of our culture and society. Today, he's going to be speaking about acting, learning, and knowing in large-scale space. So Ben, it's all yours.
Thank you very much. Let me just get my slides going. All right. All right.
Ben, one more thing. I am supposed to make sure that you're comfortable with the recording before we go forward, because we are, as you can see, started to record you.
Yes, that's fine.
Okay.
Okay. Oh, I see what's going on here. All right. So I'm trying to make sure that we have all the clocks and so forth. Well, as Rod said, thank you for the introduction. I've been working on good old-fashioned AI for a very long time, and in particular, knowledge of space for a long time. And I got started looking at knowledge of large-scale space. So why look at knowledge of space? Well, one of the really critical reasons here is that space is everywhere. And so it's not only an important kind of knowledge, but it seems to be foundational. For an embodied agent, you need to know what the structure of your environment is. And you live in a continuous physical world, but it's extraordinarily complicated. And so you need a scalable representation that will allow you to comprehend the structure of the space and then be able to make plans. And so here I'll talk about you because I want this to be a model of human common sense knowledge, but I'm also interested in building models for robots. So as I might make a reference to our robotic wheelchair sometime that learns the model of an environment and carries a person around. An important distinction to start with is the distinction between small scale space, which is the space within your perceptual horizon. So I can explore a small scale space by just shifting my attention. Whereas large scale space, the space in a building or in a city, has structure that's large relative to the perceptual horizon of the agent. And so the way that the agent can learn a model of that space is by traveling around in it and knitting together information from its different experiences. And so clearly, there will be a lot of experiences, there will be a lot of perception, and scalability will be a continuing theme here. Now, when I talk about small scale and large scale, there are many, many other kinds of space that are worth thinking about, including, for example, configuration space, when you learn how to manipulate or reach something, and for that matter, tactile space. Now, knowledge of space is also widely used metaphorically in natural language when talking about many other kinds of things. And I would definitely recommend a famous book by Lakoff and Johnson called Metaphors We Live By. Let's see. Now, a key thing that came up as we started looking at knowledge of space is that people, and therefore robots eventually, use multiple representations for spatial knowledge. And so any representation for spatial knowledge that has one straightforward representation is clearly inadequate, because when you notice how people function, they use different representations, and they're very good at jumping back and forth between them. So people are very good at learning a local model from local experience. So small scale space, if I look around, I get a pretty good model that is capable of letting me manipulate objects. It's also not terribly hard, and we'll see some examples of this, to go from not one representation to another. So if I have model of local space and I go out into the corridor and down the corridor, I can build models and connect those. If I build the right kinds of representations, then many things are easy, and this is a key to scalability. If I have a topological representation of my entire space, then planning becomes easy. It's simply a matter of search. If I have an appropriate representation that maps to natural language conveniently, then learning is easy, and explaining to others is easy. And if I have multiple representations, robustness falls out of the availability of alternate representations. So one of the keys that we developed is a hierarchy of representations. Hierarchy is a common theme, and we'll need that for scalability, but this is actually a hierarchy of representations. And we initially called it the spatial semantic hierarchy, and various developments on this became the hybrid spatial semantic hierarchy and the hierarchical hybrid spatial semantic hierarchy. But let's just call it the spatial semantic hierarchy. And it consists of 4 distinct representations that I'm going to spend a little time talking about. And they're generated by metrical representations of small scale space, topological representations of small scale space, topological representations of large scale space, and then finally metrical representations of large scale space. And these end up being connected in a way that we see. And the robot is able to learn these very conveniently from exploration experience. Some parts of it can be learned conveniently from a graphical map or by explanations from people. So let me look at the, just a second here. I want to, all right. Let's look at the map of local space. So we have SLAM algorithms, simultaneous localization and mapping. And if I have a bounded area and I have some sort of sensor, and in this case, we've got, we're using LiDAR sensors, then the robot, in this case, it's a LiDAR sensor with a 180-degree field of view. And the robot, upon seeing that, if it just turns around, it can very quickly integrate that and build a model of local space. And so that's been a technology that's been available for several decades, building on probabilistic models of space. And what that's giving us is these capabilities, building a local SLAM model, which is useful for local motion planning and hazard detection, can be built very quickly and accurately. There are difficulties with SLAM, but most of them come up when it's being extended to larger scale space. But a second representation looks at that local model and then takes the continuous space and abstracts the control laws to local actions and affordances. So here we have the same environment. This is going to continue that previous 2-second clip. It builds a model, but now you'll see it detects 4 affordances. Here it detects 1 affordance out of this place. It's going to find the 4 again, and then it's going to head on up this that corridor. So affordances are opportunities for action. And so what the robot is doing is learning, let's see if we can find that here, is it's learning that there are 4 opportunities for action that are qualitatively distinct equivalence classes. So if you go to this place, then you're choosing to move into that part of the space. If you move up here, you're choosing to go upwards. Once we have that kind of model, we can now abstract this continuous model of space into a very concise, compact, discrete model, which obviously is going to lend itself to building a graph-structured model of the entire space. And so this is going to ground the notion of a place, in particular a decision point, by characterizing its affordances and their geometric relationships. And so what was continuous under this representation is now discrete and easily searchable under this other representation. A similar kind of abstraction takes place in terms of handling control laws that can move along a path segment. A control law that moves from one decision point, there's always going to be a little bit of cumulative error, but if it falls within the basin of attraction of the next decision point, then it can eliminate that accumulated error. If it decides to go in the other direction, then it can do that successfully as well. So it allows this continuous pattern of behavior to be abstracted to a discrete link and provides a grounding for those symbols. Now, exactly how we translate that into, say, the tools that a deep neural network gives you, is not necessarily straightforward, but I'll leave that as an exercise to the reader. Now, once we are building models that describe a region in the space as something that looks like the node of a graph, and here we have the edge of a graph, we're inviting ourselves to construct a whole graph. And so the experience that the agent has as it travels is that it experiences a sequence of decision points and path segments. And so it needs to go through a process of topological SLAM, constructing a concise graph. And what that graph tells you is how large loops are closed. And so complex places like office buildings and hospitals and some subdivisions end up with lots of different places that look exactly the same and lead to ambiguities in the structure. And so the process of creating the topological map has the task of resolving those ambiguities. So here's a very simple example. If we're moving through a space where it experiences a T intersection, then a second T intersection, then a plus intersection, an L intersection, and the fifth place is a T intersection, which we, from our experimenter's point of view, can see is the same as place one, but the robot doesn't know that. Then it has to create and search a tree of maps in order to figure out what that structure is. And we'll get to that. We'll say a little more about that in just a moment. But once we have a global topological structure, that can be used, that specifies how large loops are closed, and that topological structure can be used as a skeleton to build a global metrical map, even though, and it can be accurate and precise, not messed up like this is, even though it's much larger than the perceptual horizon of the agent. Now, as I mentioned with this tree, that has the potential for being quite difficult. And so it could potentially be inefficient. And so if we exhaustively search that tree, we get a lot of possibilities. But in fact, my student Colin Johnson came up with a lazy evaluation scheme that makes that efficient and very practical. He also showed how we can build topological methods that are hierarchical so that we can get scaling. So if this is the topological map of one floor of the building here at the University of Michigan, then that map is the detailed map of the third floor. And the building as a whole has 4 floors, which are connected by path segments that correspond to the elevator. But that building is in fact this place, destination, connected to a topological map of our campus. So hierarchically structuring this allows you to have a set of concise maps at various scales. Now, what I've focused on is the representation and a certain amount about how that's learned. And the important thing is that having multiple spatial representations makes it easy to represent this knowledge and to learn it, to communicate it to other things, and to do planning and acting. Now, since a lot of that work has been done, people have built on ideas like these in order to make very large scale applications like GPS, Google Maps, autonomous vehicles, and so forth. And so we'll see those in just a second. It's worth taking a moment and pointing out that the different representations lend themselves to straightforward mappings to different kinds of communication methods. So I wanted to talk about some of the much more recent things. Here is an example from Waymo, I believe, of a local metrical map of the static environment around the vehicle. So this is the model that it uses. Meanwhile, it also has to take that static model and build models of the dynamic obstacles in it, the things that it needs to avoid as it travels along. And here we have the modern up-to-date version of the local decision model that organizes the affordances at a realistic intersection. And of course, everybody has had experience with GPS, which uses those local decision models and various graphical methods in order to communicate the next decision at the next decision point in a planned route. And of course, planning those routes is done in topological maps. And we can, for various purposes, build global metrical maps. In many cases, those are only useful if they have topological overlays of various kinds. Now, I wanted to close by saying, all right, we now know that we need to use multiple spatial representations. And we know how to engineer these large-scale applications using those. But those are often sort of kind of put together in well, I'm not sure I'd want to say ad hoc, but well, let me walk away from that question. The real scientific question that we as AI researchers would like to answer is, how does an agent, whether it's a human agent or a robot agent, use spatial knowledge to make sense of their experience? And how is that learned? How is the ability to do that learned without guidance? So that must be some combination of individual learning from experience, but also evolutionary learning over large-scale amounts of time. These engineering applications are, of course, the result of intelligent design. And so we really would like to be able to say that the ability to use spatial knowledge must come without having an engineer to explain how it all works. Another way to describe this is to ask, where does meaning come from? Meaning is what we have in our knowledge representations. And spatial knowledge is a good restricted domain for exploring that question. And so here's a bunch of references about the stuff that my group has done in this area. But I look forward to hearing the presentations later in the session that can help us answer some of these questions. Thank you very much. Rod, I believe you are muted.
Yeah, my button click didn't work. Organizers, do we have time to take a few questions here?
I think we are taking the questions in the
panel
session, at the end of the session, yeah.
Okay. Okay, Justus.
All right, my name is Justus Piada from the University of Innsbruck in Austria, and I have the pleasure of introducing Katerina Fragkiadaki, now our next speaker. She's also interested in space, but her focus is on leveraging video to teach robots about space. And sorry, my windows keep jumping around on my screen here because all kinds of things are happening in Zoom. And so today she is going to talk about object-centric 3D neural scene representations for visual motor control. She's been creating a very steep career, has already accumulated quite a few awards in her still young resume, and is accumulating citations at a steep rate. She obtained her PhD from the University of Pennsylvania, spent then some years with Jitendra Malik at UC Berkeley and at Google Research. So now I'm excited to hear your talk, and I won't eat any more longer into your time. Katerina.
Thank you so much, Justus, for the kind introduction. Thank you for your invitation. How many minutes shall I be, 20 or 15? Because we're a bit we're behind schedule. Shall I try to make it shorter, or?
Take 17 minutes and Ben owes you a drink.
All right. So yes, exactly like Justus says, what this talk is also about the space. It's about spatial representations. Just to motivate our spatial representation, I want to discuss it. One work we started with 3 years ago, which was given a human demonstrating a video, can a robot imitate it without pre-training, without a big library of inverse models, just directly by watching the video? What understanding of the visual content we require to complete actually this imitation problem? So I would say straightforward answer would be to represent the video as a graph of entities in different levels of abstraction. So some entities are objects, and some other smaller entities are parts inside the objects. And then every frame in the video is a graph that connects the nearby entities. Okay, and then ideally we want to learn to place attention to the important relationships between the entities so that we complete the imitation in the following way. Here in the first panel, we have the human trying to imitate. Here we have the robot. And as you see, the hand of the human is mapped to the hand of the robot. So we have like this symbolic mapping, let's say. Okay, so we establish correspondence between the two graphs. This is in detail what happens. And then you use this as a cost for trajectory optimization. And the cost is how well the edges of corresponding entities match across the two videos. So how well you can imitate the human much depends on your ability to correspond across the two videos. And indeed, this is the most important problem in computer vision: correspondence, correspondence, correspondence, the three most important problems. How did we learn those entities? Well, we had to start with state-of-the-art object detectors do not work, so you need to use data augmentation to get them to work in this particular video. Then we did a trajectory, we used triangulation to train those point entities by looking at the scene from different viewpoints and so on. So different forms of self-supervision to actually learn to reliably detect those entities. And the best entities here are the finger joints, because you can easily detect them simply because people have annotated them on thousands and thousands of images. All right, so just simply by supervised learning, you can actually do well following the human hand. But what is the problem with these representations? So as you'll see here from our results, we always pick a viewpoint that is very convenient. There are no occlusions. There's no fast motion so that you don't lose track of the entities and so on. And the camera is not moving, right? So if the camera starts moving, and if the camera moves differently between the imitator and the student, then those edges, the edge lengths change simply because of the 3D geometry of the space. So we identify those limitations on 2D representations in general. The fact that how the scene looks like much depends on how the camera is moving. So we really need to dig out a representation of space that is independent, or rather disentangles the camera motion. Okay. And the question is, how do we do that? Do we go all the way to 3D or not? To 3D or not to 3D for Visuomotor control? Here we have Rod Brooks telling us that complete 3D reconstructions of the external world are not they're both hard to get, but also may not be necessary for agents to act in a competent manner. Still, alternative solutions is not. So here is our solution. Our solution is still build 3D representations still represent the scene as a grid, as a 3D grid, but instead of having a point cloud or a mesh, some explicit geometric representation of space, rather represent it as a 3D grid of features. All right, so every XYZ location of that map that I'm showing, so this you see a cube, this is the scene. So at every grid location, there's a long feature vector, which is, I visualize here using only the color. So I use PCA and keep the 3 first principal components and map them to an RGB value. And why this is important to have these features? Because you should be able to train those features end-to-end for whatever is your downstream task, whether it's visual imitation or instruction following or object detection, okay? And now, just to compare with SLAM also has the, also has this beauty of taking a 2D video as input and separating how the scene looks and captures that scene appears in this point cloud map that you see there, and the camera motion, which is this nice blue triangles, okay? And it has object permanence, like you saw there a teddy bear. That teddy bear was not present at every frame. So objects do persist in the point cloud map. But the problem with SLAM is that next time, even if I've been around thousands of office scenes in the past, next time I go to an office scene, I won't be able to predict what's behind what I see. I still need to go all around and map my scene again from scratch because there's no memory, so there's no learning. So how can we add the ability of a modal completion to our, let's say, models? And this is what our architectures have been doing the last 1.5 years. So this talk is exactly about those representations that I'm going to discuss. A model, we call them a model of 3D feature representations. How do we learn them without supervision and their application in object interactions, skill, policy selection, and instruction following. So the idea is very simple. You get a 2D video as input or 2.5D video as input, and there is a network architecture that maps this video into this 3D feature grid of the scene. And for now, we can assume that this video depicts a static scene, a scene where only the camera is moving and not the objects. And the new thing with respect to previous representations is that the latent state, instead of being 2D or 1D, is actually 3-dimensional, so we don't collapse any spatial dimension. And the update of that map, it follows the SLAM idea of being ego motion stable. So we estimate ego motion and update the features. So here is a visual depiction of what I'm describing. I show you a scene coming from a table, like a countertop, okay? We take this image and the depth map and we unproject it into a shell where we put the different either RGB colors or 2D features in the right location in that shell if you have the depth. If you don't have the depth, then you need to array cast that specific feature all along the array inside the 3D volume. So this is, let's say, the unprojection operation, right? Reverse projection. After that, this passes through some 3D convolutions and instantiates the map. And when the new frame comes, and again, you do the same processing, you really need to estimate the 3D rotation and translation of the camera and fuse the features together in a geometric consistent way. So if you move to the right, if the camera moves to the right, those features need to be placed to the right in the 3D feature map that you are building, okay? And again, the next frame, again, the same thing. So it's a neural network that has essentially SLAM in its bottleneck, okay? And the benefit, well, we get the benefit of SLAM, which is the stabilization, which means that despite the fact that this yellow dot on the handle of the coffee machine changes XY location in image space, it's always placed on the same location in the 3D map, in our 3D feature map, exactly like SLAM. But in addition to SLAM, this map can be rendered and give you the scene from different viewpoints, despite the fact that you have seen only the front view. And how do we do that? Well, we can teach the network how to imagine missing content just by asking it to do view prediction. So view prediction means that your agent gets a query viewpoint as well as its, a query viewpoint and the corresponding image. And then this task is to predict the image. So the way we'll do this is we'll reorient the map and we render it in some, inverse graphics plus learning combination way. And then we'll compare it with the image. And once you do this training, then we're using a lot of different images, and this is all self-supervised. You just need to have ego motion available and you to be able to move around the scene like an embodied agent. And then this network can take a single image as input, and you can ask it to render views of all alternative viewpoints and ask it what it thinks of how things look from different view. In the same way that when we look at our screen, what I look right now is that we can also imagine what's behind, right? So we can understand the space beyond our visual observations, but rather, the 3D arrangement and so on, at least qualitatively. In having an explicit, what we call 3D bottleneck in the network, it gives you fantastic generalization abilities. So here I'm comparing with another network that does view prediction. I mean, you can grab any architecture and give it different multi-view images and ask it to predict those images. And our network, although it was trained only on scenes of 2 objects, so both models here are trained on scenes of 2 objects, this, what we call geometry-aware network, GRNN, can predict how the scene looks from different viewpoints, even when you add more objects in the scene, while the other model can still see only two objects, as you see here, right? So this is the problem of generalization when you have learning architectures, right? You want to have some meaningful generalization, what I'm showing here. So the 3D bottleneck, the spatial bottlenecks allows you to have this generalization. So the question is, what are we going to do now with those architectures that look at images and imagine in their bottleneck the 3D feature map of the scene that this image depicts? Well, we can detect objects in this map the same way we detect objects in 2D. From 2D images, we can detect objects in that latent 3D map, and there's going to be 3D object detection. And now I'm going to show you how we can use these architectures for the 3 things that I said. So the first is, let's predict how objects move under interactions. This is a problem that we found very interesting in 2016. When I was still a postdoc in Berkeley, we said, okay, there is a billiard, and we want to predict what's going to happen. So this was our results from back then, ICLR 2016, which we used this toy billiard environment, and now people use maybe more advanced environments, but all the environments are 2D. So everywhere you have this planar scene, and you have the objects, and you need to predict their 2D trajectories. And so now what is the architecture? The architecture will detect the objects, feed them into a graph network, a network that essentially computes node features and edge features within this graph. And then for every object, predict its 2D future trajectory. And the big problem is exactly the 2D assumption, right? Because you need to assume a planar world. Every object is all the time visible. So now that you have GRNNs, you can take this 2D image or 2.5D image if you have depth and lift it into this 3D feature map in this imagination. And then do the same graph reasoning, detect the objects, fit them into your graph network and predict their future 3D rotations and translations. And, you recurrently, kind of unroll the network over time. And the benefit is that even the objects now will not get occluded in a 3D feature map. The objects will persist in that space that you are imagining. So you see here the robot is 2D, but imagines 3D in that 3D color feature map. And the other benefit is that you may see the same scene from different viewpoints. Your predictions will be the same because of your viewpoint invariant representations. And we show that, not only you can push objects, you can also drop objects from the ceiling and so on, and other type of object interactions. And the objects have different colors and shape. And we compare with other architectures that either, use only XYZ locations for the objects, so forget about the appearance, just to stay in the 3D space, or stay in 2D space. And, these representations do better. Okay, and we also did this in the real robot. Of course, you can use those dynamics to push objects to desired location using model predictive control and so on. Now, the second application of those representations is for policy search, for policy learning. So the standard vision to action mappings either take some XYZ representation of the object and map it to actions, and the XYZ unfortunately doesn't have the appearance of the object, or take images and map them to actions. Now, instead, on the left is very data efficient, but cannot generalize to new objects. On the right is very data inefficient because you need to learn to map those, high dimensional images to actions. but of course you can capture appearance of diverse objects. The network sees the different objects. So what we propose instead is find the objects in your workspace, build their 3D feature maps so that you are independent of the viewpoint, so you are not hostage of where you're going to place the camera in the real robot, and then use those features as a selector on which behavior I should use to operate on this object. Okay, and you can learn this selector in a very, using very few samples with reinforcement learning. You have different controllers to pick up this object, you try them out, you see which one works, and you update your features to actually retrieve the correct controller. And here is a demonstration. We have different behaviors of some can pick up the object from top, some can pick up the object from the side, some can pick up the object from even lower, and so on. And you can learn those 3D feature representations to do correct, controller selection for different objects. And these controllers for grasping are open loop, for pushing their closed loop policies that only use the XYZ of the object because the 3D features already capture the appearance. So these are some comparisons with previous methods and so on. And I mean, for the interest of time, I want to discuss about instruction following, and this is the last topic, which is how now can we follow instructions, okay? How can we say, put the Mac behind the keyboard? The standard representation in the literature will take the image and we'll take the description and feed it into some big network, and we'll spit out, let's say, actions. We'll fuse, let's say, the image and the language stream, and we'll spit out actions. We have found in our previous work that this actually does not generalize very well. So now what we do is, first, when you tell me a particular scene and you tell me, oh, imagine a second keyboard to the right of your keyboard, or put your cell phone inside the bucket, and so on and so forth. First, we take the language and vision and spit out an imagination of what you're telling me, right? In terms of a compositional 3D feature map of the scene that has the different objects in different arrangements. And then we take that imagination and then we feed it into our policy search, for example, trajectory optimization, LQR, which will have now the objects in their XYZ locations and will be much easier to learn. So basically, you can learn this language to vision mapping without involving manipulation first, and then have the robot to act on the imaginations that you learn. Something that we find very, very, so now I'm going to go into details about this. Something that we found very, very interesting from linguists is there is, for example, this theory of simulation semantics, that we understand language by simulating their content, using similar constructs to perception and control. This is one great example. He used a newspaper to protect his face from the wind versus you use the matchbox to protect his face from the wind. We can simulate what the sentence says and says that the first makes sense while the second doesn't make sense. So how can we get our robots to do something similar to that? Instead of learning from language and images, we're going to learn from language and scenes. So we're allowing our agent to go around the scene and build those 3D feature maps. And there we're going to learn generative networks that map noun phrases, green rubber cylinder, to a 3D feature map of the object, blue ball to another 3D feature map of the object, as well as spatial modules that you'll tell them, put this to the left or to the right or behind or inside, and learn the 3D offset placement. And each one of them is stochastic. Every language can have multiple realization in terms of different object configurations and different spatial offsets. And based on your predictions, you will put the objects in a canvas and render and make sure that when you render, you agree with the input images. So in this way, now we build a compositional generative model from language to the 3D scene configurations. And you can use now these two and can give you at test time much, much longer configurations, and you build your imagination and ask the camera to render it all around. And because I really don't have time, I just want to show you how now we can use this for instruction following. When we take a scene and you tell me, put the blue sphere to the right of the green cube, the first thing I want to detect the objects that you're mentioning. Then I need to imagine the objects that you are referring to that are actually not in the scene and place them in the right location. So this is exactly what we did in simulation in the real world. And again, this is the same as before, is zero shot. The robot hasn't trained before. But however, it knows the agent has gone around scenes and knows how to map language to 3D visual imaginations. And then we use these 3D imaginations to guide LQR to learn the correct trajectory. So in conclusion, what we discussed entity-centric representations, mostly object-centric representations for imitation and visual motor control. We discussed about building a model 3D feature representations from images to the full 3D feature maps and their applications to skill selection, object dynamics learning, and instruction following. So thank you very much again, and I'll be happy to take your questions later.
Yes, thank you very much, Katerina. Sorry that we are so short of time, but there will be the Q&A and the panel afterwards. And now
Yes.
I'll hand over directly to Rod for a third speaker.
Yes, thank you, Katerina. Excellent talk. Our next speaker is Cynthia Matuszek, and she is an assistant professor of computer science and engineering at the University of Maryland, Baltimore County. She works on a whole bunch of stuff that's relevant to our discussions today: robotics, HRI, NLP, machine learning, in particular, active learning for grounded language acquisition, which will be represented in her talk, I hope, as the title suggests. And mapping noisy and unstructured, chaotic information on signal streams into language, human languages. She's the director of the Interactive Robotics and Language Group at the University of Maryland, Baltimore County. Today, as I hinted before, she'll be talking about grounding language symbols in percepts and concepts. Cynthia?
All right, thank you very much for the kind introduction, and thank you very much for inviting me to be here. So as Rod said, thank you. I'm Cynthia Matuszek. I'm going to talk today about grounding symbols that we use for day-to-day communication. That is, I'm going to talk about grounding natural language in a context provided by robotic sensing and contextualization. So what do I mean by that? In this talk, I'm going to talk about how the robots that we have can use grounded language to interact with people. So natural language is one of the core symbol systems that we deal with every day. It's one that's closely connected to symbolic reasoning and computation, and one on which a lot of our formal symbolic reasoning systems are based. And it's important that robots that go in human-centric spaces be able to interact adaptably. But right now, flexible is like one of the main things our robots aren't. We're still pretty bad at novel, dynamic situations and needs. And my goal is to have robots that can depend on instructions and information from the people around them to overcome that. So as you can imagine, this is a pretty multidisciplinary space. It needs robotics, natural language, human interaction. And since the goal is specifically for robots to deal with dynamic environment, it also requires learning. So there's a lot to say about all of these pieces, but in this talk, I'm going to talk primarily about the importance of being open to a wide variety of kinds of learning, and then some about using speech as a language source. So what makes language grounded? When I keep saying grounded language, is the idea that instead of language being learned by sort of careful programming, by formal representations or in a vacuum, we can learn it from interactions with the world. And what we learn can be an explicitly symbolic representation, something that's declarative, or more likely, if we want to extend it to a large set of things, it can be something that we learn from interactions involving perception, which is harder to represent purely symbolically. So in many ways, it bottoms out in kind of the classic symbol grounding problem. How do we take these terms and turn them into a representation that we can reason over? And that's the core question I'm trying to address in my work. So I treat language as a collaboration mechanism. The successful interactions between humans and robots are functionally ones where the robot does what the user intends. And natural language is a nice mechanism for that. It's good for teaching and directing and customizing your teammates and providing information about the environment. Language about the world is grounded language. And I want to point out, and I'll elaborate on this in the next slide, that when people say grounded language, they don't always mean the same things by that. That varies a lot. But what I'm talking about in the course of this talk is grounded percepts and actions. That is how the symbols that we use to interact and convey information can be grounded out in the kind of perceptual, noisy data that robots deal with. So fundamentally, grounded language bottoms out in referring to real things in some context. This is the core, traditional symbol grounding problem, which is not new as of our recent resurgence in interest in combining systems. And this is made somewhat more difficult by the fact that our subdisciplines, as I mentioned, mean slightly different things by the idea of what does context mean. So for natural language people, context means the linguistic context, the words around the words. If you can answer questions, about statements, and so on. For vision people, language tends to mean referring to, retrieving, or generating, imagining images and spaces with language. In cognitive systems, context means the combination of all past experiences with all current knowledge, current belief state. But in robotics, the space in which I work and in which I'm talking, the context in which language occurs is the literal physical context, the objects around us, the actions that are taken, the things in which that you can poke, that the language bottoms out in. So we're trying to learn from novel language about novel things in dynamic environments from heterogeneous people. And obviously, when I put it that way, that's a very large scale problem. So one of the things that I'd like to note here is that while machine learning, neurosymbolic methods, and deep learning is our current big toy in machine learning, deep learning is our current big hammer. We just walk around hitting things with it to see what happens, right? And so far that's going pretty well. But language grounding is a fundamentally multifaceted problem. No one thing is going to be the approach that solves it or even solves any large swath of it. So other approaches, so I'm not going to talk about deep learning today. Other approaches are critical for solving other pieces of the problem, such as geometric methods and information theoretic approaches. And I'll talk briefly about some of our recent work that tackles kind of a subset of those problems. So one way to think about grounded language, and the way that we like to think about it with these joint models that we learn, is to think of it as a sort of a shared embedding problem. In that sense, symbols and language and percepts and sensory inputs both refer to some real thing in the world. It may be an object or a type of action or a complete task, but it's something that's mediated for a person by the language that they're using, and it's mediated for a robot by its ability to sense the world. So this is a doubly mediated, non-observable thing. And that conceptualization is useful because we know a lot about different ways of discovering and using shared embeddings. So one way that you can tackle that kind of shared embedding question is as a product of manifold alignment. And in manifold alignment, featurized language and sensor data are treated as projections of some underlying manifold of a non-observable space. So the goal is to find the functions that approximate the manifold. And that can be done using a variety of methods, but it can be considered as a geometric analysis method because that's fundamentally what we're trying. We're trying to find a literal, functionally defined manifold that describes some space that's projected versions for which the observed speech and the observed world are lower dimensional projections. And if you can treat it that way, successfully, then that means that you can learn alignments. You can learn alignments from those shared, describing those shared embeddings between heterogeneous data sources. So you can use deep metric learning to learn a projection of data to an embedding space where intra-class distances are smaller than interclass distances. But my intention is that the learned metric and embedding can't capture the semantics of the paired data. We care a good deal about semantically well-formed representations. So what we want to do here is use data from heterogeneous domains to learn metric embeddings. For example, in language, if somebody refers to something as a tomato while gesturing to it so that the robot knows to direct sensors to it, then we want to learn two embedding alignment functions that map those sensor inputs and that language data respectively to some shared representational space that we can then ask questions of. So one way to do this, we've done this successfully using triplet loss. And triplet loss is just a function that directly encodes the idea that samples from a common class should be closer per some district metric in a shared embedding, while forcing dissimilar samples to be farther away. So specifically, we're trying to minimize the distance between an anchor point. And here, an example of an anchor point is the perceptual inputs of an object that's been described with an associated sample in another modality, which in this case is the symbolic description, the language describing that object, something like a red tomato on the plate. And while in the shared embedding space, we're trying to force those things to be close together, we are at the same time trying to maximize the distance between the anchor point and some negative point, such as the description of a different thing, something that should be dissimilar because it doesn't describe what those percepts describe. And that approach works, not only in producing embeddings that can be visualized and show substantial overlap. And this is just a subset of 10 randomly selected objects from a very large set of objects. But I'll put some circles on the top figures to show what I mean about how we've got language on the left and vision on the right. And you can see that these things are being brought, quote unquote, together per the distance metric that we're using, but also in performance on a series of object selection tasks based on following instructions. If someone is, based on this learning, if someone describes a set of things they want the robot to do, how successful is that? And here our triplet loss methods, that's these orange and blue lines, substantially outperform the kind of naive, deep methods that we tested. So what I've been talking about so far, and most of the current work that's out there, is about grounding visual features plus symbols from text. And one of the things that makes symbolic language, or language broadly, such a tough nut is that these interactions are really very multimodal. They have to do with a lot of things about the state of the world beyond what can be sensed visually. And they have a lot to do with the variety of complex human inputs. So I'm going to talk briefly about what this means in practice if we're learning something from less simplified data, if we're trying to take noisy perceptual data into account. And specifically, I'm going to talk about that in the context of learning from speech. So far, when I say language, I mostly mean language that's been typed out or in a handful of cases has been transcribed from, something that's been spoken. And in practice, spoken language is a much more difficult problem. Spoken language tends to be disfluent, tends to be agrammatical, tends to be substantially more redundant than if you ask somebody to type a description. So even leaving aside the questions raised of sort of the back and forth that goes with dialogue, and I mean, I really shouldn't leave those questions aside, but in the interests of time. Spoken language is just a much harder problem. But when we talk about deploying robots in human spaces, speech really is the modality we're envisioning, right? We're not really talking about people carrying keyboards around all the time to interact with their technology. And automatic speech recognition isn't the answer. Not only does it fail often in very simple cases, for one thing, it's often cloud-based, which isn't great for robots in terms of things like lag in interactions, but it's also been widely shown to perform less well on different kinds of voices, including women's voices, people who aren't native speakers of Midwestern English, people outside a fairly narrow age range, and so on. So if we don't want to deploy agents who perpetuate existing inequities in technology, we need to be moving away from these very large-scale automated speech recognition systems. So this is just an example, and unfortunately, I don't think I have audio, but this is just an example of somebody asked to describe 6 very simple objects with a very literal transcription of what was said. These are green objects seeming like vegetables. This one is a cucumber or a dull oval thing. You know, I'll spare you. Whereas if you ask people to type in descriptions of the same thing, you get something like, here are some cubes. Here's a green cucumber. Very, very different animal. So you can see there's a lot going on here. But the key insight here is that speech is just another sensor input, right? It's not different from visual and perceptual inputs that are going into this joint model. I mean, it's different, but it can be handled similarly, at least in theory. So given that I've been describing relatively general learning approaches, it should be possible to learn groundings that directly connect speech to other perceptual data without using an intermediate textual representation at all. And of course, one of the immediate problems is that there aren't really any data sets designed for this kind of thing that include things like both speech and sensor data that includes depth and images. We don't have a lot of data sets out there that are that kind of multimodal. And ideally, we'd like that data set to also have the kind of textual data that people are used to working with in grounded language for comparison purposes and for sanity checking. So we've recently published about a data set called Gold, and this initial data set has about 4,000 spoken descriptions and 8,000 typed ones. In the next 2 weeks, we expect to about triple that. It also includes automated transcriptions from Google speech recognition, and we find that those are about 67% accurate. So not great, not terrible. And all of this data was collected using Mechanical Turk, which has its own set of concerns that we're working on addressing. So these sound files, these clips of people saying things like there is a white coffee mug, can be used as direct inputs to the learning system I described. So what we're doing now is we're directly featurizing speech, and we're combining those features with the other sensory features that are included to try to solve this grounding problem, to try to understand when people are talking what they're referring to, what objects and actions in the environment are going on. So this is not going through something that we would ever, apart from the language, that we would ever recognize as a symbolic representation at all. But of course, it's there, right? It's coming from the language, and language is a fundamentally symbolic, declarative, hierarchical space. So I did not expect just pulling out speech features and comparing them to the performance of something like Google transcriptions to do well up front. I expected that to be something that would take a significant amount of work. And I was really pleasantly surprised that the results that we obtained on learning directly from featurized speech immediately performed comparably to learning from automatic transcriptions. If you go from speech and trying to turn this into text out of the picture entirely, then you can get something that's comparable to state of the art. And we also found that the transcribed data did in fact perform less well for some user groups, as expected. Transcription has these known problems, but the learned model, the model where we're learning directly from featurized speech combined with information about the environment, performed equally well across groups. So this implies that learning from speech has the benefit of generally reducing biases towards specific subpopulations. Like the most notable of the results that we had in this case is we found that Google speech transcriptions worked substantially poorly on accented voices, non-native English-speaking voices, and our learning system didn't have that effect. It didn't learn less well on accented voices compared to other voices. So broadly speaking, grounded language, treating language as a set of symbols that you're working from is a complicated space requiring multiple tools and perspectives. The symbolic nature of language and representations of it and formal parses of it, and the symbolic nature of the cognition that takes advantage of it is combined under the covers with the sort of more neural approaches of humans if we're dealing with objects, picking them up, rotating them around in front of our sensors. And learning directly from those inputs and directly from percepts, including the percepts derived from the human interactions, is a good next step. Speech is a good exemplar of that, but only one exemplar. And since I know we are somewhat tight on time, I'd like to thank many, many people who were involved in this, and I'll go ahead and be finished. And I believe we move on to the next step at that stage. Thanks. Rod, I think you're muted again.
I switch my screen and the mute button doesn't toggle. Excuse me. 3 excellent talks. I think there's a lot of material to discuss, debate, characterize. So we're going into the panel discussion now, where we would like to focus on maybe some ideas that the audience has had that arose during one or more of the talks, clarification, nomenclature, anything you want, how to use declarative knowledge and how to produce symbols while using it is the subject. So are there any, I'm not sure how we're going to do this. Question, is the audience invited to ask questions on the fly, or are we doing it through chat, or are we doing it through raise your hand, or can I have some guidance on that?
You're the boss.
I'm the boss? Well, you know, it's challenging to do these things over Zoom. So because you lose the spontaneity and the kind of, you know, give and take. If you do it with orders in chat, then you jump around from subject to subject. So, you know, perhaps what we should do is monitor participants and allow people to raise their hand. Is that okay? So if you go to the participants panel, you'll see that there should be a raise your, anybody, oh, more, maybe it's in there. No, it's not.
We actually have a question in the chat box already.
In the chat, okay.
It's from Katerina. How will the object representation will change when you have multiple objects, more than 3 on top?
Can we hold on just a moment? So Katerina asks, how will object representations change when you have multiple objects greater than 3, for example? Okay, sorry.
Yes. So nothing actually changes. Let me explain. So you can have as many objects as you want on your table, and then you learn this object-centric generative model that goes from noun phrases to 3D feature maps. And then now the question is, if you give me another language phrase much longer, how do I, let's say, generate it? And how do I put the objects? And what if when you're sampling or you're adding your objects in this 3D canvas, right, in your imagination, you decide to put an object in a location where already there is an object from before? Well, precisely because you're in 3D, you can detect those non-intersections, this violation of spatial constraints, and then you sample again from your generative model because it's stochastic. And you sample, you have an upper bound of number of samples. And if you sample a lot and you cannot find the consistent configuration, because maybe the user told you, I don't know, the piece to the right of the phone and the phone is to the left of the, I don't know, air condition control, and the air condition control is to the left of the pen, and you cannot actually realize it because he said something that doesn't make sense, then you can go back and say, I don't think what you said makes sense. It is not realizable. And I think this is a great benefit, that because you generate in the 3D space, you can say, whatever you told me doesn't make sense. I actually cannot generate it. We have experiment about this also in the paper. I hope I answered the question. Yeah, thank you.
Okay, so I am told that if you go to the reactions button at the bottom of your screen, you can then click raise your hand. And if you'd like to ask questions that way, please do. They will become ordered. And so we'll lose a little track of the thread, but perhaps that's the best way to do it. You can also do it through chat. We'll try to monitor that as well. Any other questions from the audience?
I guess Alessandro has his hand.
Yes, hello. I have a question for Ben, actually. Nice to see you, Ben, by the way. I was thinking about when you presented the tree of maps, in that particular example, all the maps considered had 90 degrees angle intersections. And of course, this greatly simplifies the problem, and of course is not realistic in many cases. But more generally, I was thinking, even for us humans, at least for me, whenever we're put in an environment with non-90 degrees angle intersection, we get lost very quickly. So this seems to be a very reasonable cognitive simplification to only have 90 degrees angles that have something to do with the way we also function. On the other hand, of course, it's not, we need something more general. So I was wondering about your experience and your thought about this 90-degree angle assumption.
Well, thank you. Part of the topological representation is to be expressive enough so that it does not require the 90-degree angle assumption. So that if you, but you would be able to tell when you come into a decision point, for example, is there a continuation, a sort of single unique natural continuation in the current direction, or are there directions from one side or the other? So they wouldn't necessarily have to be metrically 90 degrees. And so if you have multiple directions, that's completely expressible. Now, on the other hand, when you actually look at experiments with humans, they do exactly what you said, which is that they tend to remember things that are a little off from 90 degrees as being exactly 90 degrees. And they use a variety of heuristics that assume that, for example, this direction can be factored and separated from this direction, which effectively says that those are 90 degrees. Now, I had been actually thinking of some examples about Katerina's example, because she has built into her system a three-dimensional Euclidean frame for this model of the object. But if I take an object that, like a pyramid or a tetrahedron, that is deliberately not 90 degrees, then it can be very difficult for people to reason about that. And you can give people puzzles that they can't solve in a very easy way. So I think you bring up an interesting fact which about human limitations, but they aren't necessarily limitations in the topological representation if you want to build a superhuman representation.
Thank you, Ben. I hope, Alessandro, your question has been answered. Erhan is asking a question which he calls naive. I don't think it's that naive. He asks, is declarative knowledge always linked to language? Or do some animals have some form of declarative knowledge without language? And I'd like to expand on that question a little bit. To what extent is language necessary for symbol formation or concept formation, and vice versa? To what extent or how does language maybe arise from symbols both ways? And I'd like all three panelists, if possible, to address that question and hopefully engage in some controversial discussion.
Thank you.
Who would like to go first?
Maybe Ben.
Yes, I mean, I guess I would say that a lot of the higher level spatial knowledge we can see in many animals just as well as in people. And so the assumption is that those animals don't have language. So I think declarative representations, which I mean, are likely to be available to animals as well as to people. And so I would not consider declarative representations to be necessarily linked to language. I would consider them to be essentially providing a version of logic, in the sense that you have descriptions, excuse me, you have descriptions of objects and relations among objects. And that's what a declarative representation has. And those may or may not be linguistic. Now, I don't think you can have language. You can't have very much language without having declarative representations. But I think the other way around is okay. Cynthia,
Do you agree, or do you want to counter his argument? Or
Oh no, I agree. And I would go a little further and say that I think that language is only one way of deriving a symbology from declarative knowledge. And we know it's an exceptionally powerful way, right? We know, for example, that that people think differently about problems when they've been given language that helps them describe components of those problems. We know that our understanding of sort of the declarative state of reality, the state of reality that can be represented declaratively, is managed differently when linguistic symbols are applied to it, when we're thinking of it in that symbol frame. But that doesn't mean that the two are equivalent, right? And I absolutely agree with what Ben said, that the declarative knowledge is not necessarily dependent on language. Whether language is dependent on that sort of declarative infrastructure, I would probably argue yes, but that's not the question that was asked.
Interesting.
Yeah, I also completely agree with Cynthia and Ben. I also heard exactly what Cynthia said, that when you have these language concepts, then you can do better spatial navigation when you have learned about left and right and so on. I think the way we see language for learning is that it's a shortcut. It's so cheap. Supervision is given there while learning the abstraction problem. How do you map the RGB, let's say, pixels to abstractions? It's hard, but if it's supervised by language, it becomes easier, right? It gives you a guidance of what features to focus on and what to forget about, let's say. So it's rather a shortcut as opposed to, oh yeah, do we need it for symbol generation?
One of the ways to get some leverage on this question is to think about what kinds of concepts children learn during their first year of life, before they have mastered language, and certainly before they can be learning very much of anything from linguistic explanations. And so children do learn to find their way around a house, for example, or the affordances that they can perform with a variety of toys. They can recognize equivalence classes among objects that have small differences but are functionally the same. So I think there's a variety of examples where there are interesting declarative connections between things that come pre-linguistically.
so would you say that our ability to use language helps us organize our world into useful concepts and reason about them?
I'd say we learn the meaning of words in language because we are already developing useful distinctions about how to distinguish between different situations in the world.
Yeah, I agree. And may I expand a little bit? So
yes.
What is the role of hierarchy? So typically language is at the top of that hierarchy or somewhere near the top. I would claim it's very close to the top. And there's this common important theory or observation within the language community about the basic level of discourse. When do you describe it as a tree and when do you describe it as a forest? and it's very adaptive, and it must reside on the basis of some other hierarchical organization of experience, right? So I think that's where Ben's kind of prior embodied, situated knowledge starts to emerge and form patterns that you can then attach these linguistic tokens to. So is it just another tool that can help solve computationally complex problems, or is it another way of stabilizing the history of observation is what I'd like, if anybody has any interesting ideas on that kind of a topic.
Well, so to respond to that, I'd come back to the point that people do appear to think differently about things once they have the linguistic constructs for describing them and interacting with them using the symbology of language, right? So I think it's a self-reinforcing question. There's not really a question of, do we use language to think about the state of the world that could be described in other declarative ways, or vice versa? Do we, does language purely for describing that? Language clearly helps us expand that understanding, and that expanded understanding in turn helps our language development, right? So these aren't things I think that can be decoupled.
And likewise, language is often vague and leaves the grounding to the listener. And so that's a very efficient way of kind of probing and sending a conversation in a certain direction and allowing each of the agents to kind of put that together in terms of their local context. So it seems like they go hand in hand, and that cognitively language is indispensable for kind of providing those, abstract high-level summaries of what you expect either current activity or future histories of expected activity, how they will take place.
So an interesting example, I'm agreeing with Cynthia. An interesting example would be, let's suppose that you and I independently categorize colors. So we might very well categorize the colors that we're looking at in significantly different ways. But once we start communicating linguistically with each other, then I might say, okay, here is a red thing. And you might say, oh, that's not red, that's orange. And I might say, no, I think that's red. And we would work it out some way or another. And basically, we would converge on pretty similarly co-referential terms. And similarly, I mean, chair versus stool versus sofa versus whatever. We might, without communication, we might have concepts whose boundaries are significantly different. But once we actually want to communicate linguistically with each other, the fact that we want the communication process to succeed is going to be a force on both of us to modify our concepts so that those boundaries are at least closer together. Now, Luke Steels, I don't know how many of you know Luke Steels, but he has did some very, very interesting work with a robot implementation of this.
I also want to mention something about the hierarchical representation. I really liked hearing this from Ben. He said that it's very flexible. It's not just one representation, and we jump abstractions based on the situation. So the way I understand that is, imagine you have your favorite toy and you've seen it falling from the table many times, and you know exactly how it falls, how many times it tumbles. And now a new object comes and you're going to throw it, right? A neural network would just take all the features, squeeze it out, and predict something nonsensical because it's a little bit out of the distribution, right? But you flexibly will abstract whatever you need to abstract, and you may jump in a higher level and say, oh yeah, sure, it's going to fall down. I think it's going to follow roughly this trajectory, right? So I think this hierarchy also has to do with familiar, non-familiar type of relationships. Yeah, I think that you said that this hierarchy allows to be robust, allows robustness to enter into the model. I think this is an important idea. Yeah.
So I think one interesting case that a student and I saw this, we used an implementation of Pong. And what we were doing is asking the system to take the pixel array and understand what the objects in it were. And so it would detect the static boundary, and it would detect the movable paddles and the movable puck. But then what we did was we added a great deal of noise. And this was sort of speckle salt and pepper noise. That is, each pixel would independently flip its parity with some probability. So then when the puck is moving along, the background is mostly dark, but with a lot of white speckles in it. The puck is mostly white, but with a lot of black speckles in it. But of course, a human visually looking at this can see very clearly which is the puck and which is the boundary. In spite of the fact that you basically never, ever see the identical same shape. That is, the noise is enough to make sure that you are never seeing the same configuration of bits. But the statistics help you define a boundary. And so it's at that abstracted level that the puck has an existence and it has a location. And so when you're looking at a pixel array, there is no motion, there's only changes of pixels. When you're looking at a puck, there's motion, and it has a location and it has a velocity. So you've totally changed the ontology for describing that object. And humans' perceptual systems do this all the time, very easily, automatically. And you say, oh, the puck, it just moves. It looks the same all the time. Well, it doesn't look the same all the time. Its pixels change all the time.
Katerina, you have a question?
Hi, everyone. I hope you can hear me. Thank you. Yes, I think that's a very, very important part, concepts and new concepts. And this is related to the question I had in the chat previously. I think new concepts will depend on how much prior information do we have about a problem or whatever, and how much information can we infer. And that will lead perhaps to identify new concepts. So the question is, what is the best strategy to detect that a new concept has been seen, for example? Does that make sense?
Mm-hmm. Give an example where you learn that, where you learn a new concept.
For example, a new action. And
Yeah.
I think communication, when you say communication, I think that's very important. I mean, you learn from your parents or your teacher or someone is teaching you, but sometimes you discover new things and you start doing it until somebody gives you the concept, right?
Mm-hmm.
And as I said, I think that depends on the prior information that you have accumulated somehow.
So let me pitch in and suggest an example. Say the concept of inside something, right? This is a concept that we grow up with, so it's important to us. But if we take it purely abstractly, this may not something that is easily discoverable by an unbiased system, say a neural network or something. So I think this is a very interesting question. How do we learn such abstract concepts, or for example, relational concepts?
And also how to place it into this hierarchical representation that we've been discussing, because you need to know which level you need to learn this concept, right?
Yeah, there has to be some cognitive overlap, I think, between speaker and listener. And Masataro mentioned something in the chat that's related, I think, that symbols grounded by a system do not have to correspond to human symbols. But there must be some common experience that allows them to be grounded in a way that is compatible for them to be understood. So, you know, one example I can come up with, maybe this is related, I hope it is the relationship between human beings and their working animals, like horses and dogs and things like that. They clearly cannot generate verbal tokens the same way. And in fact, we have no real clue why the dog is barking right now. We can infer it from our past experience. But their ability to interact with each other very effectively is remarkable. And so I think, you know, is a robot another species, or is it a human? And should there be a layer between human language and robot experience in which there's a translator that puts it in kind of the native tongue of the robot, and vice versa?
Now you're pushing a hot button here.
Well, that's my job.
I would say a robot is not a thing. A robot is a medium. It's a medium for expressing an idea about how a perceiver and actor should interact with its world. And so just like a piece of paper is not a communication, it's what you write on the piece of paper that is a communication. And then you can evaluate that. Saying what is native to the robot doesn't make any sense at all. It's like saying, what is the sentence on the paper when the paper is blank?
Well, for somebody who thinks that, I'll speak only for myself, for somebody who believes that I am in fact a somewhat sophisticated robot, I would like to be classified as at least a thing.
Well, you have become a thing because you've learned an awful lot of knowledge. And so when we talk about what you are, we can't say that. We look at what you do and we say that tells us about Rod Grupin. We don't say that tells us about people. So at any
do
rate,
we not? I mean, do we not, when we have interactions with, say, Rod, are we not generalizing that to things that we know about people of whom Rod is our current exemplar?
some gets dangerous.
Perhaps, but I mean, that is where the whole concept of people and what a people is comes from, right? Is from the exemplars that we have.
People is a much richer concept than robot.
Currently, yes, but I mean, but I'm just making an isomorphic argument that when you say we interact with Rod and we learn about Rod, but we don't learn about people, that I'm not sure then where our sort of meta structure of people comes from if it's not from generalizations from individuals.
Yeah. Okay. But we don't have that. We don't have that quality of knowledge about robots generally. And I think there are fewer generalizations that are true across robots than are true across people.
Robots are more heterogeneous and less frequently occurring. So I think that's inevitably true at the moment. Yeah.
And the upper bound on complexity is much lower for robots than it is for people.
Again, currently true.
Currently true. Eventually, I mean, I'm not saying we can't have Lieutenant Commander data.
But going back to the question of concept generation, right? So one example that we were thinking when we're in Google is imagine that you go to take the Google bus and you look sad and the bus driver asks, what's wrong today? And you say, my network didn't train. The whole day was wasted. What will the driver understand? He doesn't have a shared experience of training a network and the frustration you get from programming, right? So the only thing he'll understand is something that makes people sad. If the other guy comes and says the same, it's like, oh yes, like this previous guy that came here. So I think this shared experience is very important for concept understanding. And what a virus means to me and to a doctor is also very different, right? Because he knows more.
So this area is rich, as you can tell, and we could go off in many different directions with this conversation. I think we're endeavoring now to build a system. I would like to throw out this thought and see what people think. Unless I see Masataro has responded again, let me see. A set of symbols that is required by an agent, either human, robot, or dog, is limited by the set of communication messages required by the system. An agent that does not have to communicate with other agents does not need symbols. That's a pretty, I think that's a pretty provocative statement. He's sticking his neck out there. Anybody have any comments regarding that? I can suggest that symbols are distinctively important because of the fact that they summarize and help us to defeat complexity. They give us sketches of solutions before we have to think about implementing them as instances of behavior. Masataro, if you'd like to, you want to chime in?
Yeah, thank you. Yes, I just no, thank you, but no, nothing to actually talk about. But yeah.
I actually have a suggestion though, which is, I think people talk to themselves, and in part, people tell themselves stories about what's happening. So it is certainly true that communicating with other people is very important. But if you look at what consciousness is and what people's consciousness of their experience is, it's kind of a fairly low-level story that you tell yourself about what's going on 300 to 500 milliseconds after the fact. And so psychologists can actually sneak in and interrupt that process and catch you at being aware of things only 300 to 500 milliseconds late. So I think when you are experiencing things, there are processes. Now, I don't think that they're talking in English, but they are using some kind of description, and I suspect that it's a declarative description to say, this is what's happening. I'm perceiving certain things. I'm performing certain actions. I'm observing certain results. And one of the types of experiments that can reveal some of that are these experiments called change blindness, where they provide an experience where you look at a situation. For example, you're talking to someone on the street, and they've asked you to stop. They want you to answer some questions, and they're writing on a clipboard. And while you're in the middle of the conversation, some workmen walk right between the two of you with this very large piece of plywood. And then they go off the other side and the person is still there writing, except it's a different person. And about 50% of the time, people don't even notice. So what you're doing when you're experiencing something is you're telling yourself a story that says, oh, I'm talking to a person in a lab coat with a clipboard and answering questions. And then I get interrupted, and now I'm talking to a person in a lab coat with answering questions. And I don't even ask whether it's the same person. Of course, it's the same person.
Yeah, top-down guidance. So we're about done with our question and answer period for this first session. I did want to make one comment that we didn't get to that I think it would be a shame if we didn't get to it by the end of the day. And that is that what we're engaging in is a scientific question that is invokes hierarchy, right? So it's a systems question. It's you cannot build one piece of it without being well informed about how it must interact with all the other pieces. Architectures have been historically kind of shunned in the robotics community because of the fact that it's simple. You publish little publishable units, and the audience does not necessarily want to adopt your entire perspective on the problem in order to make a contribution to that area. They have their own ideas. And so one of the things that I think as a community we must do is, well, first of all, we need to come up with quantitative metrics and ways of measuring. Somebody mentioned, I think in one of the abstracts, that the idea of breadth versus depth is really what a cognitive system that requires symbols is about. So how do we build such a system? How do we test it? How do we quantify its performance? These are all kind of new ground scientifically, and as a scientific community, I think we should start maybe discussing that and trying to see whether or not there are some good acceptable metrics for measuring when we've made a contribution. I believe we should give the meeting back to the organizers now and get some instructions for how we should reconvene after a short break, I think, is happening next.
So right now the RSS sessions has just started, and it takes like 3 hours, and we'll continue 3 hours. So we'll have a 3-hour break actually, and we'll start at 13:00 Eastern Daylight Time.
Great, thank you.
Okay.
Thanks
I
very
want to
much.
thank all the speakers for great speech. All of them are very inspiring. I took some notes to think about it later on, and might actually ask some more technical questions later on. So thanks. Shichi, would you like to add anything?
No, just many thanks, and we'll have it's not really a break, but we're going to the main conference, and then in 3 hours we're getting back to the afternoon session in Eastern time. So we will have again invited talks and panel sessions. So see you back in a few hours.
Thank you.
Thank you.
Our session starts in 10 minutes. Hello, Shichi. You're on mute, I guess.
Hi there.
Hello, Anthony. Welcome.
Thank you. Thank you.
Thank you for coming here today, and also thank you for attending our workshop as a speaker.
No problem.
Hi, Tony.
Hi there, Alpa. So when do you want me to share my slide? Now or only after you introduce me? Or after Matteo introduces me?
I guess it would be better after Matteo introduces you.
Fine. Okay. I've got it in presentation mode, so ready to go whenever.
Okay. Thanks.
Is Matteo here? Not yet.
Not yet, I guess.
Yeah, I can see your screen at the moment. That's all I can see.
So, Tony, do you have any suggestions or things we should highlight in the afternoon session? I mean, it's afternoon here in Eastern, so.
No, it's afternoon. It's afternoon here. It's 6 p.m. here in the UK. So, well, late afternoon.
Yeah. 5 hours difference, I think.
Yeah, 5 hours. Not too bad.
Yeah.
I don't think so. I managed to grab some of the talks earlier. Unfortunately, I heard the introduction and the start of Ben's talk, and then I had to bail out for a meeting which had been arranged for a long time. But I listened to the question and answer session on YouTube afterwards. So yeah, that looked like it worked well.
So I think the first one will have 4 20 minutes invited talks, then we will hold the question. I guess Matteo can give the details, and we will have a panel together. So if you have any suggestions, we can be adaptive and maybe adjust things a little bit.
Nothing off the top of my head. I mean, hopefully we'll get some questions from the audience. It's always more difficult to get questions in these virtual settings than in real life. But it seemed to, we got some questions in the first session, so hopefully we get some here as well. I'm just trying to remember exactly what we've got. Sheila is the last one, isn't it?
Yep.
I'm just trying to see what the sort of similarities are in the, it's, me then Nick, who I was in a project, the Strands project with a few
And then
years ago.
George
And then
Konidaris.
George, yes, I don't know George, but yeah, looks interesting. And then Sheila, who I know work quite well.
Have 5 minutes. So Albert, maybe could you maybe send a reminder to Matteo and Yuqian?
All right.
Oh, Matteo is here. Hi, Matteo. Looks like you are on mute. Are you saying anything?
So do I have?
Okay, I can hear you guys, I think. Anybody say something?
Hi, hello, Matt. Can you hear me?
Okay. Can you hear me? Yes, I had to press a few buttons, but I can now.
What I don't have, I've got 3 screens on the computer, and I've got one which has got, say, next, which is your slides. But I don't seem to have a window which allows me to go and present my, maybe once you stop presenting your slides, then I'll.
Yeah, I'll stop it right now. Yep. I think it stopped.
Oh yes, I think I can then be. I will be. I won't share it yet, but yes, I've now got my green share button, screen button, right. So I'm ready to go.
So this is all on YouTube, right?
Yes, this is also streaming live on YouTube right now.
Well, almost live. I think it's a few seconds late, isn't it?
Yes, there's like 30 seconds of delay, I guess.
Yeah, I watched the first session or some of the first session on the YouTube channel.
Was there any problem with YouTube, by the way? I couldn't watch it.
No, it seemed to work fine. It was,
Right.
it was very, very good. No problem.
So both Matteo and Yuqian are here. So you're going to lead this session, Matteo and Yuqian. So do you want Tony to start sharing, or will we keep like this for the next few minutes?
Let me do a brief introduction and then we can start.
Okay. Hi, Sheila. See you are here.
Hi, Sheila. You remind me.
Sheila.
So Matteo, let's before each invited talk, let's make sure people are comfortable with recording. I think Sheila gives this suggestion very good. Thanks. And also, yeah.
So why don't we do it now? I don't want to put people on the spot 1 second before the presentation. If they say no, what do we do?
Well, because not all of the invited speakers are online yet.
No,
So
but hopefully
there is. George is now.
Yeah, hopefully they will be in the next few minutes.
Right.
At least with those who are, let's try. Because otherwise, I guess we need to stop recording or the question is pointless. So it would be good to know. Hi, George.
Welcome, George.
Hey, how's it going?
Nick isn't
George.
online yet.
Good to see you. George, are you okay with being recorded?
Totally. Yep.
I'm sure Nick will be.
Tony, you are too?
Yeah. Nick's very hot on public dissemination.
True. And Nick is here. Hello.
Is he? Oh, yes.
I see him. Might be setting the audio and that stuff. Okay, so Nick, if you can't hear me.
Yeah, sorry, my speakers take a little while to wake up. Hey, Matteo.
Yeah, of course.
Welcome, Nick.
We're making sure that everybody's okay with being recorded. So is that fine with you? Yes.
Yep, absolutely. Then someone can slow down my talk and actually understand it. I think I've tried to cram too much in. Hey, Tony.
Hi, Nick. Good to see you.
Likewise.
Well, good to see you.
Yes.
Hey, Nick. Good to see you.
Oh, George. Hello. This is really exciting. I was in the earlier session. There's lots of friendly faces there too as well. Cool. How are you all coping with lockdown and things and children and whatnot?
All right. Managing.
Cool.
We start having a good crowd.
Hi, Ben.
Hi, how are you?
Well, thank you.
Very good.
Yeah, hi, Ben.
Hi. Hi, Sheila.
Nice to see you.
It's nice to see you too. So, Tony, I'm looking forward to hearing what you have to say about the about manipulation.
Excellent. You probably didn't know I did manipulation, did you?
No, I didn't. It's a good problem.
Well, this is a joint work with Matteo and a bunch of other people at Leeds.
Mm-hmm.
Well, of course, Matteo's no longer at Leeds now, but when we did this work, he was.
Very good. Very good. Did you know that I do manipulation?
No, actually.
Like as a human being, or with robots?
With robots.
Yeah, I guess I knew as a human being.
Yes. Right. And well, I'll send you a paper.
Great.
Should we start?
Yeah, I'm losing minutes of my talk.
Let's start actually. I'll start recording since everyone is agreed. The floor is yours, Matteo.
Okay, excellent. We have very good attendance, so we should use the momentum. So thanks everybody for being here, coming back after the long break. It is our pleasure to introduce, well, a bunch of people. I will start with my co-host, Yuchen Zhang, who is a PhD student at the University of Texas at Austin. And myself, I'm a lecturer at King's College London. I've been there for the grand total of 2 weeks. Before that, I was at the University of Leeds, next door from our first speaker, Tony Cohn. So Tony's a professor at Leeds, and he's well known for a bunch of stuff, probably, generally related to automated reasoning, especially spatial reasoning and qualitative reasoning. But in the recent, I don't know how many years, few years, he has drifted towards robotics more and more. And so his talk will be partly about qualitative and spatial reasoning and partly about robot manipulation. So I'm very excited to leave the stage to him. Before the presentation starts, I just want to say we will have questions at the end. And so if you want to leave questions in the chat, I will keep them and collect them for later. But you're also welcome to use your mic and ask questions at the end. Okay, take it away, Tony.
Okay, can you see my screen?
I only see black, but hopefully it's coming up.
Tell me when you can see it.
I can see it now.
Okay, great. So this talk is about human-like planning for reaching in cluttered environments. This is joint work with some colleagues at Leeds, including Matteo, as I mentioned, and some others who I'll mention in a couple of slides' time. So this work came out of a project funded by our National Funding Council, where they were interested in trying to encourage work on human-like computing. So this was specifically not to use neural nets or deep learning. It was to trying to, it didn't have to be about robotics, but it was about trying to get AI systems which were more human-like. And so a bunch of us at Leeds, including 4 of us in the School of Computing and 2 colleagues in psychology, decided to get together and put this proposal in to work on human-like planning for reaching in cluttered environments. And what you see today is one of the papers that came out of that work. Just waiting for it to move on. Okay, here we go. So reaching in cluttered environments, of course, as many of you well may know, is a challenging problem for robots, but actually is very easy for human beings. Even young children can do this from a fairly early age. It's a kind of common problem which we face, like when we're trying to get in your fridge. My fridge looks pretty much like this, very cluttered, far too much stuff in it, and I have to retrieve objects from maybe the back of the fridge. And so I need to develop a plan to try to figure out how to squeeze the gaps or move objects to the side or maybe take them out altogether in order to access the desired object. So we're not quite yet at the level of this sort of cluttered fridge, but we started off this preliminary study by looking at sort of tabletop environments where we have a target object and then a robot arm, and we want to reach the target object through a cluttered environment. And we allow ourselves, if there's not a direct path, then we might be able to either go directly or we might push objects away. So this non-prehensile manipulation. And so the question is which path, and if we're going to push, then which objects and where to. And of course, this is sort of partly motivated by experience that some people may have had in the Amazon Picking Challenge, which we aim to bring people together to work on problems like this, manipulation in cluttered environments. And of course, the actual problem then included various aspects such as computer vision, but which were not particularly addressing the computer vision problem in this work. But it still seemed to be the case that as a result of that challenge, whenever it was held a few years ago, it's still an open and hard problem. Particularly the motion planning problem when considering physics in cluttered environments with numerous objects. So it's an open problem, it's a hard problem when considering physics in cluttered environments. Existing robot planners tend to work by random sampling in configuration space. And this can get very high dimensional and computationally expensive as we get large numbers of objects. And this results then in long planning times. So we were trying to say, well, can we do better? And also, if you look at the plans produced by those standard sort of stochastic planners, they actually are not at all human-like. So you look at them, you think that's a crazy plan. It's nothing at all like the one I do. And that's not surprising precisely because those plans are a result of the robot planner sampling in some space and just finding the first one plan which happens to produce a trajectory which works. So we thought, well, can we actually learn these high-level manipulation planning skills from humans? And then can we transfer these skills to robot planners? And we wanted the plans to be human-like in the sense that the motion of the robot arm should be expected. It should be what we call legible in the sense that it shouldn't have unexpected contortions or trajectories. And ideally, it should also be explainable. And so this work I'm presenting today, as I mentioned, is in collaboration with a bunch of colleagues. Hassan, the first author of this paper, was the main computer science research fellow. Then we had another couple of people from psychology and computing, Wisdom Agbo, who did the low-level manipulation work. And then my colleagues, Mehmet Dogar, Matteo, He Wang, and then 2 colleagues from psychology. So here's the overall architecture of our high-level planning robot architecture. So at the top we have let's just change my pointer. At the top we have the learning part of this, And at the bottom, we have the test phase. So in the top part, when we're doing learning, what we did was we acquired a bunch of VR data. And the advantage of getting VR data was it meant we could acquire lots of it much more quickly without having to reset the tabletop each time. We could make sure that we could get multiple people doing exactly the same environment task. And we could very easily then record the motions of the human arm. So having got that data, we then segment those demonstrations in a way I'll describe in a moment. And then we build a bunch of decision classifiers for important aspects of choosing the path. And having got that, we can then produce a high-level plan, which then goes into the test phase. So I'll talk through the different components of this planning architecture. So first of all, let's look at VR data. So just waiting for the video to load here. So here on the left, you can see the setup. We have somebody wearing VR goggles, and they've got a controller. They've got some sensors mounting on their upper arm, elbow, and they've got the sensor in the hand, the thing gripped in the hand. And on the right, you can see the view through the VR goggles. And so we have this sort of setup here. You can see that in this acquired data, we actually kept the life fairly simple. It's a tabletop environment with some sides, so you can't go off the sides. We've got 3 objects in 2 rows, but it turns out we can actually generalize to scenarios which aren't as constrained as just 3 objects in 2 rows, and we'll see that later. And you can see there's an initial position and then a target object we're trying to reach. So the next thing is to talk about the demonstration segmentation. So you can see at the bottom of the figure here, we've got the start, which is where the robot arm starts. Then we've got a target. In all the training data, these were aligned, but in some of the test data I'll describe later, they weren't aligned. So the interesting things are the objects, which are in red. We have the gaps between the objects. We have segments which link gaps in the different rows. And then because we may want to move objects out of the way, we then have a qualitative spatial representation of the scenario, such that we categorize the different directions we might move an object to into these 8 different directions: front left, front right, left right, back left, back, and back right. And we'll learn classifiers for each of those. So here's an example training scene. Hopefully this video will work. Yes. So here's a demonstration of what one of the human trials is doing. It moves that middle object out of the way and then retrieve the target at the far end. Hopefully this is going to repeat. Yep. So it goes through gap G2 and then moves 06 to the left, I think to the back left, if I remember correctly, yes, and then is able to reach the target. So we get a high-level plan, which you see at the bottom left now, where we go through exactly that, through that gap and then move that object. So a high-level plan then is a sequence of key points in the action space connected by the segments, but it doesn't give us the metric information about the precise motion that the arm should take. And we solve that problem later after we produce a high-level plan. So the next thing is to talk about the decision classifiers. So the decision classifiers, we have a number of different decisions that we might need to make. We've broken up the scenario into these gaps and objects. So first of all, we would look for gaps. We identify the gaps, which, as I say in the test scenes, might be more than the 4 gaps in each row that we see in the training data. And there's a question, which are the best gaps? We choose a set of gaps, in fact, and then we later will select which precise one to go through. Maybe the gaps aren't big enough, so we then need to move an object. So the question is which object and in which direction to move it to. So that's the 3rd classifier we build. And then finally, we then need to figure out which segments. And remember, segment is basically links, gaps and objects in different rows. And as we saw on the previous slide, we're using qualitative spatial relations as features, not just for the moving of the directions, but also in terms of the feature vectors for the gaps and objects and segment classifiers. And what we do is we train binary classifiers for each gap, object, and segment to learn a probabilistic classification. And the point about training a binary classifier, well, actually, it's an 8-way classifier for the object direction. But we don't want to just assume that we have exactly 3 objects and we're going to choose which is the best of the 3 objects, because we want to learn for this simple scenario with the 3 objects in each row, and then have it be generalized to an arbitrary number of rows and an arbitrary number of objects in a row, and even hopefully scenarios which aren't even strictly row-based. So in terms of features, for the gap classifier, we have distances and orientations to the target start, the target and the start, and also the gap size. And these things, the gap size are relative, so we can say this gap is larger than that gap, for example, or it's larger than the target object. We have object classifiers, which will have the features there, things like distances and orientations to the target and start, the object size, the amount of free space around the object, horizontal overlap with the target and start. And then for the object direction classifier, we have the amount of free space in each of the 8 directions and the directions to the target and the start. And finally, the segment classifier, which then has the horizontal and vertical distances between the different segments, the horizontal overlap with the target and start, orientation with respect to the start and target vector. And the point about having those is that we want to avoid actions if it's moving between gaps which are considerably apart from each other, or having no or little overlap with the target, which might then be expected to result in collisions and awkward motions for the robot arm. Is there anything else I want to say? And obviously, intuitively, humans prefer gaps which are close to their hand and having an appropriate size, and leading to the target easily and not requiring acute motion. So that all this sort of motivated our choice of features in these different spaces for the different decision classifiers. So having then got our decision classifiers for objects, for gaps, for which object to move and in which direction and which segment, we then put all that into the human-like planning algorithm, which you can see abstracted here. So we first of all have the environment. We extract the key features from the environment. We find the gaps and the objects. We then find the best set of gaps, a sort of short list of gaps, a short list of objects. Then once we've done that, we can link up gaps and objects to provide segments which link these in different rows. We then move away from the high level to a low level when we start estimating the arm configuration and detecting expected collisions. That then produces a high level plan in terms of the key points in the trajectory space, which is then given to a low level planner. So it is basically this high level plan is generated hierarchical in 3 levels. What we want overall is a path, but a path that's composed of multiple segments, and each segment is then a result of actions which involve going through a gap or moving an object to one side. The human arm is a model as a planar arm with 4 joints at the neck, shoulder, elbow, and hand. And the arm configuration is modeled by 2 angles, the neck, shoulder, and the upper arm links, and the upper arm forearm links. Okay, so that's an overview of the learning algorithm. So now let's move on to the test phase, which then is the bottom row of this figure here. So with first experiment we did then was on the same structures we had in all the training data. So a 2-row structure with 100 trials altogether. And you can see that our success rate here is higher than the stochastic optimizer, a more traditional state-of-the-art planner, and 94% opposed to 84%. The planning time was a lot faster. We used a Matuszek physics engine, and the stochastic trajectory optimizer we used was in fact one from one of my colleagues who was also an investigator on the project, Mehmet Dogar, and one of his students was Demagbo. So you can see it seems to be quite promising in terms of not only the success rate, but also in terms of the planning time. Well, of course, I said at the beginning that we wanted to produce plans which were human-like, which were similar to humans. So we took the training data set and then we trained on just part of that training data set, 80%, and then we did a cross-validation on the remaining 20% 5 times. And then we compared the overall accuracy, the overall similarity of the robot-generated plans to those of the humans. Now, of course, there could be multiple human plans, and indeed we did have some of the trials, training data, we did have multiple humans doing the same task, and they didn't always produce an identical plan. So we would never expect to get 100% accuracy here in terms of matching the human plan. But you can see that actually we're getting pretty close overall accuracy here in terms of selecting the gaps, 95% correlation, 85% for the objects chosen to move, 70% overall for the overall plan. And then those bottom two rows are just basically indicator functions, which is 1 when its argument is true and 0 otherwise. So again, that gives us a correlation between the metric, the robot plan, and the human and ape human plan. So here you can see a qualitative demonstration of the similarity. On the left, we have the robot generated plan, the human-like plan, and on the right, we have an actual human plan for exactly the same problem. And if we see that basically they both go through the same gap up in the bottom row, and then the human-like planner, the robot planner, then moves that middle arm object then to the top left, whilst the human plan, it moves the, sorry, they both move the bottom right object to the right, but then they move that middle object in different directions, but it's still choosing the same object. So it is still pretty similar in terms of the overall motion. I see time is moving on, although we started slightly late. So let me just move on. This is planning times then for 100 randomly sampled scenes where the start and end positions are no longer aligned, and we don't have quite such nice row configurations, and with different numbers of objects, 5, 7, and 9. And you can see the initial planning time before we do the optimization is pretty much constant, though it does increase a bit as we have more objects and we start doing the optimization. But it still compares fairly favorably even when we have the more objects with the stochastic optimizer. Let's just show a few videos just showing it on operation on a real robot on a real table with real objects. Here you can see the high-level planner has actually figured out there's a big gap off to the right, which it can go through and retrieve the object, target object, without disturbing any of the objects that might be in the way. But what's the stochastic planner is trying laboriously to try to take a path going through these. And as you can see, it's much slower. Let's move on to the next one with 9 objects. We'll just wait for the video to load. Here we go. So this is a little bit more complicated, but again, we'll see the robot planner going off through to the right, that gap in the right. The stochastic operator hasn't noticed that. It's just trying to force a path through the middle here. And the robot planner has now already got the target operator, whilst the stochastic optimizer hasn't. And finally, one with 11 objects. Again, just waiting for the video to load. I never know why this is quite so slow. So this is clearly much more complicated. There aren't any gaps we can go through, so we're going to have to do some object moving here. And it's isolated a bit of a gap there, and it's now going to move that object off to the right, and it can fairly quickly then find a path through to the target object, whereas the stochastic optimizer is again behind in its how quickly it can get there. Okay, so I'll cut that video short and move on to conclusions. So we demonstrated we can learn from humans interacting in VR. We have this qualitative representation of the task space and the action space. There's some metric information there as well, but it's also quite a lot of qualitative representation. We produce this high-level planning algorithm, which then enables us to then quickly guide a low-level trajectory optimizer. It seems to be quite scalable as we move across increasing number of objects. It's not tied to the particular morphology of the robot arm that we used. It could be, because we're producing a high-level plan, it can be easily adapted to different robot morphologies. We continue to work on this, doing more work on non-row structured environments. We've trying different classifiers. All the existing classifiers support vector machines. I've also had a student project looking at using inductive logic programming. And the nice thing about that is we then get an explanation. We actually get a plan, which is a set of essentially prologue rules. And then we can actually investigate. We can ask the plan, well, why are you moving this? And it give us an answer. At the moment, it's open loop planning. We have the initial task, and then we produce a plan, and we blindly execute it. We're currently looking at then doing closed loop planning, where we maybe replan as the task goes on. And we're also doing some work now with LSTMs to use learned features rather than handcrafted. And so then viewing the whole planning problem as a sequence generation problem. And that's it. Thank you for listening. And thanks to our sponsors. And that's it. I look forward to any questions when we get to this question time later on in the evening.
Thank you very much, Tony. Perfectly on time. We started at 5 past and it's 25 now. Yuchan, do you want to take it from here?
Yeah.
I'm just trying to stop sharing my screen just a second.
No worries. Okay, now it's my great pleasure to introduce our next speaker, Nick Hawes. Nick Hawes is an associate professor in the Oxford Robotics Institute at the University of Oxford. He leads the GOES research group and does research problems in mission learning, planning and decision-making for autonomous systems, particularly goal-oriented, long-lived robots acting in uncertain environments. So basically has done a lot of important work on the long-term autonomy of robots. And in this invited talk, you will hear about some of his recent work planning under uncertainty while updating and learning models. So take it away.
Cool, thank you for the introduction. That saves me 2 slides, which is awesome. I'm just going to share my desktop and jump to my presentation. Is that all visible and healthy and stuff?
Yep.
Yes.
Yep. Cool. Excellent. Thank you very much. Cool. Yes. So this talk is going to be about some kind of new-ish or recent directions that my group are taking. It's a bit. I'm still formulating the ideas. We're still formulating. We're exploring different bits. So this might come across slightly half-baked, but or maybe I hope there's something useful and important there, and I'm quite keen to share it. So as you heard, my group works on sort of decision making and mission planning. So we're particularly inspired to make robots make very good choices over long periods of time. So we're interested in long-term autonomy and have done work deploying, in fact, with Tony in a previous project, deploying robots for months of long-term autonomy in everyday environments. And we're really interested in what it takes for a robot to be autonomous over these long periods of time and to do that in a goal-oriented fashion. So achieving some kind of mission specification, typically in some kind of formal logic, described in some kind of formal logic. So the kind of premises of my kind of pitch for you today is, I think, starts with stuff that's reasonably obvious and maybe gets slightly less obvious as we go. So this kind of long-term behavior requires some kind of planning, some kind of search, some kind of look ahead to compare alternative courses of action. So we need to do some planning to make sure we're making good decisions. Planning requires a model, right? If you want to explore possibilities, you need some kind of model of the task, the environment, the robot interactions, so you can explore those possibilities into the future. So we're very much a kind of model-based group. But when you're doing this long-term autonomy and long-term interactions, when you sit down and you write your robot software and you develop your solvers, you don't know the model in advance, right? There's no way you can fully specify a model that describes the whole world your robot's going to interact with at design time. And it's almost certainly impossible to come up with a model that complete anyway. So we cannot specify the model in advance or fully specify the model in advance before we set the robot off running. So this kind of leads to this sort of cycle. And we want long-term autonomous behavior. But because these models can only be partially specified in advance, and I'll give you some examples of sort of partial specifications as we go, we have to do some kind of online model acquisition. And because we're acquiring bits of our model online, so during a mission or during a robot deployment, we have to plan with an awareness of this. So the fact that our models are incomplete or partial or uncertain, we have to plan in that space. So the robot behavior should reflect the fact that the models are being acquired online. And that's why, I mean, the topic of this workshop is super exciting for me. It really feels like this, for me, this is one way of including learning and the results of learning into a kind of model-based system that runs on a robot. And that's really kind of where our long-term vision is. So a little bit of kind of revision in terms of types of uncertainty, because this might come back useful later. So often in robotics, we think about kind of internal or aleatoric uncertainty. So when the robot performs an action, there's some kind of stochastic outcome because of the inaccuracies in our action model or some kind of external dynamics, somebody's walking past. And we capture those stochastic outcomes using an MDP. Also, if our sensors are noisy, or actually often because we're doing some kind of belief or some kind of estimation process to fill in bits of our state, then we get uncertainty due to partial observability, and we fill those, we deal with that with a POM-DP. So this is one type of uncertainty. And I'm going to talk about MDPs. When I mean models, I typically mean an MDP. But in everything I say, you could insert partial observable before me saying MDP. It's just for tractability reasons, we mostly think about MDPs in the first instance. But there's this other class of uncertainty, so parametric or epistemic uncertainty. And the way I think about this is there is an MDP, or there is a model that describes the world, and I just don't know what it is yet. So for example, there may be a model where my grasp fails 20% of the time, and there's a model where my grasp fails 30% of the time. But I don't know which one of those models actually describes the world I'm in right now. So that gives us kind of epistemic uncertainty. Sometimes it's described as not knowing the initial conditions of the process you're working in. And for us, a kind of underspecified or partial specified model can be kind of easily or naturally thought of in this kind of framework. So we've got two types of uncertainty, and our robot actions should, or our robot behavior over the long term should reflect kind of sensible behavior given both these kinds of uncertainty. So that's the background. I'm going to give you a starting example with the work that Tony and I did back in the Strands project. This was work running 2013 to 2017. We deployed autonomous mobile service robots into a range of real environments, and these robots operated for long periods of time. And when we started off with only a kind of partial model, and the robots built bits of that model as they went on. So the model we started with was a graph. So if those of you that are here for Ben's talk earlier, we had a topological map. The nodes represented places where actions could be performed or choices could be made in terms of navigation, but this was manually constructed. But that was kind of the model we knew. That was the model we could fully specify. And a part of our state was the robot's location on this map. The bits we couldn't specify were the sort of transition dynamics in that map, or effectively the transition probabilities and the costs in the Markov decision process, which describes navigation on that map. So we had some kind of failure events, lots of failure events, and I could talk for a whole day about the different types of failures we had. But we also had uncertainty in the duration of actions. So we cared, particularly in service robot tasks, about getting to a location on time. But actually the duration of those actions was also uncertain. So these bits of the models we couldn't specify in advance, and we had to acquire those during the lifetime of the robot. So we took, as I said a few times now, a Markov decision process approach for planning, for mission planning in the missions that robot followed. In general, the states and actions in this approach were defined by the map and task. So we could take the topological map, we could take the particular things we wanted our robot to do, and we could generate an MDP from that. We then generated the transition probabilities and the action costs, so typically a duration cost or time, by learning from data as the robot performed. So we logged a whole bunch of data as the robot acted, and then we were able to regress the probabilities and costs using various machine learning mechanisms to populate the MDP. So that gives us a kind of way of we can think about the world. So we had this loop running on the robot. This loop took about 20 minutes because that was about the scalability of our MDP solver. So we built an MDP model describing the task we thought we could do in about 20 minutes. We solved it. So the goals were typically specified using co-safe linear temporal logic, which was a nice additional layer to give us some kind of formal properties from this. Then we executed the policy and came back. As the robot was executing the policy, every action that was performed generated a little bit of data. And over the course of the day, we accumulated all of that data. And then when the robot went to sleep at night, we did some machine learning on the data that would allow us to forecast probabilities and costs for different actions at specific times of day the next day. So we were doing online model acquisition, but this wasn't really online in some sense. So typically when planning people talk about online, they mean the pink loop, whereas we were doing online within a kind of larger life of the robot. And this overall approach, whilst it got us going, had a few problems. So first problem, and the major problem, that's the one I want to kind of deal with most, is that what we were doing is we were coming up with point estimates for the costs and the probabilities. So those were like, the mean of some distribution or something. And that meant that our model was incorrect. Because our model was learned from data, there was some distribution. It might be a multimodal distribution. There's some variance in the knowledge of what we think those probabilities will be. But when we were collapse them down to a single point, that meant our model was effectively overconfident about particular bits of that of its model. So we were acquiring the model online, but we weren't really reflecting it when we were building that model. And also this whole learning process was kind of out of the loop. Like the robot, the mission planning, the solvers we used had no knowledge of the fact that these models were being learned from data and couldn't really influence the data gathering process. So this was a good start. But what I want to sort of tell you about in the rest of the talk is the approaches we took to address some of these problems. And that's kind of led us on a journey via quite a few different approaches. And I'm going to try and sort of bring some of those approaches together to kind of put them all in one place and hopefully generate some discussion around it. So to talk about how we address these, I'm going to switch to a different domain. And in fact, really every example I give will jump to a different domain, which makes it a bit confusing. I'm sorry about that. Let's now think about the problem of how we explore a hazardous environment. So we're going to assume we know a map, we have some kind of map of our environment, and that's going to be the model bit of the MDP that we know in advance. So it's going to be a topological map again. And this time, rather than being something that's mapped to the environment, it's going to be a fairly horrific grid discretization of the world. So on this plot here on the floor, that is a grid map where each node is a node in the graph. And the problem we're trying to solve here is to explore in this world where there's some a priori unknown feature. So that feature can be represented by this plot. So there's some value you can go to each location and sense. You just don't know what that location is. And what we're interested in is exploring under hazards. So we assume that this feature represents something that's dangerous to the robot. And to represent that, we put a bound on the upper level of that feature. And then the goal is to explore all of the safe states in the MDP or the safe locations in the map without violating that bound. The key thing here is just to reflect, we've got this partially specified problem. So we've got the map that we know the model of already, but we've got this value of a feature which we don't know, and we can only acquire that by acting and moving in the environment. So the question is, how can we act sort of sensibly, rationally, not necessarily optimally, but smartly in this kind of environment to solve this exploration task? And this leads us to our first way of kind of putting more of that epistemic uncertainty into our planning process. So we build what we call an MDP with unknown feature values. It starts where our state is a mixture of the known state, so SK is a known state, and SE is some kind of estimated state. And what we're going to do, and this problem is set up to work this way, so this is based on prior work by Taketa et al. From a 2016 Neurips paper. We model the estimated bit of the world by using a Gaussian process. So this works well when you drive to a location, you get a noisy observation that you can feed into your Gaussian process. So we're going to model the known bits of the world by our kind of model that we've got, a robot location. We're going to estimate the rest of our state or the rest of our model using a Gaussian process. So we build an MDP using this approach. So we have a transition system or transition model that describes the transitions in the known bits of the world. And then what we do is we use the GP posterior to build the transition dynamics and the state features for those estimated features. So the way to think about this is each kind of interval in our GP posterior represents the probability of getting a particular observation given our current knowledge of the rest of the world. So this kind of reflects our uncertainty over the model, and it allows us to plan given what we expect to observe in the future. So it's modeling our uncertainty over the observations we'll receive in the future. So that's the way that we've been thinking about putting in epistemic uncertainty in this case. And the system works reasonably well. It can plan for safe actions. And that's because when you go to a location, your observation in the GP kind of spreads. So what's happening here, the GP is spreading what you know about the feature value where you observe it to some local regions around that. And that means that you can safely move away from your location without worrying about violating the state. So the fact that you can observe at one location allows you, through that Gaussian process, to kind of spread your knowledge to a local area around where you're stood. And I mean, the kind of results of the paper are not super relevant in this talk. I'm trying to give you the big picture view, but this approach, the formalization we took, allowed us to outperform the existing work on this. And here, outperformance means faster exploration, safer robots, and lower variance in the results of the exploration in the end. So our graph now looks like this, or our plot now looks like this. We've got rid of that blue bit because we built the GP and the GP updates into this loop. So now we build our MDP using the Gaussian process posterior. We build our MDP, we solve it, again, using value iteration and co-safe LTL to achieve a goal. We execute the policy, and after we execute the policy, we take our observation data and update the GP. There are some problems with this, or some things that aren't fully satisfying. So the GP posterior, we discretize, so we're still making some approximations there. And in this planning problem, the thing we didn't know in the model, the thing we were acquiring online, was really just a constraint. It didn't necessarily affect the dynamics of the problem beyond that kind of that dangerous constraint. And there was a few kind of heuristic things in here about when we should update the GP. So in effect, if we got a very unexpected or very unlikely observation, that told us our GP wasn't doing a very good job, and then we would stop execution, update our GP and replan. So there was some heuristic things in there that I think we could do better. But the key thing here is getting rid of that blue bit and having a kind of more formal knowledge, more formal notion, and more formal way of inserting the fact that we are learning and that there is uncertainty over the model we're acquiring online. So we like this approach. We wanted to take it and kind of push it a bit further. So then we moved to a mission planning problem. So again, the problem of moving a vehicle around in some space. And this time we found one of my favorite challenging domains, which is a kind of unknown, partially unknown time varying domain. So in this case, we've got an underwater vehicle that's trying to move through a space. Its transition dynamics, the duration it takes to get from A to B, and where it ends up, so which state ends up in, is affected by the currents. And the currents change with time. And the only way we can know about the currents is, well, there's two ways. We have a prior, which again, we can model with a GP, but then we have to observe the currents as we move to kind of refine our prior model to give us a stronger idea of what the currents are. So this is a super challenging planning domain. So what we did is we're performing missions here with a time bound. So you need to know the currents because you need to know how to exploit the currents to get to your locations on time. We had to deal with these unknown time varying dynamics. Again, this time we use a spatial temporal GP. So we're modeling kind of vectors in every cell that tells us something about the currents. And now we're moving to a continuous duration. So the things we don't know about in the world affect continuous dynamics of the vehicle. So particularly the duration of actions. And so we move to a semi-MDP formulation. So where the actions have some duration, and that duration is governed by a distribution. So moving into this continuous world gave us lots of headaches, but it was maybe as a precursor of what was to come. So no longer did we discretize everything and solve with value iteration. Now we moved to using Monte Carlo tree search, and that allowed us to kind of sort of plan using samples from our belief, which is fairly standard in the POMDP literature. And we're able to kind of sample a current or a set of currents from our GP and use that sampled set of currents to propagate an action and propagate time as the vehicle moves. So that allows us to build in a sample-based way a kind of reachable MDP. And that reachable MDP is kind of the likely MDP you would get given your belief over the model you've got right now. So effectively, it tells you, it kind of gives you the MDP you expect. It's almost like an expected MDP given the belief you have represented as your Gaussian process. So again, the kind of paper result is not super interesting, but it's worth just throwing them up. This approach works reasonably well. There aren't many benchmarks, so it works better than an SMDP that doesn't know anything about the dynamics. And we also have the green line here shows you what you can do if you have full knowledge of the dynamics. So we're able to kind of perform somewhere between those bounds, which is kind of what you'd expect. But it is a complex problem, and I encourage you to look at planning in this space if you're interested in planning. So this took us from this GP model, which was the safe exploration model, where we had a kind of model construction phase, and kind of collapse all of that corner into building and solving an MDP online as part of the sort of sampling process or action selection process during MCTS. So now everything's really is sitting within an action model and our GP, and that really allows us to only focus on the future models we expect to see given what we've observed. So this is kind of now fully online. So before we were solving policies and then executing the policies before we introduced the results of learning. Now we're really onto the online kind of mode of just performing one action before running MCTS again. So this has both pros and cons. You know, we don't have to search so far into the future, which is sensible because we don't know really what the future holds because our model is incomplete, but it prevents us from doing some optimizations. The big problem here, though, is that the amount of our model that we can acquire online is really limited by the GP length scale. So that tells you how far your knowledge spreads from your current location, or how much of the model you're acquiring by observing at one location. And that can be a real restriction, because when you look at some of these real kind of current models, they're governed by a physical process, and knowing about the transition dynamics or the currents at one location tells you something quite strong about the dynamics you might experience somewhere much more distant from where you are. So that led us to start thinking about how can we build our uncertainty, not over kind of local dynamics, but over the whole MDP. And to explain that in the time remaining, and again, I'm sorry I'm trying to cram so much in, we had to sort of take a change of approach. So you can think of what we were doing before as a sort of single MDP approach, where we had the aleatoric uncertainty in the transition dynamics and the epistemic uncertainty in the kind of GP that's allowing you to compute future possible worlds that you might encounter. But the way to kind of switch that up and think about like larger model uncertainty is to do what, I mean, I like to think of it as a mixture of MDPs, so aligned with a mixture of Gaussians. Think about a mixture of MDPs where there's a bunch of possible MDPs. So reflecting back to what I said at the beginning, there's some true MDP, but you don't know what it is. So you have to plan given your expectation that you could meet any of these MDPs. And you could think about it purely in set terms, or you could have a prior distribution over the MDPs that you expect to encounter. So how do you plan in this space? Well, point one, planning in this space is hard. There's kind of two models that you can use, or that we've used at least. So the first model, if you want to be just robust against bad things happening, you can use an uncertain MDP, and that ignores the distribution. And I think the kind of master model of it all is a Bayes adaptive MDP. So the Bayes adaptive MDP uses your knowledge and maintains as you plan and execute a belief over which MDP you're in. So that's really where we're headed with a lot of this work, I think. So a quick idea on uncertain MDPs. So the way uncertain MDPs work, you have a set of possible MDPs, and then you optimize for some worst case metric. So typically you think about this as a stochastic game of the agent against the environment, and the environment gets to choose all the bad outcomes from your action, and your policy has to be able to be kind of minimize bad outcomes given that behavior of the opposition. So you set it up with kind of a sample of MDPs. I'm just going to really just go through this. We worked on a minimax regret approach, which is less conservative than really modeling the absolute bad outcomes. And I just want to give you an example of what some of these worlds look like. If you want to look at more detail, please just look at the paper. So your kind of set of MDPs might look like this, where you've got different costs and different obstacles, and you have intervals or regions. So sometimes these are called or compared to interval MDPs. And then you have a kind of an actual MDP and instantiation, which looks like this thing on the right. And then you can plan to minimize maximum regret across all your models, and you get some results. And the kind of key thing to take away from this paper is that we did something that scales reasonably well to quite complex models. And maybe that's enough for today. We also tackled the glider domain here again, where your set of MDPs represents a set of possible forecasts you might encounter for a particular time of day. And that's really nice because we know that forecasts vary like that, but are quite inaccurate in terms of what exact time you're there, or you might be inaccurate in time of what time the vehicle gets there. And so we can think about kind of uncertain MDPs as giving you good performance across the range of environments you might expect. So just to wrap up, the other way to think about the world is with this Bayesian adaptive MDP. I don't have time to talk about that. The nice thing here, though, is that your policies use the state transitions in the MDP to try and infer which MDP you're in, a bit like a POMDP taking information gathering actions. And our future work is really kind of just pushing in these directions. So we're looking at risk-aware planning in Bayes adaptive MDPs. We're trying to kind of reframe our MDP plus GP approach in this Bayesian adaptive way. And we're also looking, I think, most excitingly in terms of applications at kind of shared autonomy or human-robot interaction tasks, where the unknown bit of your model is the performance of some human collaborator. Okay, so final seconds of wrapping up. We want long-term autonomous behavior. Models can't be specified in advance, so you have to learn them online. But if you want to plan in this space, you have to plan around the idea of online model acquisition. And I think there's a huge space of interesting ways of including machine learning, neurosymbolic stuff, and these declarative structured representations for planning. And I think that's what you're going to need to make your robots do smart things over long periods of time. And just to wrap up, I want to thank the amazing people in my group who did a lot of the real work here, the people highlighted, the people that directly contributed to this, and to also thank the sponsors for my group's work. Okay, thank you very much, and sorry for going so fast.
Thank you. No, you've also been quite precisely on time, so thanks. As we know, so questions at the end. I've seen a few people join, so I'll just refresh that we are having a session at the end to discuss with all the speakers, but you can drop questions in the chat and I will collect them for later. All right, now our next speaker is George Konidaris, a professor at Brown University, who I had the pleasure to meet a ridiculous number of years ago during our PhD and made my stay at UMass Amherst both more fun and more interesting. You'll see that his work is incredibly relevant to this workshop because he was independently invited by both groups of organizers. This was 2 workshops before and then merged into one. And he's gonna talk about one of the topics that I love the most out of his work, which is how to learn representations, a hierarchy of representation through skills. So the floor is yours.
Great, thank you so much. Can you see my slides if I do that?
Yes.
Thank you, Matteo. Yes. Okay. What Matteo didn't mention is that when he came to Amherst, he also made Amherst much more interesting. It wasn't. It was definitely a two-way thing. Just to make sure that the slides are moving, is that right? You're on the second. I'm on the second slide now. Cool.
Yes.
Okay. Great. Great. Thank you all very much for the invitation. I love this community. This is where I get all my ideas and where I have the most fun. Actually, one of the things I wanted to say up front is that a lot of the ideas here and actually for my whole career have been drawn from many of the people in this community. Like I think I saw Ben here and Rod Group, and so it's good to be home and among friends. So let's talk about why we want to learn these abstract representations of the world. And I'd like to kind of pitch the special reason why I think we should be able to, which is that we should all be trying to solve the AI problem, right? Nobody got into AI and robotics to build appliances. We got into AI and robotics to, build C3PO or something like that. And so it's a sort of characteristic of AI. I think it has 2 key characteristics. One is that it only really makes sense if you're talking about a robot, because you're a robot and I'm a robot and every other natural agent in the world is a robot, not a computer. And the second one is that, the right way to think about intelligence is it's not the ability to do anything better than the best human in the world. Okay, because N-1 humans can't do anything as well as the best human in the world, and they're still intelligent. It's about the ability to do almost everything reasonably well. And that's particularly challenging when you're trying to build an intelligent robot as opposed to sort of a general AI system. Because when you're trying to build a single AI system to solve a single task, it's completely reasonable to take as input to that AI system or as a sort of given to the AI system, the description of the task. Right, what are its inputs and outputs? So if we're thinking about an MDP, what is the state and action space? So if you want to play Go, it's totally reasonable to assume that you're already operating inside Go space, which is to say that your actions are legal Go moves and your states are Go positions. And if you're diagnosing, if you're looking at pneumonia detection in scans of people's lungs, it's totally reasonable to assume that you're living in lung scan space. Your inputs are images of a particular size that are oriented around lungs, and your outputs are like pneumonia or no pneumonia. It's all of those domains sort of assume that that's kind of pre-built in and just comes, it just, the world is created like that. But that's completely not the case if we're talking about an intelligent robot, right? You and I have to solve every problem that we ever encounter through our eyes, which are basically pixels, and that's our sort of input. And then our outputs are joints, which are basically motors. Right? We don't get to naturally be given the right state space in which to think about this problem. We have to solve every problem in the hardest possible state space, which is this like wildly, overblown state and action space, which is of course what you have to have if you're a generally intelligent agent, because you have to be capable of solving all the problems with that complicated state space. Okay. So when we think about how to model this, we've introduced the term, my lab has introduced the term, the ego process. You and I, roboticists, so we just call this, the robot control loop, but in AI, we have to give it a name. So it's the ego process. And the idea is that you can take actions in the world, and they're always the same actions. No matter what task you're solving, you can just move your motors. And no matter what task you're solving, you could receive inputs, and they're the same inputs, you just get pixels, right? Because you're the same agent for all the tasks that you may wish to have to solve. And what you're observing with and interacting with the world, not the task. And then what we're going to do is we're going to say that single agent can solve any task, and any task is described as a reward function over this thing. So it's going to be some reward function drawn from the reward function describing all the tasks you may wish to solve, and that's going to be given to the robot, and that's what it has to do. And that's really hard, right? It's extremely hard to think about solving something like a Go when you're interacting with the world, not a Go board. Right? We think in robotics it'll be interesting to learn to be able to pick something up and move it around, but if we are to be able to produce an account of general intelligence, we need to be able to explain how you go from one to the other. Okay, so this problem is often called the signal to sort of symbol problem, like how you go from being able to deal with the world as you experience it to a problem representation of the world that actually captures, just that specific problem in its natural form, that captures just that problem's complexity. Doesn't matter how complex your robot is, if what you're doing is you're learning to play tic-tac-toe, the problem is exactly as complex as tic-tac-toe and no more complex. Okay, but if we write these things down formally, then we can actually gain some insight. So what we want to be able to do is say, okay, well, the ego process plus reward function, that's a Markov decision process. And let's call that, the base Markov decision process that the robot may wish to interact with the world in. And now let's say, well, we want to build a Markov decision process that corresponds to the complexity of only this one specific task. And if we look at that thing, we see it's states, actions, rewards, transitions, and gamma. And the rewards and the transition function just describe the operations of states and actions. Those are not things that you actually have to build. You really only have to build states and actions. And these are two things that we've been studying in reinforcement learning and robotics for a long time. You can build abstract states through something called state abstraction. You can build abstract actions through something called action abstraction. So state abstraction is called the symbolic representation in robotics, or a state abstraction in reinforcement learning. And action abstraction is called a motor skill in robotics, or sometimes an option or in reinforcement learning. And if you build these two things, then it turns out that you're done. You've built an abstract representation of the world, okay, or of a specific task. Now, that's tricky. To build these two things in isolation and assume that they're just going to work together is never going to work, right? So you've got to build one and then build the other one to support the first one, so that together they build a well-formed task model. And it turns out that if you were to build such a thing and then you look at its properties, you find out that most of the existing AI decision-making processes just drop out as special cases of this, right? So for example, if your state space is discrete and your action space is discrete and your transition function is deterministic, you have a search problem. And if the transition function is adversarial, then you have an adversarial search problem. And if your state space is discrete and factored and your action space is discrete and factored and your transition function is deterministic, you have a classical planning problem. And if your transition function terminates after one step always, then you have a banded or a contextual banded in reinforcement learning. And if you have demonstration data for contextual banded, what you have is supervised learning. It's classification, right? Almost everything else just boils down to special cases of this. Okay. So in my lab, we've decided that this is the most interesting problem, right? This is what we really care about. How is it that we can build these abstract representations? Because if we have these, then we have an explanation of how we can build a generally intelligent agent that exploits all the technology we've had built in AI in the last 70 years by being able to index into these particular solvers for special cases. And we've chosen to go sort of action first. You have to either be state first or action first, and we've chosen to be action first because motor skills are real things. They actually are grounded in the environment and they're real, and state abstractions are things you get to hallucinate however you like. So we're going to be action first. And the idea then is, you're going to have the ego process, and then you'll learn like an action-specific, task-specific representation for something like chess, and you'll find that it's discrete state and action and adversarial transition functions. So you fill in, you drop in alpha beta pruning, or if you learn something for a robot that's navigating around in the world, you're going to learn something that looks like a map, and it's going to turn out to be discrete state and action and deterministic transitions, or maybe slightly stochastic transitions, so you can do classical search. And then maybe sometimes you learn an abstract representation, and you know what, the states are continuous, and there's nothing you can do about that. They're not really symbolic, and the actions are continuous. There's nothing you can do about that. They're not really symbolic. And so you do something like a policy search algorithm there. so it's key that we be able to understand the properties of under which circumstances these things happen and under which circumstances they make sense, and deeply understand the semantics of what this means. So how do we tackle this task, right? We have to build a theoretically principled framework that accounts for a couple of things. It has to, tell us what these abstract representations mean, how they're grounded. It has to account for when they're discrete and when they're continuous and when they're deterministic and when they're stochastic, and it has to enable the robot to learn them autonomously from scratch. So the approach that we took is something that we call constructivist. And so what that means is that we're going to formalize the computation question being asked of the representation. We're going to write down the math that it has to be able to compute. And then we're going to basically eyeball that math, and we're going to kind of poke around in it. And then we're going to construct a representation that provably by construction is capable of answering that question. So let me show you what that looked like for the sort of first thing we did. What's the sort of core question of classical planning? Well, let's start the simplest question that we could start with. Let's say you start in a state, and then you have a sequence of motor skills O1 to ON. And like the simplest question we can ask is, can we definitely execute those with probability 1? So now let's look at the math that you need to be able to require, or we looked at the math that you need to be able to do to answer that question. We sort of looked at which abstract entities arose in that math. And it turns out that there's sort of two key things that arise in that math. We need one set and one operator per skill. So the first set is called the precondition set. It's a set of states from which you can execute a skill. Like that's the set of states from which you can press that red button. And the second one is the image operator. That says that if you were in a set of states and you executed the skill successfully, what is the set of states you would land up in afterwards? And the proof that we came up with sort of looks like this. It says, imagine that you have a plan O1 and O2, very simple plan, and you start in set of states Z, and you ask the question, can I execute the first action O1? And the answer is you can execute that if and only if Z is a subset of the precondition of O1. Okay, so let's say that that's true, and then we execute O1, we would land up in the image of O1 from Z, and then we say, can you execute O2? And the answer is yes, you can execute O2 if the image of O1 from Z is inside the precondition of O2. And you can actually write such a proof, and if, that's an if and only if statement. You can write such an if and only if sequence of statements for any such plan in the environment. And the only things that occur in that if and only if statement are that little image operator on the left, the precondition on the right, and Z, the set of states that you could start with, right? So that's proves that that set, a collection of sets, is a necessary and sufficient vocabulary for reasoning about whether you can do this sort of classical planning, right? Now, a follow-on question is, and just to show you what we're now going to do is we're going to say, okay, what I'm going to do is I'm going to build an abstract representation where every state in the abstract representation is grounds to a set in the world. And then when I determine whether an action can be executed from an abstract state, I go and check if the grounding set is inside the initiation set of that action. And if so, then I can, and I compute using the image, the identity of the next abstract state that you'd end up in. And then once I've built this, it's kind of definitionally sound and complete. So I can throw away the grounding part and just plan with the abstract model. It's sort of provably the right thing. Now our question is, when is that thing finite, right? There's no reason at all to believe that you only need a finite number of such sets. And so here is a condition under which it's finite. What happens if you have a motor skill and the motor skill always pushes you strongly towards a single small set, and it doesn't matter where you started? So you can you can rewrite the image. It doesn't matter what Z you start out at, and you can just replace it with that place where you're always going to terminate, which we call the effect set. So that's called the strong sub-goal condition. It says there's a sub-goal set, and you always hit the sub-goal set. And there's a weaker version of this, which says you can substitute where you land up with the sub-goal with the effect set, which is the sort of union of all the images. You can substitute an individual image with the union of all the images, and it never changes whether you're in the precondition set or not of another skill. That's the weak sub-goal condition. Okay, so these are two conditions under which the resulting representation is finite, and therefore would be considered symbolic by most people. And here I should say, there are always going to be such conditions. It's completely unreasonable to believe that a problem can be made finite or symbolic. Just can't, right? So if you do this and often you can break motor skills down into sub-motor skills in which this is true, even if it's not true originally. So if you have these things, you can provably build a plan graph in which a node is a skill and an edge is a transition between two skills. And that plan graph is sound and complete. If you can find a path in that planning graph, there's a plan, and if you can't, there isn't a plan. Okay. A more interesting case in the robot community is what happens if you change some of the state variables in the world using a motor skill, but not all of them, then you don't actually get a graph. If you have something like the sub-goal condition, but you only change some of the state variables and leave the rest the same, you do some maths, and what you find you get is strips. Okay, so strips is the representation that you land up in when you have abstract sub-goal actions. Just to quickly talk about, that was the first thing we did. We upgraded this almost immediately so that you could do learning and you could do probabilistic planning. So the question then becomes, what's the probability with which you can execute a sequence of actions? And to get that, we just replaced the precondition set with a probabilistic classifier. So we replaced set with distribution, and we replaced the image set with an image distribution. That's a density estimation problem. And probabilistic classification, density estimation problem are well-studied machine learning questions. You can just drop in a machine or whatever machine learning thing you like to be able to learn them. So now we have a framework where you can execute some skills and get some data. The data looks like the state, the skill you executed, the next state, and the reward. And also for every state, which skills can you and can you not execute. For every action, what you do is you just keep breaking them down till they look like they're approximately abstract sub-goal. And then you do machine learning to learn the probabilistic classifying density estimator and a reward regressor for each skill. So we were able to apply this to a real robot. Here's a domain that I like to show off because it took so many years to build. So here is a robot in a room. You can see on the top left, there's a cupboard, and in the bottom right, there's a cooler. And I just hand built the motor skills, right? So remember, for now, we're assuming the motor skills are given completely. I have a whole nother talk on how to learn them, but I'm not going to do that now. I hand built motor skills that the robot could move between the cooler and the cupboard. And when it was at the cooler or the cupboard, if it had both hands free, it could open or close the cooler and the cupboard. Also, you can see there in the sort of top right, there's a switch next to the cupboard. And the robot had motor skills for switching the switch on or off when it was standing in front of the cupboard. But if you open the cupboard door blocks the switch. And then when the switch is on, there's a light on inside the cupboard that's so bright that you can't see inside the cupboard. Okay. Then finally, there's an object that could be inside the corner of the cupboard. It's a green bottle. You can see the robot in the top right holding it. And when the robot picks it up, it can pick it up when it's in front of it and it can see it. It sort of holds it up here in its arms. So now you and I could write down a small MDP describing that environment pretty quickly. It would have really not very many states in it. But that's not the interesting thing. The interesting thing is let's learn that from scratch, from sort of pixel data at the robot level, right? So this is the input to the robot system. It's got its X, Y, theta in a map. It's got a voxel grid of the whole room. I've just clipped the cooler, but that is the whole room. And it's got all of the robot's joints. And those are just dumped into a vector. So here's the robot executing motor skills. And you can see it kind of opening and closing the
sounds. White noise.
That's my annoying
4.5 stars by over 6,400 people.
That's my annoying Amazon Alexa. So you can see it opening and closing the cupboard door there, and then opening and closing the cooler, and it's turning the light on and off and picking up the object. Right. So it had to execute about 160 such motor skills in order to get enough data to learn this abstract representation. But after execute, and that took a couple of hours. So after executing all these motor skills, there you can see the light is on. It's very bright inside, and it washes out the landing tags for where to put things, so it can't do anything when the light's on. We get the representations that look like this. So on the top is the representation. It's a text file, right? So inarguably a symbolic representation. And on the bottom is the symbol groundings of the symbols learned by the process. So for the action navigate to cooler, the precondition is that symbol 1 is true, and that's a distribution over states. And so if you look at samples drawn from that distribution on the right, bottom right, you'll see that they mostly refer to the robot's pose in the map. So it's standing in front of where the cupboard is, and it's looking upwards. So it's standing in front of the cupboard, roughly speaking. And afterwards, symbol 1 will no longer be true, but symbol 0 will be true, and it will take about 37 seconds for that to happen. And if you look at symbol 0, you can see that it's now standing in front of the cooler. Okay, so that's a pretty obvious way to say if you want to navigate to the cooler, you need to be standing not in front of the cooler, and afterwards you'll be standing in front of the cooler. But in this case, the robot has invented that distinction because that's the necessary distinction for planning. It's learned it using a probabilistic density estimator in this case, and it's built a symbolic representation that's a text file that it can plan with, having thrown those density estimators away, right? The text file is provably sufficient, provably sound and complete. Here's a more interesting grounded learned representation for opening the cupboard. So symbol 1 has to be true. You can see in the top right that just means, again, it's standing in front of the cupboard. Symbol 3 has to be true, and that's a distribution over the robot's joints. And if you remember, when the robot had picked something up, it was holding it up here. So instead, the robot's arms are down here. That means it's not holding anything, so its arms are free. And symbol 4 is a distribution over the whole room's voxels, and I've just kind of shrunk down to the ones that show the cupboard. And you can see that, well, the switch could be on or off, and there's a bunch of stuff that could be happening with the cupboard, but it's closed. And then afterwards, it won't be closed anymore. Afterwards, it will be open. Okay, so that says if you want to open the cupboard, you have to be standing in front of it, not holding anything. It has to be closed. Afterwards, it will no longer be closed. It will be open. Okay. There's a whole bunch of similar sorts of things, which I don't have time to show you. But given these things, you can hand that representation to this robot, and in 4 milliseconds, it produces a plan because it's a really simple representation. Here's an example of the robot being asked to move the object from the cooler to the cupboard. So it opens the cooler to observe the object, but it doesn't pick it up straight away, because if it did, it wouldn't be able to open the cupboard. So it moves to the cupboard. And then it doesn't open the cupboard, because if it did, it wouldn't be able to turn the switch. So first it turns the switch so that the switch is off. Then it opens the cupboard. Then it goes back to get the object. Okay, so that's classical planning doing what classical planning classically does, which is unexpected, which is totally expected, right? That's not surprising or complex in this environment. What's interesting in this environment is that the classical planning representation was learned from robot sensory motor data. So here it's now it's going to take the object and move it to the cupboard. And then the slowness here is actually just the point cloud merging, because I'm not a computer vision guy, so I did that badly. And I also asked it to clean everything up, so it's going to close all the various cupboard doors. It's going to come back and do the cooler as well. So since that time, since the time we started working on this framework, we've actually instantiated in very many domains, right? We started out in 2014 as the first paper on this work. We were doing it in this kind of factored sort of, it was a 30-dimensional continuous problem, but it was a toy problem. And there was no learning in the initial case. And now we've done it on kind of more and more complex tasks over time. The HCAR 2016 paper involved a true hierarchy where there were multiple layers of this. The RS 2018 paper involved motor skills with real value parameters. The ICML 2020 and insubmission paper involved portable object and agent-centric representations that are lifted and can be reused. The RSS 2020 paper involved mapping language to learned representations. And so now we've done it on 1, 2, 3, 4, 5 real robots and a bunch of interesting domains. So it's really real. It's actually really happening. There's going to be source code available soon. If you need it, send me a shout and I can get it to you. But this is becoming a practical framework for learning this stuff. So the key takeaways that I wanted to sort of communicate to this audience, my happy, friendly home audience in some sense, is that I don't think we should think of learning abstract representations just as interesting and cool. I think that they're necessary for general AI. They're a very large fraction of the whole problem, and they're part of the key argument for how we think this is going to happen, how one agent is going to be able to solve any problem, is that it's going to learn an abstract representation of that problem. Sometimes it'll be symbolic and discrete and lifted in that nice way, and sometimes it won't, and our job is to understand exactly where the joints of these things are. Okay, so that means that we have to be principled and mathematical about this stuff. We can't just try stuff, we can't hypothesize things, and we can't assume symbolic representations of the world and then go build complex algorithms around them when they might not be the right ones, right? We really need to deeply understand what the properties of these things are. And then to pitch that my lab has produced such a framework, we think it's the right one, we're very excited about it. It's been used to learn I think I put up 9 different domains, abstract representations of those 9 domains, in many cases directly from pixels, some cases from sort of real valued features, but in many cases directly from raw sensory motor input. Lots of remaining work, in particular for this workshop. It's useful to mention this framework has not yet been made deep. And the reason for that is just pragmatic. It's the case that we use an SVN because we would like to be able to learn these symbolic representations from like 5 or 6 samples. It's very hard to do anything with a deep net from 5 or 6 samples, but you can put structured data in an SVN and get out a good density estimator from 5 or 6 samples. So there's nothing stopping us from using a probabilistic classifier that's a deep net. It's just that we're not really in the right sample regime for it yet. But you know, we'll get there. So and just keep this picture in mind because it's the big one and why we're all here. Okay, thank you very much. It was a great pleasure to be here, and thank you all again for the invitation.
Thanks a lot. Yu Chan, I think you're introducing our last speaker, and then we'll open the floor to questions.
Yeah, now it's my great pleasure to introduce our next speaker, Sheila McIlraith. She is a professor in the Department of Computer Science at the University of Toronto, a Canada CFAR AI chair, and a research lead at the Schwartz-Reisman Institute for Technology and Society. Broadly, her research is in the area of AI sequential decision-making, and she has done a lot of work on combining machine learning and knowledge representation and reasoning. And I personally have been a huge fan of her work, so I'm excited to hear what's happening.
Thank you very much for the very nice introduction, and it's a pleasure for me to be here today. Can everybody hear me and see my slides?
Yes.
Yeah, good, very good. So the topic that I'm discussing today is building human-taskable robots that learn. And excuse me. I wanted to start by acknowledging my senior PhD student, Rodrigo Toro Acarda. A lot of the work that I'm going to be talking about today is work that's been spearheaded by him and his thesis in collaboration with Torren Claassen and Rick Valanzano, some of it with other students, and also Alberto Camacho has contributed to some of the topics I'm just going to discuss today. But other students in my group have also worked on related topics, and some of them are listed here. So the problem that I wanted to talk about today was how do we advise, instruct, task, and impart knowledge more generally to our robots? And then how do we then use that knowledge in order for those robots to learn? So the paradigm that I want to look at today is reinforcement learning. Reinforcement learning is proving to be a very powerful technique for building robots that learn. And of course, the basic paradigm is that we have an agent, and the reinforcement learning agent, the robot in this case, knows a set of actions, but it doesn't know the transition model, and it doesn't know its reward function, and it performs actions in the world, and the environment gives it back what state that action resulted in, and any reward that it might get from the state that it's in. And that reward and state is fed back to the agent. And over time, in a trial and error paradigm, the agent acts in order to learn a policy, a mapping from states to actions or action distribution, in order to maximize the agent's expected cumulative reward. Unfortunately, in the context of actually thinking about tasking an RL agent, the only or the main paradigm we have for communicating what we want the reinforcement learning agent to do is the reward function, which is just a mapping from a state, in its simplest case, a state to a scalar, or a real number, or a mapping from state, action, state, triple to a real number. And so two really big challenges with reinforcement learning, and they're ones that we see in robotics, are reward specification. It's really hard to define reward functions for complex tasks. And some poor graduate student usually has to do it to write that complex reward function. And then the other problem that we often see is sample efficiency. Reinforcement learning agents might require billions of interactions hitting their head against the wall with the environment in order to learn a good policy. And that's often not practical in practice, particularly in robotics domains where we're working in a real environment rather than in a simulated environment. So just to ground this paradigm, I wanted you to sort of go through this thought process of thinking about buying a robot, and you bring the robot home, and the robot has a set of skills or a set of capabilities that it's able to execute. But regardless of that, similar to if you were to hire somebody to come and work in your at your home that has certain capabilities, you'd still want to be able to talk to them about what you wanted them to do, to ask them to do specific things, to refine or to compose the types of things that they're able to do other things in the environment. So there's definitely that motive to want to instruct or advise or impart knowledge to your robot. And some of the things that you might want to say might be things like, run the dishwasher when it's full or when dishes are needed for the next meal. Make sure the bath temperature is between 38 and 43 Celsius immediately before letting someone enter the bath. That may be good for children, or it might be good for a healthcare robot. Do not vacuum while someone in the house is sleeping. So these are interesting goals and preferences, and they have particular different properties. Sometimes they're conjunctive, they involve a bunch of different things, or different things that are temporally extended. They could be conditional. They're quite rich in terms of their form, and some of them are not just very hard, remember, to represent as some sort of a mapping from state to a real. So how do we communicate these types of goals and preferences to a reinforcement learning agent? Well, one way that we've adopted is to use a formal language called linear temporal logic, which is a compelling logic for expressing temporal properties of traces. So you have a set of properties, binary propositions, things that are either true or false. You know, it's someone's sleeping, someone's not sleeping, the temperature is 43, the temperature is not 43, together, and you combine those together into formulae that using logical connectives and or and not, you can use, and then you combine these together to talk about temporal patterns using temporal modalities such as next, weak next, until, eventually, always, release, and you can talk about very complex properties of traces, of evolutions of the world. And for some of you who may be familiar with linear temporal logic, we often use this language in formal verification to talk about desirable properties that we want to verify of a hardware or software system, or we might use them as specifications in order to do automated synthesis or controller synthesis or strategy synthesis. So this is a very compelling language that's been around for a long time, since 1977 at least, by Newelly, and it's a very rich and I think compelling language. The semantics, it's interpreted either over finite or infinite traces, and importantly, and we'll come back to this, it can be transformed into automata. So here's a very simple example of one formula. Do not vacuum while someone is sleeping. I might write that as box, not vacuuming and sleeping. Those are the propositions that are either true or false, and they can't co-occur. And they can't co-occur in any state, which is what the always indicates. So at every state in the evolution, it can't be the case that vacuuming and sleeping is going on at the same time. And of course, we can construct far richer formulae than this, and we can have nesting of these temporal modalities, always, eventually, next, and so on and so forth. It's a very nice language. So again, I may have convinced you, I hope, that linear temporal logic is a nice language for expressing some of these goals and preferences. And unlike natural language, it's unambiguously computer interpretable, which it has an advantage over natural language, of course, but still, how do we communicate this to our RL agent? We can do it using linear temporal logic, and we've done that in some of the work that we've done in the past. But what I wanted to talk about here is another way to do it, which involves Noam Chomsky. So many of you, I'm sure, know Noam Chomsky either as computer scientists because of his beautiful work on language, or perhaps because of his political writings. But here we're interested in his contributions in language. And in particular, Noam Chomsky has, of course, defined this Chomsky hierarchy that talks about increasingly expressive languages, all the way up to unrestricted type 0 languages, and that they can be captured by increasingly expressive automata. So for example, regular languages can be expressed as finite state automata, and if we need memory, we go to push down automata, and so on and so forth. So in the spirit of Chomsky hierarchy, my answer to the question, how do we communicate this to our RL agent, is that we're going to use automata. And in particular, we're going to use something that we refer to as a reward machine. So in the rest of this talk, I'm going to talk about reward machines. I'm going to talk about how we exploit reward machine structure for learning, some experiments, some work we've done on creating reward machines, and then a recap. So I'm going to do this or explain reward machines in terms of a very simple running example. What you see on the left is a grid world office environment. And the office has a bunch of symbols, which we're describing on the right. The agent is the purple triangle. We've got furniture scattered around that the robot's not meant to step on or bump into, which is the stars. We have 2 coffee machines, always important, a mailroom and an office, that little O, and a bunch of locations, A, B, C, and D. And the task that we're going to use as our task for our robot is a simple patrolling task, which is that the agent needs to go to A, then B, then C, then D, in that order. And if it does that, it's completed its task and it gets a reward of 1. So how would we build a reinforcement learning robot to learn how to do this? Well, some poor graduate student would probably write some nice piece of Python code like the thing on the left that represents the reward function. And of course, it gets a reward of 1 when the robot has sequenced through and visited A, B, C, and then D. And we can, but what I'd like to argue here is that instead of using that reward function and keeping track with a counter of what we've done and what we haven't done, that we'd like to represent this as an automaton. We're going to represent going from A to B to C to D and getting a reward of 1 in terms of an automata-like structure over a vocabulary. And our vocabulary here is whether or not we're at the coffee station, whether we're not at the mailroom, at the office, and so on. More generally, our vocabulary can comprise human interpretable events or properties realized via detectors over the environment state, or it can conceivably be learned. And this reliance on vocabulary is something that I'll talk about relaxing later on. So here's the definition of a reward machine. So a reward machine, as you'll learn, is basically a Mealy machine, but it's an automata structure that comprises a finite set of states, U0, U1 here, U0, U1, U2, U3, an initial state, U0, and a set of labeled transitions. And those transitions are labeled, so if we look at this label from U0 to U1, by a tuple. And the tuple comprises a logical condition or guard that must be satisfied in order to transition from U0 to U1. Here it's just whether that A has to be true, but it could be an arbitrary, here, propositional logic formula that has to be true. And then the second thing in that label is the reward function. Here, it's just, these are what we refer to as simple reward functions. So it's just a scalar and something drawn from the real, but it could in turn be another function. These can be arbitrarily rich reward machines. So very nice expressive structures. And a reward machine is simply a Mealy machine over the input alphabet sigma, which is 2 to the P, where P is those sets of propositions, that vocabulary, and the output is a set of Markovian reward functions. So what we've done is we've obliterated the need for that count or that memory, because at each particular state, the reward function is contextually Markovian. So if we look at these reward functions and actions really quickly and watch on the left, you can see the little agent. The little agent starts at U0 in our reward machine, and it goes to and moves, and it gets a reward of 0. And now it moves to A. And now that it's at A, it transitions, it tells from U0 to U1, but it still gets a reward of 0. And so on and so forth. The agent moves through the environment. When it gets to B, it transitions to U2, moves through. When it gets to C, it transitions to U3. And when it gets to D, it's actually completed its circuit. And as you'll see by the label, it gets a reward of 1. Note that if the agent had gone from A to D, then it would only have been in U1, and that move from the same position to D would have garnered a reward of 0. So the reward is definitely contextual based upon the state of the reward machine. So we can define all sorts of different types of interesting properties. We can define safety constraints, deliver coffee to the office while avoiding furniture. So we have that we can deliver, coffee has to be true, no furniture, we get a reward of 0. And then when we go to the office, we get a reward of 1, again, assuming not star, and we loop, assuming not star. But if we hit the star, which is the furniture, then we go to this sync state and we perpetually get a reward of 0. Similarly, if we've got different ways of doing things, deliver coffee and mail to the office, well, maybe we'll pick up coffee and then pick up mail and go to the office. or maybe we'll pick up mail and then the coffee and go to the office. And all of those things can be represented in the reward machine. So what I'd like to talk about now is, now that you've seen what a reward machine is, it's this autonomous structure that's going to represent these Markovian or temporally extended non-Markovian rewards, reward functions in a very nice structured way. What I'm going to do is talk to you about how we're going to learn using these rewards, these reward machines, using these function representations, and we're going to try to exploit structure in some way. And there's a very simple idea that we have that is the basis for our work, and it's the following. You know, someone always has to program the reward function, even when the environment is the real world, even when the agent, our robot, is operating in the environment, unlike us, where we're sort of wired for pleasure and pain. I eat ice cream and I'm happy, so I stub my toe and I immediately feel pain. The robot has to be programmed, and somebody always has to program it. So the simple but when we do reinforcement learning now, the reward function is always treated as a black box. So you do something and the black box tells you what reward you get, and you never get to actually inspect the function itself. So the simple idea is, why not give the agent access to the reward function? And since we have our reward machines in a structured form, why don't we exploit that reward function structure in order to learn? This is a very important idea. And it's similar to the idea of Bayes nets, where we've actually articulated the conditional independences. We've articulated the structure of our Bayesian network, our conditional probability tables, in order to exploit structure, or in terms of automated differentiation. There are all sorts of other things that we see that use this same sort of idea. So in the context of thinking about how we're going to exploit reward machine structure, we've developed 5 different algorithms, a baseline, which I'm going to talk about, 2 other algorithms that we used as baselines, and then 2 approaches that are our own. And I'll just talk about those really quickly. So the first baseline is just Q learning using the reward machine. And the important thing that we want to observe is that a reward machine may define a non-Markovian reward function. And again, I alluded to this before. If I seeing that little purple triangle, if it went to A, B, C, and D, and to where it is now, and then it went to D, it would get a reward of 1. But if it came from A directly to this position, it would get a reward of 0. So the idea is that we really need to know what state we're in within the reward machine, and the simple Q learning baseline is simply to include the reward machine state as part of the agent state representation, and then to use standard Q learning on the resulting MDP. We defined some other work with hierarchical reinforcement learning, one just straight hierarchical reinforcement learning as a comparison, and another where we actually exploit the reward machine structure for pruning, which is very nice. And I'll show you those results. But what I wanted to talk about was our approach called Q learning for reward machines. And here's the idea right here. So the idea is that we learn one policy, one Q value function per state in the reward machine. So one for use a Q value function Q0 for U0, for Q1 for U1, and so on. And then when we select actions, we're using the policy of the current reward machine state. So when we're in U0, we use Q0, and so on. Interesting, and then we go to when we're at U1, we use Q1, and so on. The important thing about our learning algorithm is that we use we reuse experiences to update all the Q value functions on every transition via off-policy reinforcement learning. And this is sort of a form of counterfactual reasoning. So here in our example, we have to learn Q0, Q1, Q2, Q3. And if we're at U0 in truth, in the real world, in our experience, then it makes sense to update Q0. But we can also counterfactually say, hey, you know, if I was at U3 and I performed this action, how would I update? What sort of reward would I get? And how would I update my Q function? And so we can learn these things simultaneously, and it really speeds up learning, again, by exploiting the structure of our reward machine. So that's a really nice feature of what we've done. We've decomposed and exploited this structure in our learning. So the last thing we've done is a form of reward shaping for reward machines. And very simply, all that we're doing is treating a reward machine like an MDP and performing value iteration over that reward machine. And so what we're doing is for those of you who don't know what reward shaping is, it's this notion that we can sort of take our reward as a cookie and sprinkle the cookie crumbs along all the different pathways in a principled way in order to that it preserves optimality of the relative to the original reward machine or to the original reward function. But it can give some tidbits that will help guide our search and encourage us along the right pathways. And so this is an example of a reward machine where the colored rewards indicate our reward shaping that has been used to augment the environment. So the nice thing about QRM and QRM with reward shaping is that QRM and QRM with reward shaping converge to optimal policies in the limit when they're used in a tabular domain. We have deep versions of this as well that of course lose those optimality guarantees, but this is a very nice property, and it's in contrast to hierarchical reinforcement learning, which is myopic and does not have that property. So very quickly to experiments. We did some nice experiments and I'm going to report on a subset of those experiments here. 2 domains with discrete actions and state spaces, an office domain and a sort of Minecraft craft domain, and then 1 domain with continuous state spaces. And we tested it on all 5 of those approaches, the 3 benchmarks, the Q learning, the 2 with hierarchical reinforcement learning, and then the QRM, our algorithm that exploits structure, and then the one that augments that with reward shaping. You'll note in the table at the bottom that everything uses decomposition except for the original Q learning algorithm, and that everything, on the other hand, everything preserves optimality in the discrete or tabular case, except for hierarchical reinforcement learning based approaches, which are myopic and don't preserve optimality guarantees. So here's our environment. On the left is the office world that you've seen before, and on the right is our results. On the y-axis, the vertical axis, we have normalized discounted reward. So everything 1 is perfect, and that's at the top. And on the x-axis is the number of training steps. And of course here on the right-hand side, we have 50,000 training steps. And what you'll see, we were tested on 4 tasks, 30 independent trials per task. Our system, QRM, very quickly converged to an optimal policy, and which was guaranteed, of course, by that theorem. Whereas Q learning, which is guaranteed to converge to the optimal policy, you'll see in the royal blue at the bottom, is still struggling. And the 2 hierarchical reinforcement learning techniques are somewhere in the middle. The one on top, the light blue one, is the one that's exploiting the reward machine structure to help the microcontroller pick which policy to operate. But again, because it's myopic, it actually in some of these scenarios cannot get to the optimal solution. In the Minecraft domain, we see similar results where our QRM algorithm is really, doing really well. And this speaks to the sample efficiency. See how quickly it's converging to an optimal solution relative to, at the bottom, Q learning, which is completely flatlining. And I will remind you that in the limit, Q learning is guaranteed in this situation to converge to an optimal policy. But here, after 10 to the 6th experiences, it's still at 0. So it's still not figuring out what it needs to do in order to garner any reward. So it just speaks to the effectiveness of this work. We also did work with function approximation with deep learning, where we replaced QRM with deep QRM. And of course, we lose the optimality guarantees, but we get some of the decomposition results. And here, again, we did great. I won't explain the experiments, but we're the red version with deep QRM, and double DQN is down here at the bottom, and the 2 deep hierarchical reinforcement learning techniques are in the middle. So just one last thing. If we want to create reward machines, there are a couple of different ways of doing it. You've seen how we might specify it, but we can also generate them and learn them. And just to shout out to some other work that I'm not going to talk about here in case you're interested in reading, reward machines can serve as a lingua franca and provide a normal form representation for the reward functions. So again, channeling Noam Chomsky, all these different regular languages and all sorts of different languages that some of you, especially those familiar with KR, may be familiar with, can be already, there are compilers that already exist. They can already be compiled into, or subsets of them can be dialects, can be compiled into deterministic finite state automata from which we can generate reward machines. And then we can use that as a lingua franca, not only to use our own algorithms, but any sort of other algorithms that people in the future may wish to do. So you may have another language. If you can compile it to a DFA, that you can use our algorithms that already exist. So it's a really nice way to exploit structure, and of course, with these great guarantees. The other thing we can do is use a symbolic planner to actually generate those instructions by having high-level abstract actions, using a symbolic planner to basically generate high-level instructions that we represent in a reward machine, and then we solve it the way that you've seen before. And then the final work, which I won't have time to discuss, is that we've actually done some very nice work that was published in Europe's 19 on learning reward machines using and in partially observable environments. And in this case, the reward machines are actually operating as memory. They're operating as external memory, and the types and these are really, really hard problems. We were solving problems that, at the time, the state of the art, A3C, PPO, ACER, and LSTMs could not solve. So these were really, really nice results. And they construct these reward machines that I think are actually, here's one that we constructed, quite interpretable. And again, great sample complexity relative to the state of the art. You can see ACER and PPO and various other systems down at the bottom, whereas our work, the learning reward machines work, the purple and the light blue up here are doing very well, and green is of course optimal. So great results. So just to recap, I was interested in talking about how to build human-taskable robots that learn. The big idea, or one big idea, was this idea of reward machines, which I described. And the key insight that we used to compute or to learn with those reward machines was to reveal reward function structure, a reward function to the agent, so that the agent could exploit that structure for learning. We got great results in discrete domains and in continuous domains. We can construct reward machines from a diversity of formal languages. We can generate them using symbolic planners, and we can learn them in partially observable environments to solve hard problems. There's a lot of code and a lot of papers. I'm just going to click through these so that you can watch them on the video. I wanted to give a shout out both to a new version. Our original work on reward machines was at ICML 2018. We have a new paper with a new algorithm called CRM that is a little bit different. I recommend using it in the code. It's at Rodrigo's webpage. And we also have a really nice paper on LTL for anybody who's interested next week at ICML. That's by Pashutan Vazipur, Andrew Lee, Rodrigo, and me. We've got some other related work, and then also some past work that we've done in formal languages and automata using planners that have models that may be of interest to people. So kudos to my students and to my group, and thank you very much for listening.
Excellent, thank you. Okay, so what was supposed to be 40 minutes has become 20 minutes for the discussion. So we'll have to make the best of it. I will start, I have a bunch of questions that I would not be able to ask. So I will start with one or two, but then I would encourage people in the audience, which has now become quite numerous, to please bring in your own questions and participate. Okay, what I want to start with is, there has been a lot of, in this session, differently from the previous session, I also want to say, there has been almost all symbolic and almost no neuro in all your talks, right? So this was a neurosymbolic workshop. There has been a tendency, I guess, more and more in recent years to relegate learning in simulators, because neuro has become larger and larger, and sample efficiency and everything you also mentioned. So the community seems to have embraced this and focused a lot of effort towards sim to real and accepted that learning is going to happen in simulation and figuring out how to transfer. Instead, your talks, you discuss about learning on the real robots. So how do you see learning in simulation in the future? Is it something that it will continue growing and play a role, or something you envision should go back to being less important than learning on the real robot as it was a bunch of years ago?
I want George to come and hand code behaviors for all my robots. That seems the best way of doing this. to answer from my personal perspective, I mean, we do neuro stuff all the time to provide actions and perception, but that's not what I do. So we leverage all that work to give our robots capabilities. In terms of learning in simulation, I mean, for me, I would like to represent the sim-to-real transfer as a distribution over possible models. So the kind of pitch I was getting towards at the end is saying you're kind of in some sort of Bayes adaptive MDP. The way to think about that is you're learning a model in simulation, and maybe you're doing some domain randomization, but you don't know which of those domain randomizations you're going to encounter in the real world. If you use something like a Bayes adaptive RL or Bayes adaptive MDP, you can then at execution time, you're effectively doing inference to kind of narrow down to which of those domain randomizations you've trained in for your sim to real transfer. I think that's one way of thinking about it. I'm not sure whether that would work in practice, but that kind of fits with some of the stuff I see going on in the kind of pixels to grasping kind of world. I feel that those would transfer, provided you're representing the range of possibilities within your policy.
Yeah, if we can, I can just chime in. I agree. I think that learning and simulation is going to be critical. I think the more experience and representation that an agent can build up, the more skills that it has, the better it's going to be able to tackle new problems more quickly. And I think that, to George's point about learning representations, I think that those are going to be, abstraction and representation are going to be the cornerstones of learning how to tackle new problems and to learn quickly in new environments.
I just wanted to pop in to say next time I'm in the UK, I will happily come up to Oxford and write some skills for your agents. Although I should note that I wrote a whole PhD thesis on how to try and get the skills autonomously. It just turns out to be hard. So to Sheila's point, I think that's exactly right. People do the sim to real thing because it's real and useful. Again, though, there's a sort of difference of concern, right? So if you're trying to build useful systems, then it's totally reasonable for one engineering method to be that you build a bunch of simulators, you learn on the simulator, and then in real life, you go do something on a real robot and it accelerates it. But if we really, in the end, want things that are completely autonomous, I don't know that you can learn in a simulator in a completely open-ended way. And so what I see when I see people learning in a simulator is they've built a simulator of this task, and maybe they've built 10 simulators of this task using. So Nick, we have a formalism called the hidden parameter MDP, which is similar to what you were talking about. It's called HIP MDP because, of course, it is. And you can imagine parameterizing that task and saying, well, I'm going to induce some variation. But you've done something task specific already there. So now we're imagining engineers following a robot around, and when it encounters a new task, building a bunch of simulations of that task. It just doesn't feel in the limit that's gonna work for me. When it needs to be able to do everything, and you don't know what it's going to have to be asked to do in advance. I think in the end, the role of simulation, unless the robot can build it itself, which it might be able to do, right? It might be able to gaze upon the scene, and build the BAMDP thing that Nick is talking about in its own head, build a simulation. Maybe that could be reasonable, but we just can't. Anything that compromises on autonomy is bad, like fundamentally bad, not useful. If that makes sense.
I mean, I think you need both, and if we use both. I mean,
that's right.
I mean, if we use simulation to actually then to convert the high-level plan into an actual metric plan, but we use the learning from human demonstration to actually do the main learning. And we've also, like Nick, we also use neural methods as well, as particularly for extracting low-level stuff. And I mentioned at the end of my talk that we actually looking at moving that neuro level higher up the learning hierarchy to actually do more of the learning using neural. Not that I'm completely convinced that's a good idea, but the research fellow was keen, and it seemed like an interesting experiment to try in any case, just to see how far we can go with that. Though with the current methods, we're not getting as human-like plans with our neural. We're getting lower scores on how human-like the plans are.
Okay, thanks. Another question I have, and if you want to, I forgot to say, if you want to ask a question in reactions at the bottom of the window in Zoom, you should have a raise hand. That way I can see that you do want to ask a question. I'll try to keep an eye on the, okay. Alper, you will go next. So in all your talks, all your talks focused on robot versus environment. I wanted to ask what you think when we also bring in other people, and then the problem becomes kind of inherently not fully observable in the sense that you may say something that deeply offends somebody and not be able to perceive that in any way. So is that so planning or reasoning for tasks that also involve humans, do you think it's something that will naturally come as an extension of this work, robot versus environment, or that's a completely different problem that will require a completely different kind of approach? I don't know who feels like going first.
Yeah, I'll go first if nobody else will. So to the first part of your question, I think that almost all interesting problems are partially observable, or they're partially observable by the very function of the representation. Your representation may be adequate for a task, but it's inherently partially observable in the sense that if you want to do something else, you may not have sufficient observations. But with respect to humans, I think that you can build systems that fit in. The problem is that those humans are very partially observable. You cannot, it's very difficult to predict what they're thinking, how they're acting. And I think I think Leslie maybe is going to talk about this, but we've done some work on this too, that I think you're going to have a richer notion of state and belief state, and that incorporates your beliefs about other agents and what they're thinking, and in terms of almost like theory of mind, in terms of how to tackle that problem and do so effectively.
Yes, I think clearly going partial observability, which is not what was assumed in the talk I gave today, but clearly that is going to be important in general. If you're trying to get something from the bottom of the box, that you may be able to see some of the stuff, but not all the stuff on the way. So you don't know exactly where something is, or you don't know exactly its pose. So moving on to that kind of task is clearly important if we're going to go away from sort of the toy tabletop environments we've looked at so far. So I think, I do see ways of extending what we've done and not having to completely restart from scratch doing that, but I don't have time to talk about that here. But I think it's something we've been talking about a bit in the group. And in a new grant we've put in there waiting for the results for. What's the second part of the talk, the question?
About humans. So of course, I didn't want to ask this just so that you could say, yes, sure, POM-DPs, right? So is planning for human-robot collaboration, let's say, the same problem as planning to open a cupboard and pick up an object, just in a different state space? Or will that require a fundamentally different approach?
I think it's not just collaborating with robots, but also planning how you can use the human. If you're trying to conduct some shared task, then the robot ideally should probably be doing as much as it can, but then it should also be aware of what the task, the capabilities of the human are, and then let or encourage the human to help when it can. And there's some other work which a student of Mehmet Dogar's, who's also one of the co-authors of the paper I talked about, and I also co-supervise him, is doing some work in that direction. But yeah, I'll let some of the others go.
So I know, Matteo, I'm not supposed to just say yes, POM-DPs, but yes, POM-DPs. But actually, so the ego process formulation I showed, I just kind of swept under the rug that actually it's a POM-DP formulation, not an MDP formulation. And there's a computationally theoretic reason for that, right? Which is that MDPs are computable or sort of nicely behaved computationally, which is a thing that AI people want, but of course can't be the answer, right? You can't model the general intelligence process and expect it to be efficiently computable. that's obviously wrong. And so only POMDPs are powerful enough to kind of represent, there's like the solution to any Turing machine sort of thing. So you have to be partially observable in that sense. The reason that I don't talk about it that often is that I think a lot of the kind of sort of nature that we build into robots and the field of robotics is for overcoming the kind of fairly well understood causes for partial observability. So for example, SLAM is a thing that takes partial observability because of spatial location and just gets rid of it, right? So a map is, localization is the thing that turns that POMDP into an MDP, and the map is the model for that MDP. And so now there are other cases that are not observable. There are other reasons for non-observability that are truly hard, but SLAM sort of takes care of most of them once you've seen. And so I think most problems will turn out to be kind of locally MDP looking, and that's why we can solve them. But we've got to understand all the infrastructure that gets us there, which we currently don't. In terms of humans, I think that there's a modeling choice here, like there's always a modeling choice. Okay, so only your pixels and your motors are real, and that means to the robot there's no built-in notion of a human. And so the question is, you can identify humans. When is it useful to model them? Well, you can start to think about, when does that get me an improved value, right? And you might be in a room full of 100 humans, but it might be useful to model the one you're playing chess against, not all the others. And then you can ask yourself, okay, why would I choose to model that person? Well, because the transition function changes in some way that lets me compute something more efficiently. So I think if we get into this mode of thinking about learning a task-specific model, and because it's our model, we get to go eyeball the insides of it, we get to kind of tinker with the insides, then we can kind of start to get theory around when it is useful to do that and when it isn't. Also, just wanted to plug my colleague Stephanie Telix has a really nice interactive POMDP model about how humans and all that stuff, and I think it's really neat. Thank you.
Thank you very much. So now we have 3 hands and 6 minutes. So we may not be able to answer all 3 questions. I would encourage everyone to meet later in Gather Town and possibly form a nice group where we can continue this conversation. Alper, do you want to go ahead?
Okay, sure. So my question was is to George Konidaris. So by the way, thank you all for the amazing talks. So George mentioned about the necessity of the abstraction for general purpose AI systems, and he mentioned about two kinds of abstractions. One is the state abstraction, and the other is the action abstraction. And you mentioned that okay, let's for now assume that we have the action abstractions at hand. But so what do you think about when should we learn the action abstractions? Should it come before state abstractions, or should we learn them one by one, or should both types of abstractions learn together?
So that's a great question. So for the purpose of the talk, I have this conceit, which is that the action instructions are sort of all there and they're finalized and they never change. And of course, all that's wrong, right? That's just a math convenience. So I think one way to view that result from that 2018 paper is that actually all the action is in the action abstractions, and the kind of rest of it is sort of, we can do the rest of it once we have the action abstractions. And, you know, like I said, I think at this point, there've probably been 50 PhD theses on trying to discover them autonomously, including mine, and it's very hard, right? I would say that what I expect to happen really in real life is that we're going to have an understanding of the relationship between these two things. I think the dominating hardness is on the action abstraction side, and the sort of dominating push, you know, most of the constraints are going to be the action abstraction side. So I think you'll be learning your action abstractions as you go along incrementally, and then they'll be a little bit constrained just to make them nice for symbolic representations later. So for example, if they're factored, like if they change as few other state variables as possible, that's good, right? So, and there's a bunch of results in the literature showing that. We're doing some of the things to that. I think Ben had a QLAP paper at one point where you change just a few factors and therefore you get a nice structure. You know, that's a property of an action that makes the symbolic part come out really nicely. And so there will be some interlinking stuff, but I think most of the most of the sort of obligation comes from the actions onto the state representations. Does that make sense? It's a fuzzy answer because we don't know how to do all of them at the moment, so I'm just kind of guessing. But
thanks for that.
Okay, thank you. So the next question is by Rod Gruben. Please go ahead.
Thank you. Nice talks. I had a few comments. I don't think we're going to get a comprehensive answer out of the group in the 2.5 minutes left or something like that. But just a few things. POM-DPs, absolutely got to do that. They just solved the so many problems, and they're hard to compute, but I think we should redouble our efforts and figure out how to do that better. Tactile. Number of talks on manipulation and no tactile data. There was a nice comment about autonomy I really like. I think autonomy and declarative and symbolic representations are dependent, mutually dependent, because you have to be able to predict the likely future states of the system in order to make sure you don't fall into a crater when you're exploring the moon or something like that. So I think they really go together. We have to do it. Multimodal is necessary. We need more sensor data. We need vision. It's not just, I heard several times, we're just going from pixels to motors. George, I think that was you. There's auditory, there's tactile, especially when you're doing manipulation. There's a little micro domain that is exactly, I think, isomorphic to the problem people are discussing, but it's different, has its own special qualities. And when we go into manipulation, we ought to try to do that. And I guess I'll stop there because somebody else may have a question in the next minute and a half too.
I may also want to say before we answer this that there is a 15-minute break, and all of you are welcome to actually take the break. I don't want to tie anybody to their chair, but we can also stay here if you don't want to use all the 15 minutes and continue this discussion since you're all here now. Okay, now back to the speakers to answer.
maybe I can say that I totally agree on the tactile thing. Actually, we're shopping for tactile sensors at the moment because manipulation skills just don't work without them, and everything else is a bit of a hack. We just don't have auditory sensors on our robots at the moment, but totally agreed that everything, you need full body, full sense, everything.
Not just for realistic systems, but because if you just base it on vision, you're going to find yourself stuck with no legal transitions out of the states you're in often.
I would just add there's a fascinating soft robotics community that deals with tactile sensing and all sorts of kind of compliant manipulation, that for that space of problems that they've got some really interesting technology. So like we're a long way away from being able to do the kind of things we've seen in all our examples today with soft robots, but I think for tactile and kind of rich perception around physical manipulation, I think I'd love to see some of this stuff put on soft robots.
Anybody else, or should I move on to the next question? Okay, so even before that, Emre said he has an announcement to make before everybody goes somewhere. Emre, please.
So I just want to say that the next session will start and end with contributed talks, and it will be a bit challenging because there will be 12 talks, 2 minutes each. So I think it makes sense if those speakers can try their screen sharing while we are in break. So those speakers, please stay and then try your screen sharing during break. That's what I wanted to say.
Okay, so Mohan, if you're still there, your hand was up.
You sure you want me to ask the question?
I do.
I thought you, oh, okay, cool. So this is just a kind of observation kind of thing, right? Like I'm curious what other people think. So I've been listening to these talks in this session and some in the previous session and stuff. And sort of the thought that keeps coming back to me repeatedly when I sort of see all the different people presenting their stuff is something that we all know, right? This notion of integrating symbolic and sub-symbolic approaches is not new, right? And even the notion of neurosymbolic AI, we can maybe claim as a new instance, but even that wouldn't be true because this has been looked at by others before. Right. So if we were to think of this as an instance, then maybe I can get the speakers, the invited speakers, to articulate what exactly are the challenges that we are looking at now that would be new and interesting. Like, if we don't focus on this neural thinking being the backbone, but instead focus on the symbolic and sub-symbolic approaches itself. And then I see repeatedly that people are talking about, including Sheila's talk, at least the way I understood it, is there are some fundamental concepts elsewhere that we can import to understand and draw this, get better performance. So I'm wondering if the speakers can talk a bit about what exactly are the challenges at the representation, reasoning, learning level when you try to look at the symbolic and sub-symbolic approaches. I'll stop. Matthew, you're sort of frowning. You do not want me to talk.
No. I do. And now I'm waiting. And now I'm waiting.
You've opened the Mohan box. You can't close it now. Hey, Mohan. I was, from my perspective, I think for us, what we're trying to do that feels, it's not unique and it's not new, but it's representing, and in fact, your AIJ paper, like your Hippo work, I think, Mohan, is really akin to what we're thinking about, which is how do you represent the effects of actions when those effects of actions change your knowledge? And I think that is the thing that is exciting. That's what I want to spend the next few years thinking about and going back to. So that may be, we're thinking about it in terms of the action generating some data that then updates a model that then changes something about the rest of your model. And I want to push that as further forward than has been done before. So I think that for me, that's a kind of specific new technical challenge, but builds on work that others have done, including you.
I mean, Nick, you mentioned that, and indeed we've done that as well. Going from the neuro to the symbolic is relatively straightforward. I don't say it's easy, there's challenges there, but you can often use the neural mechanisms to do the low-level stuff, move up to the symbolic level, and then stay there for the rest of your time. The problem is going back in a direction, in particular, sort of injecting knowledge, which may, wherever it's come from, back into the neural level in order to influence its behavior. And there's really precious little of that I see, but I think it's kind of a really important challenge. If I knew how to do it, I'd tell you, but I haven't figured it out yet.
That's sort of what we're trying to do with some of our work, Tony. I think we're trying to take human advice and instructions and embed it into not just symbolic, but also sub-symbolic pixel-based things. And it requires understanding what those human instructions actually mean and what the symbols mean, that are the vocabulary for the instructions. And often you can do that. I mean, people do this, they do natural language, groundings. They do it with large corpora where humans have annotated that, yes, this is correct, this is incorrect, this is correct. But you can do a lot with formal languages because you can evaluate whether they're satisfied or not. So I think that's a very important problem, the one that you just articulated. I also think the problem Nick discussed is important as well. This whole notion of epistemics, epistemic planning, being able to represent the beliefs of other agents and being able to do multi-agent reinforcement learning, collaborative or not collaborative teamwork is something really important. And to a question that somebody asked before, it builds on I think a large base of beautiful work in knowledge representation that's been done, decades ago, and understanding how to mobilize that to sort of revisit it from a data-centric or an experience-centric perspective is a really interesting challenge to work on.
And of course, I said that there is perhaps more work going from the sub-symbolic to the symbolic, but it's still, the problem is to make sure that the concepts you get out are somehow human-like and sort of align well with other knowledge sources or things that you might then want to explain or interact with a human being. And again, there is work in that direction, but I don't think it solves the problem.
Sorry, go ahead. No, Sheila, you should finish. I was just going to say, from my point of view, the neuro is kind of neither here nor there. So my lab does a lot of deep reinforcement learning. So we experience with deep nets. We use them all over the place. We don't use them in the simple work just because there's a solve complexity mismatch. for me, a sort of classifier is a classifier, right? But so the real question is what is that classifier classifying? Yeah, or is it a classifier? Is it a probabilistic classifier? Like, what's the right mathematical object you should be using as spot? So I guess I have a slightly different view of a lot of these things from everyone. I've been thinking for a long time of how to do the abstract symbolic planning with MDPs thing. And the conclusion I eventually came to is that, if we don't understand the semantics in some deep, complex way, we don't understand when you get a symbolic, when you get an abstract versus, discrete versus non-discrete versus continuous versus stochastic model out. If you don't deeply understand what your symbolic level is actually representing, then everything else could just be wrong. And I come from this sort of combined task and motion planning world where you very often assume a symbolic representation, try and plan with it, it doesn't work, and now you have to do motion planning to fix it. And it turns out that everyone is doing motion planning to fix it in a different way because their symbolic models are broken in a different way because they just hand constructed them to do something that seems like it would make sense. They don't have actually consistent semantics across. Sometimes even the same lab doesn't have consistent semantics across their own task and motion planning papers. They just have symbolic representations they wrote down because they seemed right. And so everyone's doing much more work than they should be doing. I think the community has been trying to do this for a very long time. I think there's a good reason it's been trying to do it for a very long time, and because it's an incredibly important question. And I think there's a reason that it's hard because it's an incredibly important question. And so I don't expect that it's a thing we can just make tons of progress on by just throwing compute at. But I do think that a lot of the other things that are interesting and fashionable and are making a lot of progress now are more like that, and that's to their credit. But this problem is not like that. This problem is gonna, some number of math insights later is gonna start to make sense. It's not gonna be we computed enough stuff. I don't know if that's the sufficiently controversial answer to the right interpretation of the controversial question Mohan was asking. But that is the one I chose from the distribution of questions I thought he could have meant. So.
Just to sort of come back, doesn't matter. I was just looking at your interpretation. That's as good an answer as any. So thank you.
Excellent. Okay, so we are going to leave 5 minutes for the next set of speakers to try their presentations, screen sharing and whatnot. I would like to thank everybody, especially our speakers, for the presentations and the discussion. And I hope that I can see you later in Gather Town, if that is at a civilized time in your time zone. I know it's like, I think, midnight, 1 a.m. here in the UK, so I'm not sure how many people are there.
It's only 10 minutes past 8. It's not midnight.
I'll check. Okay, so then maybe that is the time it's supposed to end. So that's good. I'll go back to the schedule and double check. So that means I will see all of you later there, and we can gather virtually. So, okay, I'm gonna then leave here and we leave the floor for people trying to share their screens for presentations. Thank you again.
Thanks, bye.
So Shiji, yeah. Shall we ask people one by one, and then if they want, they can try screen sharing, and then we continue quickly. Is it fine?
Sure. So this is a 5 minutes break to everyone except for the lightning talk speakers next. So if you are one of the lightning talk speakers, could you please connect, and so we can also see your name, who is presenting. The first paper from Prague Singla. Yep, so looks good. If you want to test your speaker microphone as well.
Hello, hi everyone.
Yeah, we can hear you. Great, thanks.
Okay, thank you.
And then Stephen Tomic. You can say something.
Hello, can you hear me? Okay, can you hear me now?
Yes, it is not full screen, but we can see the slides. It's not full screen.
Yeah, right, because I didn't press. Okay.
Okay.
Now it should be. Okay, thanks.
Thank you.
And then Marco Bagatella.
Yes, hello.
Yes, we can hear you.
Okay, let's see if you can also see this.
Looks good.
Okay, awesome. Thanks.
Yep. Next, Mohan. Yes, we can see the screen.
I think I've spoken already enough, so I don't need to test my.
Yes, thank you.
Thanks. And next, Cheng Cui.
Can you see the screen?
Yes, it's not a full screen, but we can see it. Yep.
Okay.
Good. And our very next speaker in this session, so we have 6 short presentations right now to be.
Gigi, but let's see all 12 because there is no break in between.
Oh, good idea. Yes, good point.
Okay, yes, continue, please.
So next, Wentao Yuan. If it's a first author presenting. We can see the screen, but we don't hear you.
Hear me now?
Yep.
You hear me okay? Okay,
yeah,
good.
I can hear you. Thank you. And so now we move on to contributed talk session 2. So as Emery suggested, I think it makes sense we continue, but not sure if the speakers are here. Maybe they thought they still have an hour also. If they're here, the first one in contributed talk number 2 will be Nakwo Gopalan. Nakwo, are you here? I see you here. Are you with the computer? So feel free to tap in the chat box. We can come back to you.
By the way, the first talk should be, I guess, learning robot manipulation programs and neurosymbolic approach from Parag Rohan Powell.
Yeah. We already tried that. So we are in the second batch.
So, oh, for testing. Okay.
Yeah. So it looks like Nakwo is not here. Then the next one. So again, we are testing the contributed talk session 2. In there, the next talk will be.
Shiki, I did not hear you. Yeah, you want me to do something?
We're testing screen sharing and microphone speakers.
You want me to try it now?
Yes.
Give me 1 second.
Yeah. Or we can come back to you in a minute.
Can you see it?
We can see it. It is not full screen at the moment.
Oh yeah, it's not.
Sure, it looks good. Yeah.
Yeah, but I think I can present from here. Oh, it's over here. The button was just hidden. But yeah, does that work?
Yeah. Yes, it works. Thanks. And
wait. So it is the wrong screen. It is speaker screen.
Yeah, I'll move it. So I'll make sure to share the other screen. I'll set it up in advance. But
okay.
Thanks.
So let's continue testing the screen sharing microphone speaker. The next one will be next talk will be Huang Zhiao.
Actually, I'll be presenting. I'm the second author. I'm Xiaoshen Li.
Hi, Xiaoshen. So could you share a screen and just have a quick test?
Sure. Is this working?
Okay, good. Thanks. And then Emily, she's.
Hi. Just give me. Stop sharing. Okay.
Can everyone see that and hear me all right?
Yes, we can see you. We can see the screen, not you. We can hear you.
Perfect.
And thank you. And next one, Ivana or Matteo? So Jivko.
Yep, that's me. So let me try to share my screen.
Mm-hmm.
Does this work?
Yes, we can see the slides. We can see. Great, thank you. And next, we have only two, David Fazio.
Yep.
We'll start sharing very quickly.
Yep.
Okay, good. Thank you. We can see the screen. And our very last test, Alper. Yeah, I think it worked.
Yes.
So, do you still want to test it?
No, I'm okay.
Okay. All right. So then we're all good. So all screen sharing works, microphone, speaker works. Then let's get back to the lightning talk. We have 6 before the very last panel discussion. So the very first one. So, but before that, special thanks to the first group of authors. So I know that some of you are not in very friendly time zone right now. It's midnight already, so you stayed up late. Thank you so much to make time and be here presenting to us. So okay, the first one, Praj Singla.
Hi everyone. I'm Luís, so I'll be presenting.
Yep. Please start sharing screen and give the 2-minute talk.
Yeah, is my screen visible?
Yeah.
Yeah. Okay, so I'll start. So hello everyone, I'm Vishwajit. I'll be presenting our work, Learning Robot Manipulation Programs and Neurosymbolic Approach. So our problem is to enable a robot to perform object manipulation tasks on a scene, given some instruction in the natural language. So we want to learn a task planner model that from the scene infers a task plan G is a sequence of sub-goals. Any sub-goal is a movement of object from one location to another. We assume the robot has a motion planner which can execute the plan as follows. So our learning problem is given a data set of initial scene, final scene, and instruction. We want to learn a neurosymbolic program that outputs the plan G as a sequence of goal on executing on the initial scene. So now we'll describe a neurosymbolic manipulation in a high level. So we have the instruction and the initial scene. Initial scene has objects which has some attributes like color and size. So instruction is passed through a language reasoning module that gives us a program in the DSL. A program is a sequence of action which takes an action concept and 2 subprograms. A subprogram determines the objects to be filtered. So this we have a then visual reasoning module that executes each of these subprograms and object embeddings from the initial scene and grounds this subprogram to specific object instances from the scene. Thus, we get a grounded program. Finally, our novelty here is to have an action simulator that extracts locations from the initial image, which is a concatenation of bounding box and depth. Then there's a neural operator F that takes the 2 locations and the action concept and produces the final location. And this final location is then mapped to the 3D space of the robot to get the sub goal. And executing all the action, we get a plan and also the final locations in the final scene. This is compared to ground location of the final scene through a loss function. So our key novelty is that along with learning a neurosymbolic program, we also learn the action representation. So these are results. We show strong generalization to novel scene instruction compared to a neural baseline. And on the left, we show a successful execution of two-step instructions. So thank you. For details, visit our poster.
Thank you. And our next talk, Stephen Tomic.
Okay, can you see my screen?
Not yet. Yes.
Okay. So I'm Stefan Tomic. I'm presenting the paper towards learning grounding for abstract control policies. And first motivation, because human, they don't usually think on the level of motor primitives, and we tend to use abstractions for reasoning. For example, being in a store, we will tend to think about what items to buy and not exactly how to move our legs or arms, so on. In learning, for example, when we learn to drive, we will first maybe learn how to control the wheel and maybe shifting gear, and then we will switch our attention to more general traffic planning. So we are interested in this question about how to enable robots to learn on a more abstract and strategic level, but still be able to reduce this to the level of motor primitives. And to address this, we are using this from our previous work, something called abstract policies. And main characteristic of these abstract policies is that they can be grounded or instantiated across different physical domains. So for example, we have abstract policy execute at that will act toward making agent being at the place of artifact and then executing certain action. So given this grounding, we will have a robot that is will reach the place of battery and then pick it. If we change grounding, another execution will happen when the robot will go to the cache register and then execute picking action. And basically, you can see how by changing this grounding, we can of the same abstract policy, we can execute different kind of behaviors. So the idea here is basically to learn this sequence of instantiations of abstract policies, and then learn this policy that achieves higher level goal. Okay, it's fine to have this higher level policy, but at first it's not abstracted. It means that it cannot be reused further. But then this representation, our representation allows us to, this learning also explores the state space, and we can make a structure to make also this policy abstract, which means it's reusable and can be used further in the same way as other abstract policies. Thank you.
Thank you. We move on to number 3, Marco Bactella.
Yes, just let me share the screen again.
Yep.
All right, so a good afternoon or a good evening, everyone, according to your time zone. My name is Marco Bagatella, and in these 2 minutes, I will try to quickly introduce the paper Planning from Pixels in Environments with Combinatorially Hard Search Spaces. So the intuition as a paper mainly came from 2 very simple insights. On one hand, we have that modern learning agents still struggle to form complex plans from raw visual inputs, especially when some kind of logic reasoning is required. On the other hand, we have a class of classical algorithms, for instance, graph search algorithms, that can be used as very efficient planners or solvers in particular situations, but they usually need access to a very accurate model of the environment or even on a perfect simulator. And by combining these 2 insights, we propose our method that we call PPGS, as it tries to plan from pixels while leveraging the power of graph search. Our contribution then is really twofold. First, we have the actual method. The actual method learns a discretizable war model and then uses this war model to reconstruct a latent graph representing the environment. This latent graph can then be searched efficiently to retrieve a good policy. On the other hand, we also present a suite of challenging combinatorial environments that, as I mentioned, require some form of logic reasoning to solve. And if you are interested, you will find out that it can be challenging even for human. I'm thankful for your attention, and I hope to see you soon at the poster sessions. Thank you very much.
Thank you. Let's move on. Mohan.
Okay, give me a voice check, please. Can you hear me? Hello, can you hear me?
Yes, we can.
Yeah. Okay, cool. So then let me get started. So I thought about what I would talk today, right? And I thought, okay, with all these people being overloaded, instead of me getting into the technical details, which I can discuss later, I instead chose to do a high-level kind of overview because this is work being done over several years. Okay, so the question, first bullet here I asked, right? So the observation I learned, the lessons I learned from all these talks we have heard so far, and also from work that I've been doing, is this notion of symbolic and sub-symbolic approaches is not new. Neither is this notion of neurosymbolic AI. It's just a new instance of this. And the second thing, again, that's been reinforced to me through all these talks is deep learning is a powerful tool. It's not the sort of quote unquote backbone. Right? And there is a significant overloading of terms.
terms that have been around for a long time, like inductive bias, it's known for long in machine learning, or terms that are fully autonomous, which to me has no meaning. Right. And so because what does it do? Okay, I won't go there. So the key sort of lesson that I learned is this cognition mismatch, right? So this easy is hard, hard is easy is essentially means that what is often very easy for us is very hard to do with machines. And what is very hard for us is very easy, like, sort of close range manipulation and other things. And these are the things that deep learning and other such tools seem to excel at. So then the sort of lesson that I learned is if we can focus on these interesting problems at the intersection of reasoning, learning, and control, and keep the representational choices as being the crucial thing to do, then we can learn from all the research that has been done before, even though it is not directly related to the so-called neural approaches, which again, I would say probably is a partially incorrect term to use. But so then we can sort of develop really interesting architectures. And my poster is about attempt over the last several years to develop such an architecture. So I'm going to spend the rest of the time just telling you briefly about the core ideas and commitments we make in this architecture. The thing we do is we say we're going to take a cognitive systems formulation. We're going to represent reason, act, learn jointly with different abstractions and different schemes. We're not going to try and go after this, this so-called unified representation. Instead, we're going to have these separate ones, but instead we're going to think really hard about how to couple these in nice ways. So there is nice flow of information and control between these different abstractions and different schemes. And we view this as internally to this robot, a logician, a statistician, and a creative explorer that inform and guide each other. And what we see repeatedly in different domains and different robots, in different kinds of problems, is that questions such as what to do, when to learn, what to learn, how to do so efficiently, follow through naturally and simply if we take this approach. And learning to us is interactive, but it's not incremental, it's cumulative. And there is a subtle but important difference here. We don't sort of just keep adding to the data set that we have. Instead, we try and crystallize concepts that help us sort of still reason and learn efficiently. And in the poster, I talk about an instance of this knowledge-based reasoning and data-driven learning, where you will see that the notion of stepwise refinement across these different abstractions increases your confidence in behavior and promotes scalability significantly. There's a clear separation of concerns that again follows through naturally. And so the domain-independent and domain-specific knowledge can be easily compartmentalized. So you can take the same methodology and architecture and port it to different problems. And the specific instance I will talk about, if you come to the poster, is this non-monotonic logical reasoning, probabilistic reasoning, and deep learning that inform and guide each other. Again, the state action spaces for these different things are determined automatically. And of course, learn knowledge, to answer Tony's question, I don't think it is here. You can actually go from deep learning rather nicely to up to the symbolic, and you can come from symbolic back down to the deep learning. And you can also provide quote unquote explanations, again within quotes, because these are just relational descriptions in our case, describing the beliefs, evolution, and decisions. If you want to learn more, come to the poster. Thank you.
Thank you, Mohan. The next one is Cheng Cui.
Hi, I'm Chen Cui from the State University of New York at Binghamton, and our work is called Perceptual Reasoning and Intellectual Learning.
Sorry for interruption, you're not full screening the poster.
I think that's the best ratio that I can do, or otherwise some part of the poster will be covered.
Okay, feel free.
Yes, so our work is called Perceptual Reasoning and Inductive Learning for Planning Urban Driving Behaviors. It is motivated by that existing sequential decision-making algorithm can reason with contextual knowledge, but the contextual knowledge is hardly comprehensive, and it may include inaccurate information. And so thus agents may need significant efforts to recover from those incomplete and inaccurate information. So we developed a new algorithm called Parallel, which is able to learn to improve contextual knowledge base. And with the perception of the stream data getting at runtime and the interaction, we close the perceive reason act loop to identify the main contribution of this research. From the overview graph of our Parallel framework, you can see there are two main parts. The perception reasoner and the induction part. So the perception reasoner consists of a classifier which perceives the feature vectors to make a state estimation. And the knowledge base consists of rules associated with weights. These weights can be learned through relation learning from the data collected. Thus, the agent is able to learn to improve the contextual knowledge. We have compared parallel with a few comparative baselines, and the results show that our framework is able to learn to reason with contextual knowledge, and it achieves the lowest average cost while achieving the highest average reward to achieve the goal. So that's it. Thanks for listening. More details can be found in our paper. Thank you.
Thank you. Our very last lightning talk of this session, Wentao Yuan. Yes.
Hi, my name is Wentao, and I will present SORNet, Spatial Object-Centric Representations for Sequential Manipulation. This is joint work with Chris, Karthik, and Dieter. So in sequential manipulation tasks, the robot needs to constantly reason about the spatial relationships among different entities in the scene. And traditionally, this is done by explicit state estimation plus task and motion planning. For example, we first estimate 60 object poses of objects in the scene and then use a temp planner, generates plan, and the robot executes it. But this type of pipeline, especially the state estimation part, is hard to generalize to a wide variety of objects. On the alternatively, we can use like an end-to-end policy to try to generate motion directly from pixels. However, these methods usually very specific to the task, and if you change the configurations a little bit, they won't generalize. So in this work, we present SORNet, a framework that enables spatial reasoning without explicitly estimating the object states. The key idea of SORNet is to learn object-centric embeddings from raw GP observations that capture spatial relationships between different entities in the environment. So our network architecture consists of two parts. First is a transformer backbone, which takes an input frame and a set of query objects and produce an embedding vector for each of the query object. Oh, sorry. The key thing here is these query objects need not to match with the objects in the scene. They can be arbitrary in number and appearance. So we're not doing object detection or segmentation. And the second part is a predicate classifier, which takes these object embeddings and basically generates a list of logical statements about spatial relationships of objects in the scene. And the key thing here is our network's output can change adaptively with the number of inputs. So it generalizes without retraining to arbitrary number of query objects. So SORNet is trained only on classification of logical predicates, but it can capture actually continuous spatial relationships. For example, we can train a regressor on top of the embedding to predict the 3D unit direction between the end effector and a certain target object. Moreover, SORNet generalizes zero shot to unseen objects without any fine-tuning. So we tested on several spatial relationships reasoning tasks. First one is on this clever data set, which contains
sorry for
images
interruption. May I ask how many slides you still have?
Like 2 more. So yeah, if you want to learn more details, you can come to the Gatherton poster. So here we show much smaller generalization gaps compared to baselines. And we can also apply this framework to real-world open loop planning. And finally, we show results for generalizing the 2 tasks about continuous spatial relationships. Yeah, thank you very much.
Thank you very much. So yeah, a lot of exciting work. Now we're 7 minutes behind the schedule. I think now, Emery, are you ready to lead the next session?
Okay, thank you. First of all, let me remind you the 10 minutes long videos of the long contributions are uploaded in our webpage. So please go and have a look to those videos. Okay, thanks again. My name is Emre Uğur. I am from Boğaziçi University, Turkey. I am one of the co-organizers of the workshop. And now it is great pleasure to introduce you Masataro Asai. He's already here. I think maybe you can share your screen, Masataro.
Oh, hello everyone. Yes, let me share the screen.
Okay, thank you.
By the way, just before starting, is it okay for you, Masataro, to record the session so that we can host it later on?
Yes.
Okay, let me introduce Masataro. Masataro is a research staff member at IBM Research Cambridge. So he has PhD from the University of Tokyo, and then his main expertise is in classical planning and heuristic graph search. So when I came across Masataro's work like 1 year ago, I directly wrote him an email and then asked him to be an invited speaker for a potential future workshop, which is happening now, and then he accepted that time. That is, I'm very happy about that. So Masataro is not a robotics person, but the model he's going to present here is very related to what we are trying to do. So he, like George, he also tries to learn action and perceptual symbols that can be used as PDDL inputs. And different from George, his system is built on top of spatial, but I think a very general deep neural network, which is again very related to what we are doing in robotics. And again, different from many other works. He not only learns object or perceptual symbols, but he also learns action symbols, even if he is not doing robotics. So floor is yours. Thank you very much.
Thanks for the introduction. Okay, now I think I can start. Yes, thank you for the introduction. I'm not a roboticist and no connectionist. Therefore, I may have a very different worldview from the most of the attendees in this Zoom session. Therefore, yeah, please forgive me for if I have too much problem for that. Yes, I'm Masataro Asai from MIT IBM Watson Lab. I talk about symbol grounding with classical planning as an example. Do you see this as a full screen right now?
Yes.
Okay,
yes.
Good. Okay, yeah, let me start. Now imagine that you found yourself on the surface of Mars. Yeah, you're here. You may have some kind of base, and then there are a couple of potatoes. You may have a rover. You know that there is a rocket ship that you can go back to Earth, like a couple of hundreds kilometers away. You definitely want to go back to Earth. Yes, but if you make one mistake, then you die. And also, this is an unexpected emergency. Therefore, well, you are not trained for this kind of situation ever. You need to be very creative. Now, recently, there are two factions. Well, actually, there was one question before in the previous session about this question. So there are two dominant approaches right now to the intelligence. One is to use the learned behavior. Like, do you want to, but like in this kind of Mars surface, do you really want to just follow what you learned before? Like continue eating a potato with the same rate that you were trained for? No, I don't think so. I think don't think and feel, and then like dancing like this is not a good idea. So this is what I call the reflex agent that just follows the something that he already knows. In contrast, we want to build a system that think ahead and adjust the behavior, create a behavior, and choose an appropriate behavior. So this is something I call the deliberative agent. I wish to build a logical deliberative agent that operates on the raw input, such as visual input. So this is the goal of the line of research that I am pursuing. Now, yeah, my background. So I've been working on the classical planning systems. And then the classical planning system is a deterministic, a sequential decision making under a deterministic and fully observable environment. So it has some restriction already, but well, it's a symbolic system which excels at the logical deliberation. So if the problem of solving an A puzzle, which is this sliding tile puzzle, then the system can solve it well below 0.1 seconds. It's quite fast, but only when we have the proper PDDL model given by the human. So the PDDL model is a planning domain description language, which contains a description such as there is a move up action for sliding the tile up, and then there is a precondition which allows these actions to happen, and an effect that describes what will happen if you use this action. But the problem is that for the image-based input, this is not applicable because we do not have a PDDL model, which is a big problem. I've been working on this problem with a framework called the LATPlan for almost 4 years, which addresses this problem without any human knowledge, like this image contains 9 tiles, or that some of these tiles could move. Therefore, there's no human annotation, including the propositional symbols or the action symbols, as as was introduced earlier. So, but wow, okay, let's discuss further. What's the key problem LATPlan solves? So this is traditionally called the knowledge acquisition bottleneck, which is the task of, or the cost of turning the visual or sub-symbolic observations into something more symbolic, such as PDDL model. To solve this bottleneck, we must automate 2 processes, not just one. The first one is a symbol grounding, where the symbols means the words in the PDDL model. So if you look at the PDDL model, we can find something like panel 7 or the location x0 on y0, which are called objects. Another thing we can notice is that there are predicates which describe the relationship between objects. So the empty xy is a relationship. Furthermore, there are propositions which are instantiations of the predicates with a certain objects. And then finally, there are action symbols such as sliding up. The second process we need to automate is to describe the action symbol using the other symbols, such as propositions. So the task is called, this is called action model acquisition, whose task is to describe the transition rules with symbols, such as the preconditions and effect. Now, these are the knowledge acquisition bottleneck that LATPlan solved. As a result, the LATPlan system automatically generates a symbolic PDDL model purely from the image observations. We can see the example on the left, which shows the generated PDDL model, which contains anonymous the propositional symbols, such as Z0 or the action A1 or A4 or A398. So these are not very, given by the human, but automatically generated by the system itself. And as a result, by solving this problem, we get the visualized plan output on the right. All symbols are anonymous and generated by the gensim operation generating the symbol. And I'm not interested in human symbols at all, because requiring human symbols as an input is called parasitic in the past work literature. Now, what's the now I describe the LATPlan system. It takes 2 kinds of inputs. The first one is a state transition input. So it consists of pairs of images. So each pair represents an image before some action is performed and after that action is performed. But we don't know what action is performed, and we don't know how many total number of actions exist in this environment. Now, the training is performed on this first input, and then after every training is finished, we now use the second input called the planning input. So it contains the initial image and the goal image, which specifies a problem to solve. So, and then the system contains a domain-independent classical planner that's been developed in the classical planning community for almost 20 or 30 or 40 years, which is very capable, which is very high performance. But the problem is that they require PDDO models, which does not exist because all the inputs and also the outputs are represented in a sub-symbolic representation, which is images. So we need to bridge a gap between the sub-symbolic and symbolic representations. Now, how we do this? The Lapland system consists of 5 steps. The first one is a propositional symbol grounding. So it's done by a neural network called the state autoencoder, which is a discrete VAE. So specifically, it has a binary concrete VAE. It provides a bidirectional mapping between the images and the propositional states, which contains bit vectors, which are bit vectors. So if its length is 25, you can see it as a state with 25 propositions. Second process is the action model acquisition. So after learning the mapping, we convert all of the transitional inputs into a binary state, then learn the PDDO action rules in this binary state. Now, all training is finished at this step 2. Now, there's no further training of the system. We take the initial image and goal image and convert them to the state. Then using the PDDO action model and the initial state, we use the domain-dependent classical planner to produce the plan. These plans can be simulated from the initial states to produce the intermediate states. But the problem is that these intermediate states are, because they are purely generated for the neural network, we don't know how to interpret them. But because we have a bidirectional mapping from the propositional states to the images, now we can visualize them. Bit of detail about the variational autoencoder. So it's a part of type of autoencoder, which is an unsupervised learning method for a neural network. It tries to perform a lossless compression. Therefore, the target function is an identity function. It consists of 2 parts. The first one is the encoder, which maps the input to the latent vector z, and the decoder, which maps z back to the input x. It's trained by minimizing the input, the error between input and output, which is called the reconstruction loss. In the standard VAE, well, or the neural network in general, these latent vector z is real valued. But so therefore, the real valued inputs are not usable from the propositional symbol reasoning in the classical planning. But recently we have several discrete VAE implementations which learns a latent vector z, which maps to true and false. Therefore, we use an instance of such discrete VAEs, such as Gumbel-Sohn-Max VAE and binary concrete VAE. Now, what's the binary concrete VAE? So it looks like this. Before the training, the latent vector is still continuous and the output is completely random. But after the training, the latent vector converges to a 0, 1 value and output converges to the input. Okay, now we get the state representation, which is propositional. But this is not sufficient because we need actions. We have a transition data set, xt, for each pair of states. There are xt, that's a current state, and xt plus 1, which is an image that is 1 step later. We convert each of them to the latent space, which is zt and zt plus 1. Ideally, if we know the action label or the action symbols, then we can prepare separate neural networks to predict the next state from the current state. But the problem is that our dataset does not have action symbols assigned. They are not given. Therefore, we don't know how many networks we need to prepare. Also, for each transition, we don't know which network we should train. This is important because if you train the different network or the wrong network with the wrong transition, then the training gets totally messed up. So the system is required to do an action symbol grounding, which contains 2 steps. First one, generate action symbols as many as necessary. Then assign the meaning to the action symbols, which is called grounding. Therefore, we ground the action symbols to the PDDO definitions, preconditions, and effects. Okay, now how we do this? This is done by a neural network called action autoencoder, which is the Gumbel-Sohn-Max VAE. It has a single latent vector, action A, which converges to a 1 hot vector at the end of the training. So only 1 value in the many neurons becomes 1, Therefore, the one that became 1 can be seen as indicating the action symbol out of all cells. It contains the encoder that is called action that takes two states, current state and successor state, then produce the action label. Then this decoder is called apply because it takes the current state ZT and the predicted generated action label, then predict the successor state. The neural network is trained by minimizing the loss between the successor states in the input and output. So you can notice that there's no loss function for the action labels. Therefore, these action labels are trained completely unsupervised without human interventions or the data. Okay, now we have SAE and AAE. We can combine them into a single large neural network to perform an end-to-end training. Now you can see that the AAE module is appended at the bottom, which is connected to the state representation produced by the SAE. There's one more step we need to perform, which is that this apply function, which was neural network, is a black box. And then the apply function essentially models the effect. And if it's a black box, then we cannot convert them into a PDDL. So we use a very specific implementation, which I don't describe because I don't have enough time, called backed to logit apply function in the Ichikai paper, where the entire neural network is called a cube space AE. This learns a PDDL compatible effect. Now, the meaning of PDDL compatible effect, we will come back later to discuss what it means. Okay, in the latest work, in the archive paper just published a couple of weeks ago, and then is under submission at the journal paper, is called a bidirectional cube space AE. Cube space AE is able to generate the effects, but this one predicts backward in time in order to learn the preconditions. The neural network contains a symmetric copy of a cube space AE, and this results in a more accurate and a higher success ratio. Okay, here I show several experimental results, just a short. We use the 6 domains, including the 8 puzzle, 15 puzzle, lights out game, the other types of lights out game, and the blocks world, and finally the Sokoban. These are the success ratios over 40 problems per domain. And then what we are seeing on this table is that the bidirectional cube space AE outperforms cube space AE in the blind search. But the huge advantage of our system is that we can use a off-the-shelf classical planner. Therefore, we can use a more sophisticated pruning method. We can look at the success and the failure rates, examples in this figure. So the first one is a successful or the correct planning example. But the second and third one are the wrong examples produced by the system. Now we can see that in the second example, there's a blue block that is floating on the air. We implemented the domain-specific validator, which detects that these are wrong. And also we can see that there's a red block that suddenly turns black in the next step. These are another example that is invalid. But these failure cases are quite interesting because it shows how the neural network makes a wrong decision or the wrong understanding of the world. In the bottom, we see other successful examples. Okay, takeaways. Now the system works, but what we can learn from that? I want to stress several stuff. In the earlier talks, lots of people talks about the symbols, but there's no the symbols. What I mean by this is that there are separate sets of symbols, propositional symbols and action symbols. They have different role in the cognitive reasoning. And we call this, they are in separate namespaces. If you have experience in writing in Lisp, then this is kind of similar to Lisp too. Scheme doesn't count as Lisp. Therefore, we need a separate mechanism for each namespace for performing the symbol grounding. If you look at the PDDL model written by Human, we identify 6 namespaces in total. Therefore, we need 6 separate mechanisms. So we already see that the SAE learns the propositional symbols, AAE learns the action symbols. But what about the predicate symbols, like on XY, which learns the relationship between the objects? What about the object symbols itself, like the blocks in blocks word, blocks A and blocks B and block C? What about the problem symbols, like word 9086? So this kind of tells that, like, identifying, we have been in the same room before, so identifying the same environment. And finally, domain symbols, like blocks word domain. This is kind of tell, okay, this new environment I'm seeing is operating under the same set of action symbols, same set of rules. So all of these kind of symbols must be generated by the machines by themselves without the help of human. How should we find each mechanism for each type of symbol? In order to do that, you need to understand your target formalism deeper. So I'm encouraging you to follow this kind of reasoning in your robotics context. Okay, let's revisit the cube space AE, which learns a PDDL compatible effect. What does it mean to have a PDDL compatibility? Now let's use an example of eating food, like pizza. Its precondition is that you shouldn't be full beforehand, and also you should have the food. Its effects consist of delete effects and add effects. The delete effects tells something that becomes false. So if you eat food, that there's no longer food because it's in the stomach now. And also there's an add effect that you become full. Okay, and then the action application in PDDL, actually the strips, is defined by a set operation of like set minus delete effects and the set union add effects. Now you can notice that these effects do not take ZT as the argument. So it's a del A, not del A ZT. It's a single argument function. This means that they do not depend on ZT, but in the earlier slide, I just described that in the naive AAE, the apply function takes 2 arguments, ZT and A. Therefore, there's no separation of the structure that can be seen in the PDDL model. This kind of dependency can be properly modeled as a graphical model. In PDDL, effects must not depend on ZT. Therefore, there should be a random variable E that's independent from ZT in the graphical model. Okay, on the left, we can see the naive AAE that is not PDDL compatible. On the right, we can see the fixed AAE that is PDDL compatible. Cube space AE has a mathematically sound background like this one. Therefore, we can produce the PDDL model. So this kind of reasoning provides a powerful mathematical framework by combining graphical model, maximum likelihood, and a variational method to enable end-to-end neural network training with a statistically sound objectives. So this is quite different from the existing approaches that like just put together a bunch of machine learning method that is trained separately, and then like this part has this kind of machine learning methods like SVM. This one has a different machine learning method like random forest and so on. This is trained end-to-end and is a single, and its total objective is statistically sound. To do this, to apply this kind of approach to your target formalism, you need to have a very good understanding of your target formalism. So what we did before is to convert everything into a PDDL, but for example, we could think about you have a nonlinear dynamics. We want to convert them into linear latent control and then use the fast linear solver instead of trying to use a nonlinear solver, which is very slow. So the caution, it requires deep understanding of your formalism. So if you want to do something with a neural network, you should know what you're modeling. Okay, extending the generative model, what can we do? What else can we do? These are all unpublished ideas. Some of it is partially working. I submitted several unaccepted in the workshop papers, but not in the actual reviewed articles in the conferences. First one is the lifted actions. So the current model of Laplan is all propositional. Therefore, there's no predicate. We lift it with the parameters x, which is added to the generative model, which makes the entire model compatible with the first order logic rather than propositional logic. What about the temporal actions? We could add a node about the action durations D, which follows a gamma distribution, which makes the entire model compatible with the LTL. So these keywords, compatible is the keyword. And then it needs a very deep understanding of what you are modeling. Finally, the domain symbol and problem symbol. We know that the problem symbol only affects the state representation. Therefore, there are only 2 arrows from P to ZT and DT plus 1. And also the domain symbol only affects the actions and the problems. Therefore, only 2 actions from that. Otherwise, if you don't do this, then you probably likely get the neural network. We don't know what it is modeling and is not compatible with a symbolic system. Okay, a conclusion. We wanted to model a make a logical, rational agents operating under raw observations, and then presented a lab plan, which does that. And then the lessons learned is that each type of symbol requires its own mechanism to learn. And then such mechanism can be mathematically made rigorous by coming up with corresponding generative models. Okay, so this is the journal paper that I'm being submitting to Jer, and then you can find it on arXiv. Thank you for listening.
Thank you for the great talk, Masataro. So let's continue with the next talk, and then Shiki will take over.
Sure. So we are about 13 minutes behind the schedule, but we started late. So so our next speaker will be Leslie Kaelbling. I think many of you know Leslie very well. By the way, Leslie, you can start sharing screen.
Masataro has to let go.
Oh, how do I do that?
So yeah, many of you probably know Leslie's work very well. So Leslie is a professor of MIT and received the Ichikai Computer Software Award, Schreiber Fellow. And one thing pretty significant is Leslie co-founded the Journal of Machine Learning Research about, I think, 20 years ago. And she contributed significantly to a few things that has been mentioned many times in this workshop, including partially observable MDPs. We talk about it a lot, and reinforcement learning. I think Leslie has some concern about current reinforcement learning methods, we'll see. And also pretty recently, task and motion planning. That is something I'm personally very interested in. So with all of that, Leslie, you can start. It's your time.
Thank you. Okay, thank you for inviting me to this workshop, and it's fun to go after Masataro. He and I have been doing some work together, so that's fun. I'm going to start because it's kind of late in the day, and this is a workshop. I'll be maybe just a little bit inflammatory. So I was thinking neurosymbolic, what does that mean? And what I think is, lots of people mean a lot of different things when they say these words. So I try not to say either one, but because this workshop is kind of about that, I thought, well, okay, so what do people mean when they say neural or symbolic? So maybe it's discrete versus continuous. Maybe also people seem to think it has to do with learned or hand-built. Maybe it needs differentiable, not differentiable. There's robust and brittle, interpolates, generalizes, unstructured, structured, approximate, exact, distributed, propositional, local, first order. I don't know. Okay, so I don't think it's productive. I think we need representations of a variety of different properties, but I don't think it's necessarily productive to try to make some set of particular divides between them. And we've been arguing for a long time, I think, about what kinds of pieces and parts we need to put together a kind of a robust approach to intelligence. And there's a lot of different ways we could approach this question. We could try to approach it from the theory of computation, like what really has to be in there in order to do this job. We could try to approach it from the perspective of natural science. We could ask, well, how do brains do it? What has to be in there? I'm going to approach this problem from the perspective of an engineer. So I am just a person who wants to make robots. And so from that perspective, what do I somehow think that I need in order to design and build robots that are flexible and intelligent in the way that I think, would all like? So the way I think about this problem, anybody who's heard me talk lately has seen some version of the slide, is that I have to put in my robot a program. And that's a program that takes the history of observations and actions it's done so far and figures out the next action to take, right? So pretty much nobody would argue about that. And so for me, the whole question, if the hardware is fixed, is what program should go in the robot's head? And one way to think about that is that, so I think of myself as being the robot factory. I have to make these robots, and I have to put some program in the head of all the robots I make. And what program do I put there? Well, I think about, I want to make the program that optimizes in some sense of expectation over the possible environments that this robot might have to go work in, that optimizes its reward over the distribution of environments it has to be in. And one of the reasons I like to think about the problem this way is that we don't have to argue, I think, about the technical details anymore. We don't have to argue about whether it should learn or not, whether it should plan or not, whether it needs symbols or not. In some sense, given this job, given this distribution over possible domains that this robot needs to work in and an objective function, there is an optimal computer program to put in the robot's head to do this problem. So this makes me really happy. I don't like arguing about methodological stuff. This just turns it into an optimization problem. So that seems good. But it's not all good, because now, in some sense, we've said that we understand what the problem is that the robot has to solve. But now we are the engineers, and we have to solve the problem of, given a specification of the domains that this robot is supposed to work in, figuring out what kind of program we should put in the robot's head. And that's actually a super hard problem. So we're back to the methodological problem. I think not really so much in terms of arguing about what has to be in the program, but really how do we, the engineers, have to approach it? Okay, so here's how I think about the problem. So here's my, I don't know, I made up these principles of intelligent robot design. So robots will have to learn about their environment. That seems clear, right? They won't know everything in advance. So there'll have to be some process of information acquisition. Engineers, I think we've pretty much conclusively decided, also need to use learning as a system building tool. So I would say that most of reinforcement learning work at this moment is actually not about the robot learning about its world, but more about engineers using it as a compilation tool, taking a simulator for a domain and turning it into some kind of a program or policy. But in order to get, I think, sample efficient learning and really a compact representation of complex behavior, we need to be able to reuse and combine learned knowledge. I think all this stuff I'm saying you all agree with, I assume. I also think personally, as an engineer, there's no point in learning what we know how to build in. If we care about natural science, or if we're interested in evolution of computational structures, we might want to learn things that we engineers know how to build in, but I personally don't feel the need to do that. We should build in algorithms that enable combinatorial reuse of knowledge. I think people agree with that. And we need to build in algorithms that learn knowledge for combinatorial reuse of a bunch of different kinds. And so to me, all this reuse and combination of learned knowledge is something that old AI people call reasoning. And so the interesting question is, how do we kind of put these pieces together to make interesting and complicated robots? So I am, I think, not very dogmatic and kind of pragmatic. And so I want to learn all the tools, use all the tools we have, all the learning, all the planning, all the representations, whatever we need, I am happy to use it. So let me say something about what I think about reasoning. Again, and to me, reasoning is the following thing. It's a kind of semantics preserving manipulation of representations. So a lot of people lately, even in the reinforcement learning world now, are talking about like learning a latent representation that they can later use for reasoning. Now, some people would call that not symbolic, and to me, it is kind of symbolic, right? They're learning a representation that has semantics. It means something about the outside world, and they develop some method for doing a semantics preserving manipulation of those representations. So I don't know, to me, that's at least in some sense symbolic. But I want to say that this kind of reasoning, this notion of semantics preserving manipulation of representations, is all over in all kinds of things that we do in classical engineering and AI, from Gaussian elimination to convolutional networks to filtering, to value iteration, to trajectory optimization, memory systems, graph search, resolution, theorem provers, sat solvers. All these things are instances, I would say, of reasoning of different kinds, and that we should be free to use all these different kinds of things if they turn out to be useful to us in building the systems that we want to build. Okay, so all kinds of reasoning. So how do we think about this? How do we use these in building systems, right? So one way to think about it is that the reasoning methods, the underlying engines for doing the computation, are something that we've studied for a long time. They're beautiful compositional systems, and we engineers are pretty good at thinking about them. So it might be that an approach to take would be to build in sort of the underlying reasoning machinery, but learn the models that the reasoning, learn about the world, either offline in the factory as we're designing the robot, or potentially also online inside the robot. And we can also learn to improve our ability to reason, right? We can do some kind of learning that makes our reasoning more efficient, which is what really AlphaGo does. Okay, so now I'm going to talk about how I kind of take those ideas, I think, and apply them in the research work that we do, right? So we're trying to make general purpose intelligent robots. Our strategy is to build in some set of reasonably general representation and inference mechanisms. For quite a while, we were hand building things like transition models and inference rules and search control and so on, just to try to be sure that we had a set of low-level structures that we thought would support the kind of behavior that we really wanted in our robots. But now, you know, the view is that we should be able to actually figure out how to learn these things. So what I'm going to do now is just very quickly walk through a set of pieces of research we've been doing that try to learn different aspects, different components of a reasonably generic architecture for an intelligent robot. So there's different kinds of models that we might need to learn. We could learn controllers, right? Low-level controllers, maybe reinforcement learning is good for that. We could learn perception modules, object segmentation, feature detectors, and so on. We might be able to learn some kinds of partial policies, some operator models for planning, some ways of improving our planning, and so on. Okay, so let's now just look at a kind of catalog of ways of integrating learning with also some amount of structure and built-in stuff. Now, I heard Masataro loud and clear. Let me just go back to here for a minute, just so that I can say why I'm not doing what he's doing. The most beautiful approach would be to build the structure, as much structure as we want, maybe not too much, maybe some, I don't know, like Masataro builds in the idea that he wants to be able to use it, say a strips planner or something. We might build in a bunch of different things. And we could say, okay, I'm gonna build this structure and I have some end-to-end notion of what it means to be successful in my domain. So I'm just gonna take this whole thing and train it. And I think if I knew how to do that and I had enough computation and data and so on, then I would find that to be the most beautiful thing. But I don't know how to do that. But I do think maybe that we can find loss functions for the intermediate modules that will allow us to train them individually. And it is true that the whole thing won't be as perfectly optimal as it might otherwise have been, but it might be a more practical strategy for arriving at a system in the end. Or maybe we can do my thing to get a sort of reasonable system and then tune it up end to end. I actually think that maybe that's a good strategy. So I'm going to talk about, for right now, though, not an end-to-end method at all. So one thing we've actually been doing very recently is thinking about how to solve task and motion type problems with no models at all in advance of the objects, right? So most work in task and motion planning assumes that you know models of the shapes of the objects in advance. You might use perception to detect the objects in your scene, but that you know what you're working on. We've been working on this project, which I like to call MOM, for manipulation with zero models. It arrives at the problem believing that objects exist in the world. For right now, we're just thinking about rigid objects, that we know the robot's kinematics, and we know, generally speaking, how to write some operator descriptions for picking and placing and pushing objects in the world. But we don't know what objects we're going to encounter. We don't know how many, we don't know, we've never seen these objects before. And so we're building a perceptual system which uses pre-trained vision modules to do some jobs for us. Critically, we're not trying to reduce this to the previous problem. We're not trying to recover a perfect model of the scene, but we're trying to predict some important features of the objects that we see. So first of all, we need class agnostic segmentation, right? We need to be able to divide the world up into objects. I should say that none of these vision things work as well as you might expect, and it actually takes some substantial effort to kind of use them in a way that gives us a reasonable system. We use something that a trained detector for predicting how to grasp objects, something for completing shapes and point clouds, something for doing some category detections. We take in goals in first order logic, and then we take the observations that we get from looking at the world and we plan to achieve the goals. Why is this going so slowly? So here's a case where we asked the robot to put the objects in a bowl whose color was as close as possible to the color of the objects. But these are any old objects that we just threw on the table. Like, it really doesn't know about these things. It does know that bowls exist. Here we asked it to put objects on regions of the opposite color. It makes mistakes, right? It's going to make mistakes, but it's using a nice general purpose planner, and you can give it high level goals, and the generalization is awesome. Here, it didn't know that cup was there. So when it moved the box, it saw the cup and it figured out how to do something with the cup and so on. So, okay, so there we had learned perception, built-in planning. Another thing we've been working on to account for, in that previous thing I showed you, the robot could just deal with the objects it saw, but more generally, you'd like to move through a house and see objects, remember what you've seen, aggregate multiple observations you've made of something, and so on. So if you look at filtering systems that do data association and so on, we understand a lot about how to build a probabilistic filter. What we've done is we've taken a kind of a structure for a probabilistic filter, but made many of the modules be neural networks. And now we're training just this filter module end to end. And so we end up with, the details are much too much for me to discuss here, but we end up with a system where the robot can drive through like a household type domain. It gets depth images of objects. Here we're assuming that the segmentation works for right now. And it has, the objects can move actually in the world. Some objects, it's kind of an odd world. Some objects hop around among the tables, and the robot has to make predictions about where the objects will be, what objects it's seen, and where it will find them later. And we have a bunch of scenarios with different kinds of objects that move around, and they're not the same objects every time. And it can recover some kind of abstract shape model of the objects and also make pretty good predictions about where it's going to find things that it saw quite a long time ago. Another thing we've been doing is learning abstract models of policies, right? So a lot of people are working on policies for robots, basic controllers that can stir or throw or pour. We're interested in saying, well, okay, you learned a controller that can stir or pour or throw, whatever. We would like to learn a model of it that allows us to add it into our general purpose planning and reasoning system. So take stirring as an example. We might say, okay, I want to learn an operator description, for pouring. We have some low-level skill for pouring. We have, in some sense, a template of a strips or pedital operator with continuous parameters for doing this problem. And it has a bunch of continuous parameters, like the grasp, the sizes of the vessels, the relative pose of one with the other. And what's interesting and important is that there's some constraint, there's some relation on all those continuous variables, such that if that constraint holds and we execute our basic policy, then the desired result will happen. And so we focus on the problem of taking a bunch of examples of pouring in different kinds of circumstances and trying to learn a constraint that represents when it will be successful at achieving the result we care about. We care a lot about sample complexity because we had to actually gather data, and we picked up a lot of beans. But what we get is a system that is, again, kind of reasonably robust. We were able to take those operations and add them into the existing robot's ability to plan and reason about picking and placing. And it can construct plans that combine, takes these objects in any way they appear on its table. It can combine operations there. It's moving the green block out of the way so that it can reach the cup with a side grasp, which is what will allow it to pour, and so on. In that work, it already had the template for the operator, and it knew it just had to learn the constraint. More recent work now, we're also exploring a situation where, given the symbols, it can learn these operator descriptions in continuous domains. And we're working on something now where, in fact, we don't even have to give it the sort of the predicate symbols. Another focus is learning to make reasoning more efficient, so learning search control. We've been focusing on doing that again in task and motion planning type problems, and we're interested in very aggressive generalization. So here's a case where we train on a situation where the robot just has to move the red object into the other room of the apartment. It has to potentially move these other objects out of the way in order to get there. But we wanted to generalize to problems where it has to move arbitrary numbers of these objects into the other room. And also even to generalize to situations where it has to move now small objects around in some cupboards. We're inspired by things like AlphaZero, where learning search control in the form of something like a Q function is useful. Because the number of objects varies across problem instances and we want to generalize over those things, we use a graph neural network. In this graph neural network, we have hand designed some important predicates having to do with whether one object includes the robot's ability to reach other objects. And we learn a graph neural network in a kind of usual way, and we use that to speed up planning, and it makes it much more efficient. Another thing we've been doing is trying to think about how to map a very big problem into a small one. Rather than trying to scale our planner up to solve really big problems, we try to scale the problem down to fit inside our head. So we've been working on scoring objects, taking large domain problem instances, but learning to predict which objects are going to be relevant to a particular start and goal state. Also learning how to reduce the size of the state space by reducing the size of the search space by reducing actions, saying some actions might not be relevant, or by forbidding ourselves from going into some parts of the state space. So if we can learn to reduce the state space, that's also very important. So I've given you this very fast tour through architecture for robots, a strategy for learning a bunch of pieces and parts that really mixes together all kinds of aspects of what we talk about when we talk about neurosymbolic, whatever it is: discrete, continuous, learned, design, propositional, lifted, deterministic, probabilistic, differentiable, somewhat robust, somewhat generalizing. And I just want to emphasize that I don't really care what it is or which pieces and parts we use, as long as it can let us do the job that we really want to do. So I have 17 seconds, so thank you.
Thank you, Leslie. We'll take questions after the three invited talks in the panel session. So Emery, are you ready?
Okay, hello again. So Luís, if you can share your screen.
Yes, I will.
Okay, then yes, we can hear you. Let me introduce Luís Lam. He was a full professor and Secretary of Innovation, Science and Technology of the state of Rio de Janeiro do Sul, Brazil. He was formerly Vice President for Research and Dean of the Institute of Informatics at the Federal University of Rio de Janeiro do Sul, Brazil. He holds a PhD in computer science from Imperial College London and diploma of Imperial College. So his research interests includes neurosymbolic AI and the integration of learning and reasoning and AI fairness. Yeah, actually he is one of the persons around that I have seen who has written a lot and then who gives a lot of enlightening talks about neurosymbolic AI. So he was a must to be invited person, and I am very happy that he accepted our invitation. So the floor is yours. Thanks a lot.
Thank you. Thank you so much for the invitation. It's an honor to be in a robotics venue. RSS, of course, is a great conference, and so is the workshop. I've been with Leslie in another panel a few months ago. I'm a great admirer of her work, Leslie, on robotics. And I also think in terms of making things work. And I never understood about this divide, as you mentioned, because they are AI techniques, and in science, we want to make things work. And I bring this picture here just to motivate that these guys, these people here, they were interested in advancing science, advancing knowledge, and we are living in an era where advancing knowledge and science is extremely important. We've been through this pandemic where I've been pretty much involved in the pandemic here, managing a scientific committee, and we have a meeting of our state scientific committee after this meeting here. So in addition to trying to run my small lab, I am running the other issues that are perhaps more important to humanity at this day. So let's move forward. And in this 20 minutes, I try to give you a general overview, because my research has been at the core, at the foundations of Neurosymbolic AI. Because since the beginning, from 20 years ago, what we are trying to do was to show if neural networks could learn to reason in a more formalized way. So several people here, I like Masataro talks, I like Leslie talk, they use several forms of reasoning. And what we do in our work is to try in a formal way to show correspondences between these two approaches, to show what kind of logic, what kind of formalized reasoning neural networks can perform and learn. Of course, learning is at the core of the research, but also we see further interests in a number of fields that now are coming to the fore. For instance, in any other field other than the typical fields that of computer vision, robotics, and natural language processing, we've seen some interest in places like software engineering. We've seen some tools for programming that perhaps will make programming easier in the next few years. And this subject area is also important, because if we are going to do computer programming using machine learning approach, we of course need much better tools for verifying this kind of systems. And system verification is another field that in the near future we can imagine that we'll have a lot of attention to. So I'll give you a brief overview of the field. I'm not focused too much on our research of our group, but I can mention to you by the papers we've been putting on archive that we've been dealing with integrating graph neural networks and symbolic reasoning in addition to symbolic learning, and dealing also with combinatorial problems, combinatorial optimization. So, but I'll give you a general overview, not too much of our own research here. And this is a paper that we post on archive by the end of last year. We have we tried to write this paper to explain what neurosymbolic is to a much broader audience. And this may be an interesting read if you want to come to the field, because you kind of understand the overall perspective of what's going on in the research work of several people who have contributed to this particular area. And the questions we try to answer, of course, it's a very old question here. It's not a very innovative question, but we can say that already Turing asked one of the key questions in AI is if computers could think. And we've been doing that for the last 70 years in AI. We're trying to make digital machines, as Turing said, to think and learn about the world. And this tension between reasoning and learning, it's quite interesting, because Les Valiant, in one of his books, probably approximately correct, from 2013, this is a very interesting book that I think should be much more cited, mentioned, and talked about in AI. It's an extremely interesting book by Les Valiant. Of course, he's a brilliant researcher. And he tells about the story of the tension between learning and reasoning already among the Greeks 2,000 years ago. And giving and jumping forward to our times, if we want to make machine learning even more vibrant that it's already is. It's already on the news and mainstream news every day. But as scientists, we have, and engineers, as Leslie said, engineers put forward extremely important contributions in terms of reaching to the people. We have to do with several issues like causality, issues like security that is becoming even more interesting and more relevant these days, fairness, ethical issues, but also interpretability and verification and validation. And this kind of particular questions in terms of interpretability, verification, validation are typically tackled in AI and computer science using, let's say, techniques that come from the symbolic schools. If we can put this divide, I also follow what Leslie says. I am interested in making science and engineering progress, not into making divisions among people. So perhaps that's one of the reasons that tacitly I came to this field and tried to work on neurosymbolic, on the field that is called neurosymbolic AI. And just to make you a few comments here, we are in a different venue. Perhaps you don't know that by the early 2000s, it was extremely rare to see any neural network paper, even at NeurIPS conference. I remember that I was at NeurIPS early 2000s presenting a paper on reasoning about time and knowledge in neurosymbolic systems. And one of the guys who came to our poster asked, why are you using neural networks? And then I said, well, I am at NeurIPS. I suppose that the N in NeurIPS means neuro. So that's one of the reasons that I want to remind you that this kind of techniques were not very popular like 10 years ago. We know the story, we know that neural networks came to the fore, but then people started asking too, why are you using logic if you can do absolutely everything with deep learning? Well, it's not so true that you can do everything with deep learning. Leslie has described a number of applications that she works on making robots to reason, and of course they use symbolic techniques integrated to learning techniques. Also, Masataro talked about his very interesting work, and he's using several logics to make his work to progress. And our aim here is to find perhaps what's the best representation, not only for knowledge, but what's the best representation for the integration of these fields. How can one integrate neural networks and symbolic reasoning so that we have even more efficient AI tools and tools that are comprehensible? And there have been several recent debates about this talk, about this subject field, AAAI 2020, AAAI 2021. There has been several debates, several venues where you can see people that come from outside AI, even like Daniel Kahneman has been very prominent in these debates because people have related these two schools of neural networks or fast reasoning with system 1 and system 2 that would be more related to logical reasoning, that will take a lot of time to think about what you're doing. But however, even Daniel Kahneman, he stated that in his view, these two systems are integrated. You cannot separate system 1 and 2. They're not separate systems in terms of human cognition. But for that, you have to talk a little bit about this subject with Daniel himself. And I also want to make a bit of let's say a commentary about other subjects that are related to what we've been talking about. Cognitive scientists like Gary Marcus or even Daniel Kahneman, they have been working on reasoning and learning for a long time. I believe that we should have a look at how this results from this community come to AI and how they can contribute to make more effective robots. That's of course is the interest of people in this workshop and in this conference. And most of the results, or many of the former results and results in the early 2000s have been summarized in this book. But we find quite interesting that we can use this book to produce recent results that have application these days. For instance, when one tries to explain natural language processing systems, or when one tries to formalize and to improve the verification systems using some form of connectionist systems that I will talk later on, we see that results that we developed in the early 2000s were already very useful. This also rings a bell. On the other day, some guy told me that when he was reviewing one of the papers, I had cited a paper from 20 years ago. The guy made a commentary, well, this paper is from 20 years ago, I said. And then in one of my replies to reviewer 2, I said, well, Ian LeCun's paper on CNN is from the 1980s, and Jeff Hinton's papers come even late before Ian LeCun's paper. So we shouldn't judge science for the age of the papers, but we should judge for the results that science and the utility of the models and the predictive power of models and other scientific concepts. So I'm not going too much into this divide, but just to make sure that for people who have not heard about the symbolic schools and the connectionist schools in AI, we can say and can state, and our AI history tells us that Alan Newell and Herbert Simon, who are of course pioneers of artificial intelligence, they would belong today to the symbolist school because they used to use logical reasoning and logical formalism to develop their work. Of course, we have the connectionist schools represented here by the deep learning pioneers or the deep learning fathers of the AI revolution. But we also have people who believe that this integration should be done both at the foundational level, and also we should not forget that there are other subjects, other concepts that we have to take to the fore to make AI and machine learning more effective. For instance, Judy Poor has been the pioneer of the use of Bayesian methods in AI, but he's also defended the point of view that causality is at the core, not only of reasoning, but also of machine learning. And we've seen several interesting papers. There was a paper on arXiv by Yosha Benjo last week about the use of causalities and causal models in machine learning and so on. So what we seek here is further integration, not further divide between the fields. So coming here to more semi-technical stuff, one can say that perhaps the first try to build neurosymbolic AI systems was to represent propositional logics, propositional rules within neural models. And one of the first systems to allow for learning with background knowledge in neural networks was the system known as K-BAN by Jeff Tao and Jude Shavlik from Wisconsin. This system was influential because it showed that one could perform, for instance, DNA sequence analysis. It was a promising approach that was further extended to include relations in the form of first-order reasoning, predicate reasoning, or fragments of first-order logic. We know from logics that first-order logic is undecidable, so one has to work with fragments of first-order logic that can cope with the needs of certain applications, the needs for certain tools that can be formalized or reasoned about using first-order logic. So these were some of the first works. They seek to use propositional logic and learn propositional logic and logical rules within the framework of simple multi-layer perceptrons or other models based on recurrent networks. Later on, we asked ourselves, if we want to build richer models, if we want to make representations, for instance, of temporal reasoning, of temporal notions, of relationships between states, state evolution, knowledge evolution in time, one would be, it would be needed to represent in an effective way, for instance, the concepts that come from temporal logics, from linear temporal logic or branching time temporal logics. There are, of course, several different temporal logics. And also, if you want to deal with the knowledge of agents in AI, one could think in terms of how to represent a modal logic or an epistemic logic. And this kind of work we did in the early 2000s and around the 2010s, because we showed that some form of connectionist model would be able to represent what we call temporal model programs or temporal logic programs, and they would be able, in a way, to represent and to compute the fixed point programs, the fixed point, the fixed point semantics of logic programs that included, for instance, a temporal dimension or a dimension based on knowledge. And we run several experiments, several test beds that are very well known in the world of multi-agent systems and distributed computing, such as the Muddy Children puzzle, the Wise Man puzzle, and other typical problems that one encounters in distributed systems, such as the Dining Philosopher's problem. So at the time that we did that, there was not much interest in representing and learning to compute this problem. But nowadays we see that there are a lot of interest in the effective ways of representing time. The notion of time in computer science, of course, is very relevant. And we also published a few years ago a paper on how to represent temporal evolution in time and how knowledge evolves in time, and neural networks can learn to represent the evolution of the knowledge of particular agents that interact with each other in branching time or linear time. This can be found in some of our papers too. So the point that we're trying to make here is that in order to have a richer neurosymbolic AI systems, one has also to deal with the different kinds of reasoning that need to be represented in deep learning systems or in neurosymbolic AI systems. And we claim here that we have, in order to have adequate expressive power in terms of dealing with different applications, we have to develop systems that can represent, for instance, temporal dimensions or epistemic dimensions and probabilistic abstractions in a proper way. And this is the challenge that we have these days. And if we want to find inspiration from that, one can look, for instance, at a very well-known paper in symbolic AI and multi-agent systems. It's this book on reasoning about knowledge by Ron Fagin, Joseph Halpern, Yoram Moses, and Moshe Vardi. And they explain how multi-agent systems can be formalized, specified, and reasoned about. And what we want to tell you here is that if we want to develop systems that will be able to represent propositional logics or represent first order logic, one also has to take into account that several works in AI and several schools of AI, if one looks at multi-agent systems, for instance, that has a strong relationship with some works in robotics, people use different kinds of logic that are more appropriate to have the right abstraction level, the right level of abstraction to represent some concepts such as interaction between agents and knowledge exchange. And this work motivates us to think about how to compute and learn with symbols that go beyond propositional logic, that symbols that go beyond first order logic, and systems that are able to represent, in the end of the day, reasoning rules. And when one works with formal logics, there are three key components. There is in logics you have a syntax, a semantics, and a proof theory. This proof theory can be represented via axioms, but it's not very useful for us in computer science to think in terms of axiomatizations of some logical theory. We need to get off the ground, and in order to get out of the ground, we have to develop reasoning procedures or decision procedures for a number of logics. And if you wants to reason using a connection systems or using a deep learning system, one, in the end of the day, will have to learn how to reason. And in order to learn how to reason about certain logics, one has to learn about the reasoning rules. And here I bring as an example, these are quite simple rules that in a system called natural deduction that are used in model logics. And this is just to give a glimpse of what the kind of work that one has to formalize to solve this kind of puzzles using a neural network. And in order to solve these neural networks, of course, you need to define and to design the proper algorithms that will be learned by the neural networks. You have to find ways of showing proofs of soundness, that the results of the inferences that in the end of the day that you have the neural networks correspond to the logical inference that you have in symbolic systems. But also what is interesting here is that we have to show that what we are learning to do is to adapt, for instance, in the case of software engineering, to adapt the evolution of the system and to represent the evolution of the system in time. This is another work that was done quite a few years ago by one of our students, was perhaps one of the first works where one considered a model checker. And on top of a model checker, we aggregated a neural network approach or a neural model that would be used to refine the counterexamples that were produced by the model checker to refine the specification of the system. And in this sense, what we're able to do here is that we could use systems models or models that of some particular kind of systems, models that were specified using a temporal language. And if this language can be used then to specify a system, and this system then can be subject to verification in a model checker, one can use the counterexamples that model checkers output, and these are very useful information that can then be used to refine the model. And the counterexamples are used as inputs to the adaptation engine. We call here an adaptation engine that comes from let's say the jargon of software engineering, but this adaptation engine is no more than a simple learning algorithm that refines the specifications and then can refine the behavior of the system to correspond to the desired specification. So the point here is that in addition to investigate several foundational issues, one also finds applications for the representation of logics in neural networks. The point that we're trying to sell here is that when one works at the foundations of neurosymbolic artificial intelligence, by learning how to reason about different logical systems, one can also use this foundational work in applications such as verifying the behavior of systems, verifying specifications of software systems, and several other applications. And finally, one application that was done here, for lack of time, we don't have too much time to explain the applications. A few years ago, TNO, which is an organization associated to the Dutch government, used the systems of integrating temporal logics and neural networks in order to make the training assessment in driving simulators. Because when one is able to learn temporal information, one is able to learn about the evolution or learn new information from observations of new situations that appear in time, so new situations that drivers are confronted in time. And of course, there's the link here for one of the first papers in the subject that was published at IJCAI 2011. And finally, I bring you the challenge that we have here in terms of the foundations of neurosymbolic AI. As I mentioned, we are working at the basis of this field. Of course, this can be extended further on to applications. To represent first order logic and higher order knowledge extraction from very large networks is still an open challenge in neurosymbolic AI. Of course, we say it's an open challenge because we have to make sure that this extraction is provably sound and efficient, of course. And knowledge extraction is important because it is related to the issue of explainability of neural networks. Another important subject in terms of neurosymbolic reasoning and neurosymbolic AI at the foundations of the field is to deal with co-directed common sense reasoning and efficient combinatorial reasoning. And of course, combinatorial reasoning is very important because in a way, one can draw parallels with foundational works in computer science. And if we can learn how to effectively compute or effectively present solutions to combinatorial problems, such as NP-complete problems, problems based on graphs, we find a number of potential applications that will have better results in terms of applications outside AI. And finally, in terms of natural language processing or natural language interactions, another field that has received a lot of attention recently deals with the human communication networks. Because if one wants to use, for instance, large language models in a way that people can benefit from the use of large language models, one has to be sure that the semantics of the output and the way that large language models work and provide inferences and results for us is represented in a way that we are sure about the semantic interpretation of the output that language models provide to us. And finally, I want to apologize for running a little bit too much here. I had prepared, I noticed a little bit too much material, and perhaps I should have focused less on a few topics. But I will be open to answer your emails later on. Thank you.
Yeah, I think the presentation and the time was perfect. Thank you very much for your talk, Luís.
I had to, Emre, I had too many slides. Sorry, I apologize for that. Sorry.
Yeah, but all of us enjoyed your talk. I think there's no problem at all. So now we will continue with the final panel discussion. Now I will hand over to Shiji again. Shiji, are you there?
Yes, I'm here.
Okay.
So do you want me to lead the discussion?
Yes, and I can help.
All right. So I can probably ask the first question. Well, hope that the audience can either put it into the chat or there is a reaction button in the bottom. You can click and say raise hand, and then we can you can take the microphone to ask a question directly. So I've been thinking that we have a neurosymbolic, so we need to know neural network, and symbolic, we need to know some logic. And if we talk about those language action systems, then it's even more complicated. So when we have the knowledge, we can plan at the task level, motion level, and we need to perceive the environment. We have PDDL, different kind of things. But really, suppose that we have a new student who doesn't know much about the field. How should we get this new student started? It seems like there are more and more things, and I have to give the whole AI history and robotics. There's all kinds of planning. And so is there a friendly way or an efficient way you feel for a new researcher, we can quickly get a new student get up to speed and to very quickly get into the current state of art? Okay, we can contribute to this so-called neurosymbolic and different kind of planning learning. So what should be the correct way or correct path we can bring a new researcher up to speed? So I don't know, maybe this question is to any of the panelists.
Luís, I guess Luís.
Yeah, I follow the same attitude as Leslie. It doesn't matter. It's not interesting for science to divide people. We have to think in terms of achieving better results for humanity. That's the goal of science, is to improve humanity. So there are foundational topics that are very important for any student. If you think in terms of undergraduate students or even graduate students that have a different background. I would say today that it has become more and more clear that foundational topics in computer science are at the core of a very good education. If in a certain way, these new tools and programming languages have made programming more accessible, what we see in terms of research results is that these very complex systems produced by companies, by the tech companies, they demand students that are very good in computational complexity, students that are very good in formal logic these days, as we are seeing, not to mention probability and statistics, and the core subjects of computer science. And I would say that even though computer programming is more accessible these days, By the time I studied computer science, it was much harder. Let's say we still used assembly programming and this kind of stuff that students don't see, maybe. But I would say that core computer science subjects are very important to bring students to have this vision that computer science has a foundation. Computer science is a very solid field that's becoming more and more relevant to any walk of life. And so we have to prepare students technically and give and provide them a very sound foundation. On the other hand, as computer science becomes more influential in the world, we also have to make sure that students have a sense of the consequences of their technical work in terms of ethical principles, ethical subjects that engineers and doctors have in their undergraduate degrees, and that in computer science used to be much less common than and much less usual than it is, for instance, in medicine. So I would go for a very solid core subjects associated with some subjects related to the ethical implications and social implications of computer science that are becoming more and more clear these days. Thank you.
Thank you, Luís.
So Mohan is raising his hand.
You want me to go?
Sure, yeah.
Sorry, can you hear me first? Sorry, my reception network is poor, so I keep asking this. Can you hear me?
Yeah, we can hear you.
Okay, so I had probably one direct question and one general discussion question. So one direct question was, is Leslie still here? Oh, she is. Okay, so this is, I know this is supposed to be to all panelists, but I will ask anyway. So Leslie, in her talk, she talked about this manipulation with models or without models and so on. I was hoping if I could use this discussion time to get her to talk a bit about what is given to the system and what does it figure out or learn over time in order to be able to finally get to manipulate those objects. Maybe if she can talk about that. Then I have another question, but I'll wait. Let's see.
Yeah, I can just say briefly. It's a task in motion. It has built into it task and motion planning. So it understands that there are objects in the world, that they take up space, that it's a robot that has kinematics that moves through space. That's all built in. What it doesn't know is the number, type, shape, anything of the objects that will be given to it. So the goals are described in terms of quantification, right? You can't designate particular objects except for in terms of their observable properties. The one that kind of interesting insight we had when we built that system, and it's just the first version of something that should grow to be much better, but it's a basic thing that's still kind of cool, is that what we did is we reformulated the planning theory to be in terms of properties of the objects that we had perceptual modules that could detect, right? So we don't ever really need the complete shape of the object. We need to be able to generate plausible grasping transforms. We need to be able to detect faces of an object where we think it could rest stably. We need to make a prediction about whether this thing would crash into that thing as we're moving it. So we may have to generate a convex hull, or we did alpha shapes, which are another kind of shape approximation. But I think what's interesting is that you don't have to reconstruct the world from perception, because you can't, and that to be driven by the queries that you really, really, really need to answer in order to do your planning, and just try to build perception that will support those queries.
So could I just ask one quick, probably yes, no kind of question? What I was not grasping is, in order to be able to talk about these things, there must be some grounding of some vocabulary that must be given to the robot, right? It should know what, for instance, color shape means and what, I don't know, red, blue, green means. I'm being too simplistic. I've not read your paper, but there must be some grounding that the robot.
So some basic predicates. So basically, if you want to be able to supply a goal in terms of some vocabulary, you need perceptual detectors that detect those properties of objects. So we're agnostic about what those are, but you would have to supply them.
Okay, so do I have time for one follow-up discussion question that would go to all panelists, or have I lost my chance? Somebody has to tell me. Who's?
Yeah, I guess the quick question is fine.
Okay,
yeah.
So I was curious if I could latch on to Shuchi's your question and ask a more sort of like,
like these days, like, so I'm partially answering and partially posing this question, I guess. It's like, part of this, in order to train students, to me, comes down to making sure there are enough courses or modules, whatever you want to call them, in our curriculum, that teach them what we consider to be essential, right? I mean, other research things they can pick up by looking at surveys, but oftentimes these days, even things like a course in machine learning or AI is very skewed. So I was wondering if if I could get the panelists because they all have a rich experience of teaching and stuff, to talk a bit about what they consider would be essential components, a sort of short list that they think could be taught in a basic course in AI, or sort of like, that would prepare students for taking on something like this. At, say, graduate level, so to speak. Let me make it specific.
Leslie?
So math. I think a really good grounding in continuous math, which AI people have traditionally not had, is becoming more and more important.
Engineers do.
Excuse me?
Engineers do, computer scientists
don't.
Don't.
Right. But I think to be, the modern AI person needs just a ton of discrete and continuous math, right? So logic, combinatorics, continuous, and so on, and they need to be able to think straight. And I frankly think that once you know that stuff, then you can read the things that you need to read in order to do the particular problem that you're trying to take on. So I think as long as they're agile, and I think our bigger problem is like figuring out, it would be lovely to pick a set of papers that are really, some papers are beautiful, some theses are beautiful in terms of the way they lay out a space, right? So I think having a nice set of monographs and survey papers is important. But trying to say, oh, they need a course in this particular meta learning, or they need a course in kinematics, I'm not sure that will be profitable. We'll quickly fill up, more curricula than anyone could ever actually study. But if you ask yourself, how many of you had courses in the subject matter that you actually work in? At least for me, it's like I didn't. And I think that's true for most people. So don't worry too much about that.
I would agree with you, but I wanted to ask in general what panelists thought. Let's see. Yeah.
I tend to agree, Mohan. I think courses in the foundation of algorithms, computational complexity, and continuous math these days, as Leslie said, are becoming more and more useful in computer science too, in addition to the core subjects. Yeah.
All right. So thanks. I think Emery has raised hand for a while. Do you have a question?
Yes. Thank you. I have many questions actually. Finding these many senior people in front of me. So my question is related to this big question, or the popular question. In George Konidaris, I think he left, but he said that, okay, he has a system, and then he emphasized things, and he said that in order to do classification, he used SVM, but he can also use neural networks. So that part is not that important. But he also does clustering with other methods, for example. And then Leslie told that whatever the toolbox has, then it's fine to use it. And Masataro, for example, in his system, so he used these deep learning techniques, and we always say that deep learning techniques work very well, perform very well in classification regression, but not only that, like we can use them for clustering, we can use them for dimension reduction, like Masataro does. So my question is, taking into account, for example, Masataro's system, which is a very systematical way to approach symbol emergence and predictive system, and then uses the same architecture whose input and outputs can be connected to each other. So is deep learning methods, advances in deep learning, not really a game changer in abstractions, in symbol emergence as well, or still they are just another toolbox methods? So that is the question to any panel member.
Maybe this time we can start with Masataro.
So I kind of failed to get the actual question. So do you ask something about? How do I answer this?
So maybe my particular question for you is, was it possible to use any other machine learning method other than deep learning method and then obtain similar architecture, similar generality, similar results? Or did you really need those particular deep learning methods?
Okay. Maybe that's something related to what Leslie mentioned in her presentation. Like she mentioned that it's some of the her systems are not deep learning, and also yes, I also said that that the existing systems tends to contain non-neural system but machine learning system, and then they are like kind of bunch of stuck together. Yes, I said that. Well, after I said that, I thought maybe that was a bit of overstatement. Yes, like yeah, I could replace part of my large neural network, like just part of it with a random forest, and then still could, well, we don't know how to do this, like how to combine, for example, random forest and the rest of the neural networks, or like everything as a random forest. But yeah, if that engineering question is solved, then, well, as long as the learner is a universal learner, then I don't think there's much problem. And then I also like, as long as the optimization objective is something that makes sense statistically, such as like something that exactly mathematically guarantees that it matches the maximum likelihood objective. So, I figured out rather my main complaints to the, yes, this is just a ranting of, to the connectionist community. Well, lots of papers, they add a bunch of losses here and there, but like not many of them are statistically making sense as a statistical model. That's more of my complaint. So even if part of the neural network is replaced by something non-deep neural system, as long as the objective makes sense from the statistical point of view, I probably don't have much complaint or the like problem. Does that answer your question?
Yes, thank you.
So Luís and Leslie, do you want to add anything or we move on?
I do. I have to leave in 1 minute. Sorry, I have another meeting, and it has to do with the pandemic. I want to add that what we aim to do is to explain actually what's going on in deep learning models, and we believe that symbolic techniques can contribute towards the same, because when we deal with logical systems, one has to have a very sound semantics to explain actually what's going on. And inference is a very well-defined process. And also all the contributions that people from the semantics of computer science have brought to computer science, those techniques perhaps can be used in machine learning too. But I have to leave now. Unfortunately, I have a meeting to deal with the pandemics here, and I hope we can meet again. Please stay in touch. Contact me by email or via Twitter, direct message, or what you find more adequate. Thank you so much for being here, for listening to me. It's been a pleasure. Thank you. See you soon, guys. Bye-bye.
Right.
Thank you, Luís. Thank you.
Thank you, Luís.
I guess I would chip in one more comment to that question, which is, I think, again, when you say, is it important to do deep networks or whatever, deep learning, that is a constellation of so many things that I think the question is not exactly precise, right? So you could say, well, is it really important that we're doing gradient descent in a large continuous model? You could say, is it really important that we're doing end-to-end training? You could say, is it really important that we have an over-parameterized model that has certain properties? So there's this constellation of ideas and technical aspects that arrive with deep learning systems. And you know, it seems clear that some of them are very capable and very important for some parts of some problems, but I don't think anybody understands well enough exactly what they contribute and how to design systems. And it's fascinating to watch how originally, basically everybody was doing continuously parameterized feed forward things of a certain kind, but now graph networks or learning latent spaces for planning, people are gradually recruiting ideas that come not from the continuously parameterized function world into structures and architectures that we call neural, but I don't know if those words are meaningful anymore. So yeah.
Thanks, Leslie. So we started a bit late in this session. We're supposed to conclude at 5:10, but we started a bit late. Maybe we can take one or two more questions. So Jacob, you raise your hand. Do you have a question?
Oh yeah. So I'm the new student you referred to in this field. So I'm pretty new. So I really want to learn more about the knowledge representation. So as Leslie said, and there are many ways to represent knowledge. For example, there are neural nets. There can be logic, and there can be Bayesian inference for like representing the knowledge a robot has learned, right? So I just wonder, what are your point of view on the development, like of the future of such kind of knowledge representation? What do you think? Do you think like parametric ways are some kind of better ways, or do you think non-parametric parametric way can also be useful? Because as far as I know, like non-parametric method are kind of like pretty hard to scale to large data set, right? So that's my question.
By non-parametric, do you mean things like nearest neighbor where you remember the data? I just clarify one little bit.
Yeah, or like Bayesian and stuff. I really like Bayesian ways, but I find it hard to actually use it in practice.
Yeah, I mean, I think we all have a tendency to want to have a simple solution, right? It's romantic to imagine that we just have to get the one mechanism right, and we do that, then everything will fall into place. And I guess I am somewhat skeptical about that. And my sense is that lots of different representations are good for different things. But I agree with you that, I mean, I actually am delighted that you asked that question, because I think that we really deeply fundamentally don't know. And a lot of problems in robotics now are exactly about the fact that we don't know how to represent information very well. I don't think we understand how, think about your kitchen. Think about your kitchen. Okay, you know a lot about your kitchen. How should that be stored? How did you acquire it? How do you use it? What are the queries? What are the updates? You know, a giant RNN could in principle be trained to be whatever it is that you use to remember what you remember about your kitchen. But I think that we can help systems by designing some more structure into them. And then now the deep question is, well, what structure, right? What is the CNN? What is the underlying structural stuff that we can build in so that the system can learn some aspects, right? It seems clear that it has to learn how its sensors really work and that stuff, but how do you design representation so that you can learn the models that you need to keep that representation updated? So I don't know, but I think that's maybe the most important question, at least for me at the moment.
Thank you.
Thanks, Leslie. So I think we can maybe just take one last question from Albert, and I see other people raise hand and maybe hands off. Again, we can take that offline. So Albert, can you make it brief? Yep.
Yes, thank you for all the good talks. I want to build up on the Emre's question and make it more precise. So we know that, so the main fundamental point of deep learning is to structure, place the architecture, make a deep architecture so that the architecture can learn increasingly complex abstractions based on simpler ones. So we know that, okay, and I think the main success of deep learning is because of that. And the questions for neurosymbolic methods, should we learn? Should we build abstractions from using the symbolic parts, or learn the more complex abstractions using the deep networks? So, where to start building up modular representations, from the neural part or from the symbolic part? Because we know that we can use deep networks to learn very complex abstractions for vision and formation translation. Okay, for some problems it doesn't work, like reasoning, it cannot produce very good abstractions. So should we introduce more inductive biases to deep architectures, or give up at some point and use more symbolic logical reasoning part to build up good abstractions?
I mean, Masataro, if Masataro wants to answer, he should. Otherwise, I can answer.
Can I answer first?
Yeah.
It's a short one. I think I believe the actually, so they don't contradict with each other. Yeah, okay, it sounds like Leslie also has the same opinion. I don't know. So being able to do the logical reasoning should be a very good prior information, or the inductive biases. Like, we don't want to have contradictions. That's one way to, like, just one example. But mainly that is the base idea. That's what I believe. And like in my example for the classical planning, yeah, effects should not depend on something or something else. Those kind of restrictions are, yeah, yeah, the inductive biases. So yeah, that's my answer.
All right. So Leslie, do you want to add anything?
Well, no, I was going to agree with Masataro and elaborate just a little bit, right? Which is that I think that dichotomy, making a dichotomy like that, is actually kind of harmful to our ability to design interesting systems, right? There's no, what's the difference? I don't know what the difference is. Is a graph neural network symbolic or is it not? I don't know. We need to design some structure and some bias, and eventually the bias becomes so biased, maybe you would call it symbolic, I don't know, but we just have to match the bias to the problem that we have and find good loss functions and good search algorithms, and I think not worry about what we call it. That would be mine.
Sounds good. Okay, I think that's all for our very last panel discussion, the third one. So thanks again to all the invited speakers and all the discussions. Thank you. And next we are moving to contributed talks session 2. So Oliver, do you want me to lead the transitions, or you want to do it?
It would be better if you can lead the session, because I have a contributed paper too.
Okay.
So.
Okay. Oh, I see. Yeah, that makes sense. Okay, so then we have a sequence of 6 2-minute lightning talks. So I think we are all in US time, so hopefully the time is good for you. Okay, let's get started. The first one is Nako Goplan. I think I saw Nako.
Yeah, shall I share my screen?
Yes, please.
Can you confirm that you see the screen?
Yes, we do.
Yes, we can.
Oh, I'm sorry. So hello everyone, I'm Nako Gopalan, and I'm going to present my work that I did with Matthew Gombolay about learning goal-based abstractions from human teachers. So we're interested in the problem of how humans teach robots tasks, and specifically, like, how do people actually teach these robots tasks? One way to think about it is that if users wanted to teach the robot to write one word, dog, then they might just provide a single trajectory to write this entire demonstration. But if we wanted to teach all the words in the English language, then we would probably break it down into the abstractions of individual letters of the alphabet. But using such a strategy is not trivial because not everyone can break down music pieces into individual notes, or it's not trivial to break down computer programs into functions so that you can generatively code these functions. So we investigate the behavior of people when they're trying to teach tasks to robots using demonstrations. And specifically, we ask the following questions. Can we expect for people to teach robots using abstractions? And what would induce the use of abstractions when teaching tasks? And would the abstractions that the people will teach finally be actually useful for the robot to solve tasks? Our domain consists of a soil robot on which people demonstrated tasks using kinesthetic teaching. And the task itself was to create soil mixtures with sand, lime, and manure as shown in the diagram. So there are many types of demonstrations that people could give, but we specifically care about the ones that have better abstraction. So if they teach a single trajectory to pick and place things, as shown in the leftmost figure, then they can only solve one task and the agent can't do any novel tasks. A better approach would be to teach picking and placing one object at a time, because at least then the robot can do compositions of 5 cups of sand and 6 cups of lime and things like that. A better approach would be if they broke down individual picks and individual places of objects so that the agent can actually pick and place objects from different locations on the table. So this is the best abstraction that the agent could be given. So our results finally showed, so we conducted a study with 28 subjects, and our results showed that initially, when you don't prime people at all, they don't use abstractions to teach the agents at all. When you do prime them with specific language, you can get over 85% of the subjects to actually give demonstrations using abstractions. But only 25% of the participants actually provided useful abstractions that could actually generalize to pick and place locations from different locations in the table itself, which means that there's a correspondence problem in teaching agents teaching tasks to agents in a generalizable way so that the agent can solve novel tasks. You're welcome to come to my poster, and I'll glad to have more discussions with you then. Thanks a lot.
Thank you, Nakul. And our next speaker, I think, is Jacob Xiaochen Li.
I'm sorry, I'm just trying to stop sharing and I don't know how. Thanks a lot.
Yep.
All right, just give me a second. Let's see. You guys see the screen now?
Yes, we do.
Okay, let me start the slideshow. Okay, here we go. Hi, this is Xiaochen Li. Today, I'm going to present this efficient hierarchical navigation and manipulation by constraint-induced option reward design. And this is joint work with Zhao Huang and Hao Su. So, wait a second. Okay. Our motivation is that humans have prior knowledge about the structure in navigation and manipulation tasks to solve them efficiently, but existing reinforcement learning method hardly benefit from the prior knowledge and need to discover policy structures with a sacrifice of data efficiency. Oh, wait. So, for example, as a human, we know that when we are asked to put stacks into the required place, we usually follow the implicit order, which means that we are not going to move the second block until the first square is put into the right place. Thus, we propose to use constraint. Wait, is it like auto-playing? Anyway, so we propose to use constraint to inject proper inductive bias in the hierarchical RL agents to enable fast and structure exploration. Here in the visualization of the workflow, we can see that the green block is selected by the high-level policy to be the first block to move. Under this option, our low-level agent selects actions by first approaching the green blocks and then picking it up and putting it into the appropriate locations. Assume the job is done in K steps, the high-level agents again proposes a new option. In this case, the yellow block is selected. The key takeaways from these examples are that the complex problems can be formulated into constraint-based hierarchical RL problem, and the constraint imposed on low-level agents are options selected by the high-level agents. To achieve such mechanism, we introduce an intrinsic reward that takes in options as input, which low-level agents later need to maximize when selecting actions. We also introduce an augmented option critique structure so that our method can be fully off policy, and we don't need any other off policy correction to deal with the instability issue. We also compare our approach with both non-hierarchical RL method and the hierarchical RL method with off policy correction. And the first two experiments are navigation task, and the third one is a multi-object manipulation task. We can see that our augmented option critique approach, which is labeled AOC on the graph, successfully solves all the environment and surpassing all the baseline methods. And if you want to learn more about our work, please come to our poster session. Thank you. I think that's it.
Thank you. Our next speaker is Emily Shees. If you're ready, please share screen.
All right. Hello, everyone. My name is Emily Sheets, and I work in the Laboratory for Progress at the University of Michigan. I'm presenting our work in composable causality and semantic robot programming. So in this project, we consider assembly tasks, which are challenging because they often require robots to reason over many objects and their affordances, as well as perform multiple objectives simultaneously, such as moving while avoiding obstacles or positioning and aligning object parts at the same time in order to actually connect them together. Robots can perform multiple objectives using what's called null space composition, which allows the robots to execute multiple behaviors such that they don't conflict with one another, and also induces a priority between the behaviors. In general, users will hard code these priorities between behaviors for the compositions based on their experiences with the controllers. So for example, a user might tell the robot to always prioritize maintaining grasp closure on an object over moving the object to a different location, which is what we see happening in this video. But rather than rely on predefined priorities of controllers from the users, we want robots to autonomously determine how to compose controllers and perform these multi-objective behaviors. So to do this, we provide the robot with declarative knowledge in the form of what we call a causal control basis, which contains the motion primitives the robots can execute, as well as hierarchical temporal and causal information that the robot uses to predict the composed effects of these multi-objective behaviors. The robot uses the given causal control basis to predict the transition probabilities of all possible compositions of the controllers, and then uses these transition probability predictions to determine which composition is most likely to result in a successful connection. The robot then executes the composition that is most likely to be successful in a variety of furniture assembly tasks. And we actually see that the robot is able to successfully perform the appropriate multi-objective actions when connecting object parts and assemble the pieces of furniture. Taken together, our work demonstrates that causal information about motion primitives allows robots to reason about and perform complex multi-objective behaviors autonomously. Thank you, and feel free to stop by my poster to discuss more.
Thank you, Emily. Our next speaker will be Mateo Guaman Castro. I think the first author, Ivana, is not here.
So can you see my screen?
Yes.
Okay. Hello, my name is Mateo Guaman Castro, and I will be presenting a framework for creative problem solving through action discovery. How can an agent discover new actions when the original actions it knows are not enough to solve a task? This may happen when novelty is introduced in the environment, the original model of the environment is not accurate, or the agent faces a novel task. Creative problem solving allows an agent to discover new actions to accomplish a previously unreachable goal. We perform creative problem solving through action discovery, combining two levels of abstraction as follows. In symbolic planning space, the agent tries to reach a goal state using its original symbolic knowledge base. When the plan executor fails, either during execution or fails to achieve the goal state, we enter sub-symbolic parameter space, in which the agent performs action primitive discovery through interaction with the environment to expand the capabilities of the agent and update the symbolic knowledge base. In this work, we introduce two types of action variation methods: variation through segmentation of existing actions and variation of the parameters associated with the execution of these existing actions, such as rate of movement, orientation, or magnitude of movement. In our first experiment, the goal of the robot is to reach the green block on the other side of a sliding wall, which is lowered when the left button is pressed. However, the robot only knows how to do an instantaneous push button action. Through action segmentation, the agent discovers the action keep pressed from segmenting the push button action to lower the sliding wall and reach the green block. In our parameter variation experiments, the agent discovers variations of the original actions to solve a simple cooking task when the environment changes. For example, it learns a nudge action from the original push action when the cover of a cup becomes lighter. In this work, we contributed a unified framework for creative problem solving with two action discovery methods: In future work, we hope to use reinforcement learning to extend this framework to continuous robotic state spaces and learn an auxiliary model of the world. We'll also look into methods for liable and creative problem solving that minimize destructiveness of the environment during discovery. For more information and details, check out our presentation. Thanks.
Thank you. Our next speaker is actually my student, David DeFazio. Are you there?
Yep. Okay, hi everyone. So my name's Dave. I'm a PhD student in Chi-Chi's lab, and I'll be discussing learning quadruped locomotion policies with reward machines. So there exists two common approaches to achieving quadruped locomotion. One of the more traditional approaches is to use something called model predictive control, where we assume that we have access to a dynamics model. However, often that's an unrealistic assumption in the real world. And then another approach is to use reinforcement learning, where we learn through trial and error experiences. However, this has issues in that oftentimes you need a prohibitive amount of experience to learn what you want. And also it's oftentimes hard to be able to define specifically what you want through reward engineering. So in our case, that would be learning specific styles of quadruped locomotion. And so we address the issues with reinforcement learning through using reward machines. We introduce human knowledge via linear temporal logic formulas. So this formula above here says that we want to keep the front right and right left feet in the air, while the front left and rear right feet are on the ground. This formula defines a pose that the robot could be in. And then in the reward machine below here, we want to encourage transitioning between these two poses. So the one pose, we want front left, rear right feet in the air. And then the next pose on the way back, we want the front right and rear left feet in the air. And this reward machine encourages going back and forth between the two poses. And that will ideally encourage locomotion in the exact style that we specify. We run simulation experiments with a Minotaur robot. Notice in the figure here, the red circles indicate the foot contact points. So we learn 3 styles of locomotion. And again, to reiterate, the advantages of our approach is that it is easier to specify diverse quadruped locomotion behaviors. And also we take advantage of reward machine algorithms to be able to more efficiently learn these behaviors. Thanks, and I look forward to discussing this more in my poster.
Thank you, Dave. And our very last lightning talk is provided actually by one of our wonderful organizers, Alper. So whenever you're ready.
For the kind introduction, Shichi. So let me start the timer. DeepSym and Neurosymbolic framework. By the way, can you see my screen and hear my voice? All right.
Yes,
a neurosymbolic framework for symbol emergence from interaction experience. So we would like a robot to discover symbolic representations solely from the interaction experience with the environment. And to do that, we propose a framework that consists of 4 stages. In the first stage, the agent interacts with objects with its predefined set of actions. Then using the continuous high-dimensional continuous state representation, it learns we train a deep neural network to predict the generated effect of the executed actions given the depth images of the objects. After learning the discrete representation, so this is basically an encoder-decoder network with the action is concatenated with the bottleneck representation, but with a little twist. So the bottleneck layer is actually a binarized representation, just as in Masataro's work, but with different kind of binarization. After learning discrete representations, using the discrete object representations and effect representations, we can train a decision tree so that we can extract probabilistic rules from the branches of the tree to convert the rule into a PDDL operator then using this PDDL operators, we can actually do planning. So now I will show some of the steps. Here are some interactions with the objects. So it's basically pushing from different directions and it's taking action. And this is the basic structure of the network. It takes a depth image, binarize it with binary activation, and you use the straight-through estimators for gradient backpropagation, and it predicts the generated effect. And here the effect is the change in position of the object. You can see some example outputs of the encoder here. So different objects are categorized in different categories, but some objects here in the third row are in the same category because the generated effect for a given action is the same for these objects. So the agent cannot tell the difference between those objects because the generated effect is the same. So this is the main idea behind this network. And let me skip these ones and show some results. So here how we convert the decision tree into a PDDL rule. Each node in the decision tree represents a precondition, and the leaf of the tree represents the effect. So after learning such PDDL operators, we can actually tell the robot to construct the tower using 4 objects with a height of 1, and the robot successfully executes the plan. Here is another plan with different objective. Instead of height of 1, here we tell to construct a tower with height of 4. So that's basically all. There are some limitations. We predefine the actions, but it's pretty hard to learn the actions together with the object symbols themselves. So it's not very end-to-end yet. So we do some feature engineering in the FX space, but we think it can be solved using the state-of-the-art neural nets. And for other problems, we can talk in the cluster session. Thank you for the time. And this work is supported by TÜBİTAK program. And it's a national funding program in Turkey. Thank you.
All right, so thank you, Albert. Now we are done with all the presentation sections. So next it will be our poster session in the Get-a-thon. And it's a good opportunity for social activity there. So I know it's a long day. I mean, it's already very late in some countries, some places. So if you need to grab a drink or something, please feel free. And also it's okay to have some food. So maybe in a few minutes, let's meet in Get-a-thon. Let me put the link, Get-a-thon link in the chat box. So just in case you don't have it, here is a link, and hope to see you guys there in Get-a-thon in a few minutes, and all the posters will be presented there. So thank you very much. That's the end of this session. Thank you. So Albert, do you have anything to add? Or any of the organizers?
I just want to add that, let me just share my screen one more time. So this workshop is from our, so several organizers are actually supported by the national funding program of TÜBİTAK. I just want to give the acknowledgement to the TÜBİTAK, and that's all. And thank you for all the participants to come and listen today. It was a wonderful workshop for me. So this was the first workshop that I participated as an organizer. And I think it was a great experience. I want to thank all the other organizers and thank all the speakers and participants. Thank you all for listening and coming today. I guess we are going to share all the talks. So all speakers are agreed to share their talk, and those are probably will be hosted in the workshop website.
Yep, sounds good. So if no one have anything else, then I think we can move to Get-a-thon. Thank you. All right.
Thank you. Meet at Get-a-thon in a couple of minutes.
Yeah, see you guys there.
Should we close the Zoom session?
That's what I'm thinking. Maybe, but I'm afraid maybe someone don't have the link. Yeah, maybe we can turn it off.
Maybe we can post a little bit more. Maybe someone will come and ask some questions.
Okay. Or we show the Guidathon link on the screen, so everybody's.
Okay.
Yeah, then go there. Yeah.
Okay. Yeah. See you at the Guidathon.
Yeah. See you.
See you.